Uh, Welcome to the post-lunch session. We have 5 speakers in this session before tea break. Shouvik Datta is the first speaker. Then Aritra Ghosh, Debangshu Mukherjee, Naveen Prabhakar, and Himanshu Parihar. These are the 5 speakers. The first talk is 25 minutes and then 5 minutes question and answer. The remaining 4 talks are 15-minute talks. So without taking much of your time, I now request Shouvik to start. He will talk on operator growth in 2D CFT. So Shouvik, I will remind you after 20 minutes, or you don't need any reminder?
Yeah, you can remind me after 20 minutes.
Okay, after 20 minutes, I will remind you.
Yeah.
Please go ahead.
Okay, thank you, Prasanta. Thank you to the organizers for giving me this opportunity to present my work here. So I'll be talking about operator growth in 2-dimensional conformal field theories, and this talk is going to be based on a paper which appeared recently with the same title, and it was done with 𝗰𝗶𝗶𝗀𝗀 from the University of Warsaw. Okay, so let me begin with some introductory and motivational remarks. So let's start really simple, and let's take a quantum mechanical system and a local operator O, and let's consider the unitary evolution given by the Heisenberg evolution of this operator O. And it's given by this, and as we know very well, you can use the Baker-Campbell-Hausdorff formula, and you can rewrite this as a power series for small times, and you get nested commutators with the Hamiltonian of this operator O. Now, O can be a simple local operator, and the Hamiltonian can have few body interactions. But even if this is the case, the effect of this operator O, if it's a local operator, it spreads out. It spreads throughout the system at later times. So this is this phenomenon of operator growth, and it is a route to understand irreversible macroscopic behavior, how it emerges from the microscopic or quantum mechanical details of the system. And the idea here is that the information or the excitations once stored in simple local operators, it scrambles into a large number of degrees of freedom at later times. Another way to say this is that simple operators grow into ones with higher complexity. So these are just words, but I hope to convince you by the end of the talk that one can make these ideas quantitatively precise. Okay, so just to proceed, let me just introduce some notation. We call this operator as the Liouvillean. This is nothing but the commutator of an operator with the Hamiltonian itself. And we can therefore rewrite this series as this exponential of the Liouvillean acting on this operator O, okay? For instance, this third term over here is like 3 nested commutators. You can write this as L cubed acting on O, okay? So that's the Liouvillean. Now, I was saying that operators grow, so let's now try to look at an example just to make this idea very concrete. Let's consider the Ising model. So this is a 1-dimensional Ising model with nearest neighbor interactions. And you turn on magnetic fields along the Ising chain as well as perpendicular to the chain. Okay, so this is a non-integrable model and exhibits chaotic features. And let's ask the question that how does an operator, so this is nothing but a Pauli matrix located at the first site, how does this operator grow with time? So let's look at the terms in this expansion, okay, over here. So for the first term, you can just use the Pauli algebra to evaluate this very easily. You get a sum over 2 terms. If you do it again, you get a sum over 6 terms. And if you do it once again, you get a sum over 13 terms. If you do it even one more time, you get a sum over 41 terms. But the point is that you get increasingly large superpositions of Pauli strings. So for instance, over here, you can look that we started at the first site as a local operator, but over here, when 3 Liouvilleans act on this operator O, you actually get a linear combination of operators that has support over the third site now. So it's the effect of the operator does spread as time progresses. So we need to make this evolution and try to measure this growth. So one concrete way to measure this growth, which we heard about in the first day of this conference, is the out-of-time ordered correlator. So over here, what we do is to take the commutator of the evolved operator along with the probe operator and look at the expectation value of the square of this commutator. And since this becomes a very complicated operator at late times, it fails to commute with simple probe operators. And that fact is reflected by an exponential growth of this expectation value. So by now it's known very well that this growth is characterized by the Lyapunov exponent, which has an upper bound given by the inverse temperature beta over here. So this growth or this measure of operator growth invokes additional probes. However, we would like to quantify the growth without using additional probes. And thereby the hope is that one can extract the truly universal aspects of this phenomenon of operator growth. So the way to do this is one way to do this is something called the Langsos algorithm. So let me introduce this in the first few slides and then mention what physical implications it has. Okay, so it's always good to keep this Ising model example at the back of our minds. And and now I'll be a little bit more general and abstract. Okay, so the Liouvillean evolution, it gives us a set of operators. So we start with some operator and generate more operators by acting the Liouvillean on this operator O. It's nothing but nested commutators acting on the operator. Okay, so pictorially, you start with this operator O, and then at the first step, like L1, L times O, you get 3 operators, for example. Next step, you get even more operators. And in the next step, even more, so on and so forth. What we want to do is to compress this information somehow and see how the growth happens. So that's what we want to do. We want to compress this information. So what we do is to orthonormalize. So we generate new superpositions at each step, but what we do is to orthonormalize with previously generated operators. Okay, so you get an operator O1 by orthonormalizing with respect to O and O2 by orthonormalizing.
You mean Gram-Schmidt, right?
Yes, Gram-Schmidt. Yes, you can exactly that. Yeah, with some particular inner product, which is up to you to choose. Yeah. So that's basically Gram-Schmidt, and so you orthonormalize, and this set of vectors is called Krylov vectors on the Krylov basis. And then you can see that the action of the Liouvillean on one of these Krylov vectors leads to a superposition of 2 other Krylov vectors, the neighboring ones, with some particular coefficients, which are called the Langsos coefficients. For instance, if the Liouvillean acts on O2, it gives a superposition of O1 and O3. Okay, and so by compressing this information, we have this one-dimensional chain. Note that this green dot over here is representative of this complicated superposition over here. Okay, so the further you go along this chain, you encounter more complex operators. So measuring some average position along the chain at some later times gives you an idea of how complex or how complicated your operator is. And that can serve as a measure of operator growth. So I'll be more precise about this in a few slides. So, okay, so we looked at the Liouvillean evolution, got a bunch of operators, orthonormalized it, got the Krylov basis. And by the action of the Liouvillean on one of these operators from this Krylov basis, you can get transition amplitudes, which are nothing but the Langsos coefficients, as I showed in the previous slide. And one can also find what the evolved operator or the evolved state is, and that is given by the action of the Liouvillean on the operator itself. You can re-express this as a linear combination of the Krylov vectors. And the coefficients appearing in this linear combination, these are these wave functions. By some abuse of terminology, it's called, the wave functions, okay? So these encode the probabilities that you reach a particular the nth operator at time t, okay, by taking the mod square of these wave functions. And these Lang's coefficients these wave functions are not unrelated. You can take a time derivative of this equation, and then you can see that it obeys a Schrodinger-like equation, which takes us far. Okay, so this is a bit of formalism, but what is this good for? So this formalism actually provides some bounds on operator growth. So, so the Lang's coefficients, they can actually characterize operator growth. So it can be seen that you can look at the asymptotics of the Lang's coefficients at large n's, which means like far further along this chain. And what happens is that in chaotic theories like the SYK model, it has linear growth. Whereas in integrable models, like some integrable spin chains, it grows as the square root of n. And in free theories, like the Ising model with no magnetic fields turned on, it saturates to a constant. Okay, so this has been seen in a variety of examples. So these observations actually led to this operator growth hypothesis. It was conjectured by these authors. And so the Lang's coefficients, physically speaking, these provide local velocities along this chain for operator spreading. Okay, and the operator growth hypothesis says that in a chaotic quantum system, these Lang's coefficients are just these transition amplitudes while going from one dot to the next dot. These should grow as fast as possible. So the velocities are the fastest in some sense. And so this is the upper bound.
What is the assumption that the Hamiltonian is local and the operator is local?
Yeah, the operator is local. The Hamiltonian has got local interactions, yeah.
Okay, otherwise it can go. If it's non-local, then...
Well, if it's non-local, even then this
will still be, this bound will hold?
Yes. I will just mention that in a minute. Yes. So so this Lang's coefficients, they are upper bounded, like the growth is upper bounded, and it has to be linear. So this has got the same flavor as the Bieber-Bach conjecture, which we heard about on the first day. Even the notation looks very similar, but I don't know whether there is a relation. So the fastest growth is linear, and there's analytic evidence coming in favor of this. So this is related to the question which Suresh just asked. So if you look at the large QSYK model, so in this large QSYK model, you have a Q body interaction. So, and if you look at the large Q regime of it, so this is non-local in some sense, but it's analytically solvable. And the large QSYK model, it actually saturates this. It can be seen that it saturates this upper bound. And there's also mounting numerical evidence in support of this conjecture. And if the Lang's coefficients, they grow maximally like this, if it saturates this, then and this implies an exponential growth of the size of the operator. Okay, so now what do I mean by size? So a measure of operator size is like the average position along this chain. As I said, this green dot is representative of like all these green dots appearing over here. So measuring some average position along this chain gives you a measure of operator size or operator complexity. So if you know the evolved state or the evolved operator, you know this wave functions phi n, which give you the probabilities of being in a particular site along this chain. And from there, you can evaluate the average position by this weighted sum over probabilities. So this is the location, and this is the probability of being in that location. Okay. And as I mentioned, if the Lang's coefficients have linear growth, this quantity called the Krylov complexity, it grows exponentially. Okay, so its exponential grows exponentially fast, far away along this chain to a very complicated operator. Okay, and eventually in today's talk, we'll be interested into the CFTs. So it's good to consider the Lang's algorithm in situations where you have got additional symmetries. So the action of the Liouvillean on the n-1 Krylov vector gives you a linear superposition of neighboring vectors from the next and the previous side over here. And the matrix realization of this Liouvillean just follows from here, that it takes this stripe diagonal or this tri-diagonal form, which is of this. This looks very much like a tight binding model Hamiltonian. So in cases where you have symmetries, like you can have like raising and lowering operators or ladder operators, you can realize the Liouvillean as L plus and a linear combination of L plus and L minus. And the action of L plus on a Krylov vector takes you to the next one, and the action of L minus on a Krylov vector takes you to the previous one. So that's something which can be useful for 2D CFTs. Okay, so now the question I would like to ask is that what happens in 2D CFTs? So we know in 2D CFTs, we have an enlarged or infinite dimensional Virasoro symmetry coming from the modes of the stress tensor. And due to this additional symmetries, there are exact degeneracies coming from the descendants. Okay, so consider a primary operator and let's look at its Fermat module. I mean, there are exact degeneracies at various descendant levels. And we shall be considering irrational holographic CFTs in the stock, so 3 greater than 1. And we roughly have in mind a putative holographic dual in ADS3. These theories should exhibit chaotic features and also should thermalize because we know there are black holes present in ADS3. So one question which I would like to ask here is that how do operators, like simple operators in CFTs like primaries or the stress tensor, how can we analyze the growth of these operators? Okay, so the standard CFT Hamiltonian is given by the 0 modes of the stress tensor, and it's given by this, so this is well known. However, primaries and quasi-primaries, these are eigenstates of this above Hamiltonian, and therefore the time evolution is trivial. It just gives an overall phase, okay? So what we do here is to make matters more interesting. We pick a different evolution or a different way to drive the system or quenching the system via a unitary protocol, okay? So this is a different Hamiltonian, if you like. This is made out of the linear combination of L1 and L minus 1.
I have a question.
Yeah.
So you're saying that quasi-primaries are eigenstates of the Hamiltonian, but what about the secondaries and the others? They are not eigenstates, right?
Sorry, what do you mean by secondaries?
The others, what do you mean by quasi-primaries? What are the other sorts of operators?
Yeah, I mean, all descendants are eigenstates of the Hamiltonian.
Descendants, yeah.
So I mean, we always think of the Hilbert space of CFTs, and whatever states appear over there, they are eigenstates of the Hamiltonian. So
what I'm saying is if you start with the descendants, then maybe you could still generate such a thing, right?
Yeah, descendants are also eigenstates of the Hamiltonian. I think there is no confusion here. We can discuss this later on. So maybe I should proceed. So we pick a different evolution or a quench protocol, which is made out of the linear combination of L1 and L minus 1, which is this. And this choice is not ad hoc. Like we heard about adding inhomogeneities in CFTs in the first day. And you can realize this Hamiltonian by adding inhomogeneities. And there's also an interpretation of this as the evolution by the modular Hamiltonian, as was shown by these authors. Okay, so we have this unitary, and the action of this unitary on this primary, on a primary state is just given by this. And you can expand this exponential, and it's, as you can convince yourself, it's just going to be a superposition of descendants of the primary's Fermat module. Okay, so that's what it's going to be. So you might think that, okay, so this is like just various powers of L minus 1 acting on this primary operator. However, these states for example, n-1 with various powers, these have got non-zero overlaps with actual Virasoro descendants. So these are the elements that actually appear at the corners of your Cax matrix. And the very fact that your Cax matrix has got off-diagonal elements means that the usual Virasoro basis which we work with, this is not an orthonormal basis. Okay, so for instance, this is an overlap of two level 2 descendants in the Virasoro basis, and which has got non-zero overlaps. So they are not orthonormal. So we need to find an orthogonal basis or an orthonormal basis in order to track the evolution more carefully. So thereby we can build the Krylov vectors, as I was mentioning previously. So one can build an orthogonal basis by using what is called the oscillator basis or the oscillator formalism. So the Virasoro algebra and its generators can admit a differential operator realization in terms of an infinite collection of oscillator variables. So this is very much like the simple harmonic oscillator, in which you can realize the oscillator algebra in this way, and which is realized through this differential operator and this variable like this. And the Virasoro generators, they can be realized in terms of an infinite collection of these oscillator variables. So the details don't matter, but one can construct an orthogonal basis using this formalism.
Sorry, Shouvik, you asked me to remind you after 20 minutes, so
okay.
I just...
Thank you. Yeah. Okay, so once this orthonormal descendants are constructed, these are essentially given by monomials of these oscillator variables, suitably normalized. And there's a one-to-one correspondence between this orthonormal descendants to integer partitions. So these are raised to various powers. And if you calculate the L0 eigenvalue of that, you can find the descendant level to be an integer, and each of these states, they have a one-to-one correspondence with integer partitions. And there's also a one-to-one correspondence of integer partitions to Young diagrams. So just to illustrate this, let's look at level 3 descendants. So in terms of oscillator monomials, they can be realized as U1 cubed, which corresponds to the partition 1 plus 1 plus 1, and it corresponds to the Young diagram given by a single column over here. And 3 can be written as 1 plus 2, which corresponds to this Young diagram and this oscillator monomial. And 3 can, of course, be written as 3, which is given by this Young diagram and this oscillator monomial. So one important thing here is that we are working with irrational CFTs, and in order for this correspondence to work, there should be no null states, and there aren't any null states in irrational CFTs, so we can proceed with this. Okay, so let's see how the Lang's algorithm works in 2D CFTs. So as I said, the evolution is given by this. And what we need to find is the action of L1, L-1 on specific descendant states, because these are orthonormalized descendant states. Now we can realize these descendants as Young diagrams, and the action of L-1 adds a box. So a box can be added to this in 3 ways. And the action of L1, it removes a box, and that can be done to this Young diagram in these 2 ways. So that's shown over here. Actually, this action of L1 and L-1 is a part of a bigger picture, which is called the Young's lattice. So the idea here is that you start with a primary, which is like descendant level 0. You add 1 box, you go to descendant level 1. You add another box to this box, you go to descendant level 2, so on and so forth. So the Young's lattice is a graph or a lattice with Young diagrams at its vertices. And the edges or links or bonds of this lattice, they correspond to the addition or the removal of 1 single box. And in order to relate these things to the Lang's algorithm, the weights associated to the vertices correspond to the wave functions of the evolved state. And the weights associated to the edges, they correspond to the Lang's coefficients, which is given by this. So just to contrast this with the usual non-degenerate case, we had a single one-dimensional Krylov chain, but that generalizes to this degenerate Fermat module because we have exact degeneracies, and there is no way to compress this information. Okay, so the Young's lattice provides a generalization of this Krylov chain into the CFTs. So one can actually evaluate what the Lang's coefficients are using the oscillator formalism. And the Liouvillean matrix, it takes this tri-block diagonal form. So each block connects to nearby descendant levels, like this over here. And there is a further reduction because only the non-zero contributions comes from nearest neighbors of this Young's lattice, and that is shown over here. And the standard non-degenerate case, recall that that took this simple tri-diagonal form, and the generalization of that is this tri-block diagonal form over here. Okay, so the weights of these edges are given by the Lang's coefficients. This is something which we can evaluate analytically using this oscillator formalism. So let's look at this. So if we proceed along this path, along the Young's lattice, the leftmost one, so this is just a single row diagrams. We can evaluate this analytically. And if you take the large n limit of this, you find linear growth. Similarly, if you go along this rightmost edge, you find a square root n growth. And actually, you can evaluate the Lang's coefficients between any two descendant states. For example, between two typical states as well, you can evaluate what it is. But the essential point over here is that you do get linear growth along the leftmost edge of this lattice. And you can plot it numerically, and it shows linear growth over here. So the fastest growth can be found on the leftmost edge of this lattice, and this saturates the conjectured upper bound on the growth of the Lang's coefficients, which is this. So we can track the evolution further by evaluating the evolved state or the evolved operator very explicitly. And that is going to be a linear combination of descendants of this operator O, since it's a primary. So it's going to be a descendants of this primary O. And we can get these wave functions very explicitly. And from there, we can calculate the probabilities of reaching a particular descendant state at time t. So it's given by the mod square of these wave functions. And it depends on the specific details of the integer partition, and it's given by this. So what do these probabilities encode? So it encodes the information about the chances of reaching a specific descendant state at time t. So the picture in terms of the Young's lattice is as follows. So at t is equal to 0, the probability is peaked at the primary state. And then as time progresses, this probability actually spreads out into higher level descendants. Okay, so operator growth under this protocol into the CFTs, it can be realized then as spreading into this bath of descendants of the primary's own Fermat module. So that's how it happens. One can actually plot these probabilities. So the probabilities of the probability of remaining in the primary state, it actually decreases exponentially with time. One can also find this through the autocorrelation function. So this is measuring the overlap of the evolved wave function with the original state, and that decays exponentially. And at late times, what we see is that it becomes a superposition of very high level descendants. That's what we see over here. One can use these probabilities to find the average layer of the Young's lattice reached at time t, or the average descendant level reached at time t. So that's encoded through the Krylov complexity, and it's given by this. And this quantity shows an exponential growth. So we see that this primary operator, it grows exponentially into a complex operator. So it's a complex high-level descendant. And this result is universal, and it applies to all C greater than 1 CFTs with zero symmetry. So I realize that my time is up. So let me just take 1 more minute, if that's okay.
Yeah.
Sorry. So just to conclude, we saw that operator growth into the CFTs can be realized as spreading along the Young's lattice. And we also found the saturation of the conjectured upper bound on the Lang's coefficients. And we could evaluate the probabilities of reaching a specific descendant state at time t. And the Krylov complexity, as expected, it showed exponential growth. So there's a laundry list of extensions which one can think about. So I considered a single operator, but one can think like, what if we have more than one operator or like operator products? One can ask like, what happens in minimal models? I considered irrational CFTs over here, or CFTs with higher spin conserved currents, symmetric orbifolds, or the half BPS sector of n = 4 super Yang-Mills. Now, this might look like a very odd list of topics, but if you forget about the first two examples, in all these cases above, the states or operators do admit a Young diagram-like description. So it would be nice to see whether the picture of the Young's lattice can also be applied to study operator growth in these settings. So that's all I have to say. Thanks for your attention. Yeah, and I'm sorry for going over time.
Thank you, Shouvik. So we have several questions. Somadat, please go ahead.
So time evolution can take place only through the Hamiltonian, right? So I don't understand how you can have a
So this is a deformation of the Hamiltonian. So usually the Hamiltonian, you can write it as some integral of the stress tensor. Now you can put a specific envelope function in front of the stress tensor, which is like adding some inhomogeneity, which is going to lead to this operator, which I showed you. It's going to be L1 plus L minus 1. Yet another way to think about this is that, okay, you're not exactly doing time evolution, but you can use the Baker-Campbell-Hausdorff formula to decompose the unitary, which I wrote down as a combination of translations, special cut form 1 translations, and dilatations. And you're studying operator growth under that. So yeah, so that's a perfectly physically well-defined evolution. Yeah.
So Aninda?
Hi, Shouvik. Thanks for a very nice talk. I had a question regarding the calculation of the Lang's coefficients. So when you calculate the Lang's coefficients, you have to implicitly or explicitly choose a norm. So were you using the Frobenius product?
Yeah. So over here, the oscillator basis provides you with a specific norm, which is just the simple norm between two descendant states, and that's what I was using.
And would this conjectured growth of Bn be sensitive to the norm?
I think not. I think there has been like studies like with using the thermofield double norm, for example. And even in that case, I mean, this is within the limits of this conjecture. Yeah. So I think there has been different norms studied as well. Yeah.
Okay, thanks.
So Ravi?
Hi, Shouvik. I have two questions. So first is related to what Somadat already asked, but can you take the perturbation to be something proportional to L0? And what happens in that case?
So as I said, like, I mean, if you take a primary operator and if you add L0 on it, it essentially just gives you the conformal dimension, right?
Right.
So it's not something which is
interesting,
non-trivial. Yeah.
Okay.
So it just gives you a phase. That's all. So yeah. So in order to like make it more interesting, one can study evolution under other unitaries. I mean, this is like choosing, I mean, in the quantum information parlance, if you like, I mean, this is like choosing a specific quantum circuit, which is built out of a unitary operator.
Okay, and so in the derivation, is there anywhere that you restricted to? So basically, I suppose your derivation is completely, it does not depend on the specifics of the 2D CFT in the sense that whether it's vacuum or finite temperature or torus CFT.
Yes. So yeah, that's a very good question. So the only thing which I assumed is a C greater than 1 irrational CFT. That was the only assumption over here.
Okay.
And this result applies for that. Now, you could study like operator products instead of one single operator. That would give you more details about the OP coefficients and the spectrum of the theory. But for the setting which I considered over here, I mean, I don't need any other assumptions. Yeah.
Okay. Thanks.
Okay. Before we go to Sunil, we have hands raised up to Loga. Any new hand raise will not be permitted in the interest of time. So Sunil, please.
Yeah, Shouvik, very nice talk. Can you just mentioned to Surabhi that this result is where your results are valid for C greater than 1 irrational CFTs.
Right,
but
right.
where did you actually use the fact that they are irrational?
Yes, so that was used when I used this correspondence of descendants to integer partitions and then to Young diagrams. So if you have got null states, which is, for example, in rational theories, there will be a reduction in each descendant level, and then this corresponds.
But you're looking at Virasoro descendants, right?
Yeah, it's Virasoro descendants, but
so for C greater than 1, there are no Virasoro null states, but there are still rational CFTs.
Yes, but this is irrational. That's what
I'm asking. Where did you use that? You're saying that you use the fact that there are no null states, but even though there are no null states of Virasoro algebra, you still have irrational CFTs.
Yeah, so that's
sorry, you still have rational CFTs.
Yeah, so if you have rational CFTs, then there will be null states, right?
Not of the Virasoro algebra.
Yeah. Okay, yes. Okay, very good. So over here, I restricted to the case that my symmetry algebra is just Virasoro.
So you assume that there's no extended chiral symmetry?
Yes.
Okay.
So that was important. Yes, thanks for the question. So no additional conserved currents, no double algebras, no supersymmetry. Yeah.
No Kac-Moody currents in particular, which are quite generic. Okay, thanks.
Yeah. I should have emphasized that. Yes. Yeah.
Argue?
Yeah. Hi, Shouvik. Thanks for the good talk. So the operator growth that you are showing on the Young lattice, that reminds of this Planck growth, right? So in that growth, normally we have a limit shape kind of thing where if you go to large n, then you have a particular representative or particular Young diagram which dominates.
Yes.
So is there something happening here? Is there any dominant thing in the large box limit or something?
Yeah. So that's shown over here. Like I showed the typical states. So in the large n limit, I mean, it goes to a limiting shape, and then you can evaluate what the Lang's coefficients are like between two typical diagrams or two typical descendant states, and that turns out to be this. I mean, there are also some interesting combinatorics, which you're also familiar with, like with Vershik and Krylov and Logan and Shep.
Yeah, that's what
those combinatorics actually enter and they provide some bounds on the norms of these operators. Yeah, you can find details in our paper. Yeah.
Oh, sure. Thanks.
Yeah.
Pratik?
Hi, Shouvik. So my question is regarding the asymptotically growth of this Lang's coefficient. From which range of n you are taking this asymptotics? Because after the large n, this bn should come down to 0, right? Because we are going to the end of the Krylov space. So
yes. So what you just said is true for a finite dimensional quantum system. It's not true for an infinite dimensional quantum system like a quantum field theory. You're right, like this that this Krylov complexity exponentially grows and then it saturates, and that fact is true only for finite dimensional quantum systems, not like something like a CFT. So these keeps growing, and it keeps growing forever.
Okay, so even in a finite dimensional system, so from which n you can call this Lang's coefficient? I mean, this
that's not something which is I can't give you like a number for it. Yeah, but it's large enough.
Yeah. Okay. Thanks.
Buddhaditya?
Yeah. Hi, Shouvik. Thanks for the wonderful talk. My question was regarding the different growth of Lang's coefficients that you see for different directions in which you go along the Virasoro algebra, the Varma model. So, what is the explanation for that? Why is it different?
Yeah, so if you look at the Lang's coefficients in detail, I mean, these actually depend on the specifics of the descendant state, actually. So it depends on the integer partition, the details of the integer partition. So that's the reason why you see different numbers for it. For instance, over here, you see I've labeled the Lang's coefficients like between two specific Young diagrams. So there is a very fine-tuned dependence on the details of the integer partition. So that's why it's different,
Okay, I see. So it's sort of like it's chaotic along one path and
yes,
integrable along the other things.
Yes, something of that kind. Yes.
Okay, thank you.
So last question by Logan.
Hello, Shouvik.
Hi, Logan.
Nice talk. So I wanted to ask just two questions. One question is, you had chosen a particular kind of evolution with L1 and L-1.
Yes, yes.
Can I do this with other Virasoro generators and so on?
Yeah. So sure. I mean, as long as it is unitary, you can do it. I mean, you can choose LK, L-K. And yes, this can be done. Like, I mean, then you don't go between nearby layers of the Young's lattice, but you jump across K layers one at a time. Yeah, but it can be done. It can be calculated using.
And you think the results will be similar?
Yes, the results will be similar, but this K dependence is going to enter. Yes, actually for like SL2R, like you can take like LK, L-K and L0 and like massage the generators a bit, and this also forms an SL2R algebra. And like the K dependence enters in some way, but the form of the results, they essentially remain the same. Yeah.
Okay. So just one more question, and like since you were talking about this in terms of Young tableaus and so on, yes, do you think there is a way to think about this in terms of some matrix model or some fermions and so on? This particular evolution model.
Yes, there are a lot of similarities, but yes, I don't know. Yes, I mean, very similar things arise in that case as well. Yeah, but I don't know at least like how to make some precise connection at this stage. Yeah.
Okay. Yeah. Okay. Thanks, Shouvik, for very nice talk, and I'm sorry for not taking any more questions. So Shouvik, please stop sharing. Now we have Aritra Ghosh, who will talk on contact and metric structures in black hole thermodynamics. Aritra, please share your screen.
Okay, so am I audible?
Yeah.
Okay, good. Let me try to share my screen.
So you have 12 minutes and then 3 minutes for question and answer. I will remind you after 9 minutes, okay?
Right, okay. So are you able to see my screen?
Yes.
Okay, so let me go to this full screen mode.
Full screen mode, yeah, you can go.
Yeah,
good.
So this is visible, right?
Yeah.
Right. Okay.
Please
so
go.
So thank you, Prashant. So I would like to begin by thanking the organizers for this opportunity. And the title of my talk would be Contact and Metric Structures in Black Hole Thermodynamics. And it's based on work done with Chandrasekhar Bhamdipati. So the brief outline of my talk is as follows. I'll begin with some motivation. Then we'll do some brief recap of symplectic and contact geometry. And after having done that, we'll actually look at some geometrical aspects of thermodynamics and Hamiltonian description of thermodynamic transformations. And finally, I'll actually give maybe make a few remarks on metric structures and thermodynamics, and we'll exist by pointing out a few existing challenges. Okay, so all of us know that black holes are associated with the notions of entropy and temperature, which are given by these relations, at least in Einstein gravity. And the first law of black hole thermodynamics kind of looks like this for a Carrollian black hole, where the last term, the P, this arises from a cosmological constant. So something that all of us are aware of is that thermodynamic variables such as P and V, or T or S, or maybe omega and J, with J is angular momentum, these things always appear together. So this is something we have seen way back from our high school days, that we have terms such as S, dt, and TdS. They always kind of stick together. So it kind of points towards a mechanics-like description of thermodynamics, things like associating the notion of a coordinate and a momenta, which are in a sense conjugate to each other. So the purpose of this talk will be to briefly explore these, the geometric mechanics framework of black hole thermodynamics. So let us begin by kind of recalling the notion of a symplectic manifold. So symplectic manifold is a smooth manifold of even dimensions on which you have a two form which is closed and non-degenerate. So if this is the case, then if you're given any smooth function, H, then you can always associate a vector field, XH, through this relation. You have a vector field XH, you contract it with, so this I is basically the contraction symbol. You contract it with this two form, it gives you one form, and that is the H. So this is, and because omega is like non-degenerate, so it is invertible, so this is an isomorphism. So there is a unique relationship between DH and XH. And XH is called the Hamiltonian vector field, and this is a volume preserving thing. So this is something in StatMech we know as Lewis theorem, and this turns out because if you take a Lie derivative of omega with respect to XH, it gives you 0. So that's the Cartan formula. The second term vanishes because omega is closed. The first term vanishes because the d square is anyway 0. So there's a famous Darboux theorem which asserts that all symplectic manifolds have the same kind of local structure, and you can associate a local coordinates to any open patch, Qi, Pi, in which omega always looks like this. So this is always, so irrespective of what is the topology, it doesn't matter, locally it looks like. And it's not difficult to verify that the XH Hamiltonian vector field kind of looks like this in the local coordinates. So that this condition is satisfied. And this actually gives us our familiar Hamilton's equations. And as a remark, the Poisson bracket is defined like this. For any two functions, f and g, it's just the contraction of the corresponding vector field with omega. So similarly, there is something called contact geometry. It's like an odd dimensional yet a little less symmetric counterpart of symplectic geometry. And a contact manifold is a pair where M is a smooth manifold, this time of odd dimensions, and eta is a one form which satisfies this condition. So this is like a volume form which is non-zero. But if you look from the Frobenius integrability sense, you'll find that this condition being non-zero means that the vector subbundle of the tangent bundle generated as kernel of eta is completely Frobenius non-integrable. So the hyperplane distribution is extremely twisted hyperplane. So there exists a globally defined vector field. So this is globally defined. It's called the Reeve vector field, which is defined through the following conditions. So the first one actually tells you that eta is in a sense it's dual to the one form, as in xi is in a sense dual to the one form eta. In case of contact manifolds, you have an exact vector bundle isomorphism similar to the symplectic case, for which if you are given any function h, smooth function, so then you can associate a vector field xh. And there's a similar Darboux theorem which asserts that eta will look like this in the local coordinates. S is one unpaired coordinate and Pi, Qi are like conjugate variables. And in these local variables, your Hamiltonian vector field looks like this. Your vector field xh looks like this, and it kind of looks like a Hamiltonian vector field. So we'll just end up calling it the contact Hamiltonian vector field. Okay. However, let's point out that there are two features which this contact Hamiltonian vector field has, the Hamiltonian vector field doesn't have. First of all, the contact Hamiltonian vector field is not volume preserved. If you take a divergence in the local coordinate, you find that this is in general non-zero. As long as H is independent of, as in H is dependent on S, which is the whole point. If you remove that unpaired coordinate, then you are actually not doing contact geometry at all. So the dependence on S is essential for things to be kind of non-trivial. And this vector field also doesn't conserve H, unlike the conservative Hamiltonian. So in conservative Hamiltonian mechanics, the Hamiltonian is conserved. But in this case, it's not conserved in general, unless H is 0. So of our interest, there will be a very special class of submanifolds, which are the submanifolds. These are like maximum isotropic submanifolds, which are submanifolds of maximum dimension such that the contact form eta is 0 when restricted on the surface of the submanifold. So more technically, you can think of if F is the inclusion map, then the pullback of F star eta is 0. It's just like a configuration space or a Lagrangian submanifold of a symplectic manifold, where you don't have conjugate pairs of variables. The fact that eta is 0 means that you cannot have conjugate coordinates. So now, if you recall the first law of thermodynamics, so first laws always have forms like this. Like you can have different work terms, but the first law of thermodynamics always looks like this. If you compare this one with the local expression that eta always, so Darboux theorem guarantees you this, that locally you can always write the contact form like this, irrespective of whatever might be global properties. Locally you can write it like this. So if you make this comparison, you can actually think of associating a contact structure with a thermodynamic phase space, where the local coordinate corresponds to the thermodynamic variable. So you can think of at least locally thermodynamic phase spaces as contact manifolds, and then you can actually do certain things like there are a generalized Poisson bracket called Jacobi brackets. You can define bracket kind of relations between thermodynamic coordinates. The interesting aspect is that at equilibrium, the first law should hold. So if it is 0, that means that eta is 0. And eta is 0, as we saw, is the definition of a maximum isotropic submanifold. That means equilibrium states, the states which satisfy the first law, they are all points on a Legendre submanifold. So even if the entire phase space, the ambient phase space is a contact manifold, but the equilibrium states don't have access to all the points, they lie on some kind of submanifold L. So we call it L. And contact Hamiltonian dynamics, it implies kind of evolution of variables. evaluation of thermodynamic variables because thermodynamic variables are now local coordinates. So therefore, Hamiltonian dynamics can actually describe thermodynamic transformation. However, H is not conserved, so an arbitrary XH is actually not tangent to the level surface H equals to 0 or levels as in a Legendre submanifold L. However, if L actually is a subset of the level surface H equals to 0, that is, if you choose carefully a contact Hamiltonian which vanishes on the Legendre submanifold, the space of equilibrium state, it may not be vanishing everywhere, but on that space of equilibrium states at least it vanishes, then the contact vector field, if at initial point we choose on that surface, on the L surface, it's actually going to stay on that surface throughout its evolution. So you can think of all the points lying on the integral curves of that vector field, provided one of the initial points is, as in one initial point is an equilibrium state, all the subsequent points are equilibrium state. So you can think of a Hamiltonian description of thermodynamic transformations of a system. So for example, I'll take a very simple example, is that of the BTC black hole whose mass is 4Ts²/pi, and thermodynamic volume is simply just del m del p. If you choose the following form of the contact Hamiltonian, a simple computation of the vector field in local coordinates reveals that T dot is 0. So this can point towards an isothermal transformation of the system. Now, since for the BTC black hole, you have this relation between B and S, if you substitute this relation into the expression for H, you get something like this. And this is 0 on the space of equilibrium state of the system because of what's called the Smart relation. So it's like an Euler relation for black holes. It's the three-dimensional Smart relation where, so it's like, although the Hamiltonian is non-zero off shell, it's going to be 0 on shell, something like that. So that means the flow, provided an initial point you choose, which is an equilibrium state of the black hole, all the subsequent points are equilibrium state, and it's an isothermal transformation. And it's actually simple to check that the P and V evolution equations, the Hamilton's equations for P and V, they satisfy all the thermodynamic quantities. So similarly, you can choose this kind of choice, which can generate isobaric transformations. You can, if you're smart enough, you can choose anything for any system you take, you can find a Hamiltonian.
Sorry, Aritra, you have 3 + 3 minutes.
Okay, so 10 minutes is over, right?
Yeah.
Okay, thank you. Thank you. So, okay. So another aspect is that if H is not vanishing on L, so the previous case was that when H would, the chosen Hamiltonian would vanish on the Legendre submanifold. If it doesn't vanish on L, then the resulting flow need not be tangent to L. So even if you take an initial point, which is an equilibrium state, your integral curves may not actually stay on that submanifold. So the subsequent points may not be equilibrium states of the initial system that you started out with. However, such a transformation, such a Hamiltonian flow can be taken to generate a family of related thermodynamic systems. For example, for a Schwarzschild radius, if you choose this kind of Hamiltonian, this is something works with a little bit of guesswork and a little bit of constant later. So it turns out that T under the vector field T and V, they do not evolve, whereas P evolves in the following form. Here, the first two terms on the right-hand side correspond to the equation of state of the Schwarzschild radius black hole. Whereas the third term, this is the term which depends on tau. Tau is like an affine parameter. You may not think of that as time, some parameter which parameterizes the Hamiltonian flow. So when tau is 0, you're on the initial point, you're on an equilibrium state of a Schwarzschild black hole. Now, as you increase your tau, you happen to get equations of state of charged black holes with charge values q² tau. So you can generate an infinite number of charged black holes via a Hamiltonian transformation. So this is one different aspect. So okay, so I'll put a remark or two about thermodynamic metrics. So this is called the Ruppiner metric, which is defined as the negative Hessian of the entropy. And this actually agrees with the Fisher information matrix, which is defined in terms of the density matrix of a system. That is much more general, of course, where thermodynamic limit may not exist. This is defined in the thermodynamic limit. Now, this is very intuitive, which can be seen by writing. You can take your Boltzmann entropy omega, and you can write omega as exponential s. You can invert the formula. And if you expand entropy about the equilibrium to the second order, then you can argue that the probability of finding the system between Zi and Zi plus Dzi is actually proportional to exponential of that length, negative length. So it's like more the distance between two states, the less probable is the fluctuation between them. So that's why this Ruppiner metric is kind of intuitive, and it has been empirically demonstrated that the curvature scalar of the Ruppiner metric, the Ricci scalar, possibly carries some useful information about coarse-grained microscopic interactions. So these are still in some speculation stages. So the final thing which I would like to point out is that such metric structures, Hessian metric structures, can actually arise from the contact structure of the phase space, thermodynamic phase space. For example, Sasaki, he actually introduced the concept of a contact metric manifold. So these things actually carry his name. They're called Sasakian manifolds. So where you have a metric which is compatible with the contact form, and so that there is a compatibility condition to be satisfied. So it turned out that if you project this kind of metric, if you choose your thermodynamic potential slightly carefully, if you project this metric on the Legendre submanifold on a space of equilibrium states, you get the Hessian structure back. So that is a wonderful thing, that the geometrical features of the thermodynamic phase space actually incorporates everything. And Hessian geometry seem to offer insights into the phase structure and microscopic interactions. So you can think of that as a macroscopic probe for black holes, in which you're not able to directly compute microscopic things possibly. So as a simple illustration, I'll just show a comparison of the thermodynamic curvature, the Ricci scalars, these are the Ricci scalars, versus the fugacity of an ideal Bose gas and the large black hole branch of a short-shelled black hole in ADS 510-5. So there was a proposal a few years back. Dolan made this proposal that if you take a dynamical cosmological constant, on the boundary side, it would mean that you're varying the number of colors, you're varying the number of degrees of freedom in the larger limit. So then a Schwarzschild black hole in ADS 510-5, in the fugacity goes to one limit, which is the Bose condensation limit, appears to have a similar condensation effect. So we wanted to just check whether, because of certain claims that the thermodynamic curvature could capture microscopic interactions, we wanted to check if the curvature scalar shows some similar behavior, and we actually indeed find something very nice. It looks like this. Okay, so okay, so I'll just end with some existing challenges. So first of all, the first thing is that some kinematic properties, like for example, we did some Hamiltonian flows, but the fact that because these flows are not volume preserving, you can have focusing effects, you can have sources and sinks. So certain properties such as existence of sources and sinks, their significance, and things like shear and rotation characteristics, the ones that you look for when you're writing right-order equations and all for geodesic flows. So things like that have, I think, is worth investigating. And thermodynamic Hessian metrics, although they're nice, they're related to fluctuations, they have a serious drawback of not being invariant under Legendre transformation. So they are sensitive to the ensemble that you choose. It depends on what is the free energy that you choose. So a thorough comparison and classification in that regard is something which is yet of a challenge, because a lot of things are empirical. You don't have exact results for most of the time. So, okay. So all the thermodynamic Hessian metrics define distance between states, equilibrium states. But we saw that things like a Schwarzschild black hole can be mapped into a charged black hole via Hamiltonian flow. So kind of things like distance between states, distance between different thermodynamic systems related by Hamiltonian flows, things like that are still open. So I think I'll stop here. Maybe I'll take questions. So thank you.
Okay, thank you, Aritra. We are running out of time, but if there are any one or two quick questions, then we can take. Okay. Okay, if there are, maybe if there are questions, we can take it in the discussion session. Okay, thanks, Aritra. Thank you very much for the nice talk. You can now stop sharing.
I'll unshare my screen.
Yeah. So we now have Debangshu Mukherjee. She will talk on from 2D droplets to 2D Young-Mills. So Debanshu, I will remind you after 9 minutes. Is that okay?
Am I yes? Am I audible, Prasanta?
Yes, you are audible. It's visible clearly.
Okay.
Full screen. Yeah, please start.
So let me start by first thanking the organizers for giving me this opportunity to present my work here. And I would also, in fact, try to applaud Alok and his entire team for bringing together this in such difficult times. So I'll be talking about my recent work, the droplets to the angles, which was done with a couple of colleagues, Orko and Nico, and my mentor, Professor Shouvik Datta at IIT. So, sorry. Okay. So the interplay between unitary matrix quantum mechanics and 2D Yang-Mills is well known and quite old. And this is how the partition function of 2D Yang-Mills theory look like with the underlying gauge group SUN on a generic Riemann surface with genus G. And as you can see, it's written as a sum over representations, and every representation. So I will actually talk about two very popular examples of connecting these unitary matrix quantum mechanics and 2D Yang-Mills. So in this sum, every representation can be mapped to a state of energy C2R, where C2R is the quadratic Casimir associated with the representation. So what Minahan and Polychronakos did in '93 was they mapped these states to string states, 2D string states, which wind around one compactified spatial direction. And they wrote down a Hamiltonian for these string states, which turned out to be exactly same as the Gauss-Javicky Hamiltonian, which I will talk about at some time, which comes up in the study of unitary matrix quantum mechanics. Another very popular example is the work of Gross and Matitsin in '95, where they started with the partition, the same 2D Yang-Mills partition function, and in the large n limit, they looked at the equations of motion, which they interpreted then as a Hamilton-Jacobi equation. And once they wrote down the classical Hamiltonian, that also turned out to be the same as the So we are trying to explore this connection further, and we will take, however, a bottom-up approach. So starting from unitary matrix, so my main goal is over the next few minutes to show to you that starting with this unitary matrix quantum mechanics, I'm going to quantize the system, and I can construct transition amplitude and higher point amplitudes for a variety of 2D angles. So this variety is important. And in fact, it seems to us that the Hilbert space of this quantized unitary matrix quantum mechanics seem to contain a large volume of information about the partition function and all higher point amplitudes of Yang-Mills theories of 2D angles. As a matter of fact, even amplitudes of Q-deformed Yang-Mills theories can be constructed using our proposals. Okay, so the starting point is obviously the 0 plus 1D unitary matrix quantum mechanics that you see here. This is the partition function, and this system can be mapped to a collective field theory of real bosonic fields, the field being rho, which is the eigenvalue distribution of the matrix U, and pi being the corresponding conjugate momentum. So, of course, the equation of motion that follows from this Hamiltonian, it's non-linear, it's coupled, and of course, to handle. But what one can do is you can define this nice this nice variables p plus and p minus as here in this equation. And what this does is it decouples your equation. I mean, just non-linear, but it at least becomes a bit more practical. Now, there is an alternate view of looking at this p plus p minus. So what you can define is, you can define, I'm not sure if one can see, so this y-axis is what I'm calling the p coordinate, the x-axis is the theta coordinate. And you can define a sort of density here, which I'm calling var phi, which is essentially a theta function. Which so in this adjoining diagram, if you see, we have a area in this p theta plane where this upper and lower surface are essentially characterized by these two curves, p plus and p minus. And the integral of over dp gives you the density, and times this gives so these are precisely the droplets that I'm going to talk about. And so this is basically the classical picture. And in terms of so various large n phases of these unitary matrix quantum mechanics, in essence, can be characterized by the shape of these droplets. So how they look like. And naturally, the evolution of these droplets also tells us about the evolution of the.
We have lost him probably.
Sorry. Hello.
Debangshu.
Yes.
I think because you're moving back and forth, so your voice is actually breaking.
Oh.
So.
Is this better?
Okay. Yeah. That's okay. Now it's okay.
Okay. So eventually, the Hamiltonian, in terms of these p plus and p minus variables, take this form that you see here. And because of the original theory having a U going to U dagger symmetry, the area of this droplet is constant. So a natural thing to do would be to quantize the system. And in order to quantize this system, we first start by regularizing the total number of states in the phase space like this, as that I'm dividing the phase space into unit volume, with each volume being h. And this is classical limit is a double scaling limit between n and h such that the product is equal to 1. So if you want to reproduce the correct equations of motion, you have to impose. And this is how I describe my fluctuations in terms of these functions p tilde. And once we quantize the system, this is how the commutator of p tilde plus minus looks. Decomposing this into Fourier modes in the theta direction, what we see is that the modes A and B corresponding to this P plus and P minus follow abelian Cash-Moody algebra, and the full Hamiltonian actually breaks down into nicely two chiral sectors, H plus and H minus. So this plus and minus basically corresponds to, so this plus and minus corresponds to fluctuations in the upper Fermi surface and the minus to the lower Fermi surface. So you also have a H minus which will be essentially this A replaced with B. And as you can see, the Hamiltonian divides into three parts, one part being a constant. This part is V theory, which looks like harmonic oscillator, and you have an interacting cubic piece. So in order to construct the Hilbert space, we first define a vacuum like this. And a generic excitation above the ground state is essentially a bunch of A daggers and B daggers hitting the vacuum. And of course, even the full Hilbert space also decomposes nicely. Now, the catch here is that this K state that we have just defined, they are not eigenstate, they are only eigenstate of the free part of the Hamiltonian. So it's eigenstate of only this part, not of this. And the expectation value of P plus in this K state goes like this, where again, this is the classical value, and you have this H contribution coming. And so physically speaking, this K states characterize ripples over these spaces. Also, by the way, I should point out, so from now on, we will only focus on one sector, only the H plus sector, because as you can see, the Hilbert space decomposes nicely. So all the arguments go through for the negative sector. Now, the things that we will be mostly interested, the thing that will mostly interest us is these coherent states. So these coherent states, this is how we define it. And the expectation value of the P plus operator in this coherent state looks like this. Now, this third term is the one that should grab your attention, because what you see here is that these are essentially characterized odd-one deformations of the classical solution. And in fact, if you calculate the quantum dispersion, you see that it vanishes identically. And this is precisely the reason why we dub such states as classical. Okay. Now, we saw that K was not eigenstate of the full Hamiltonian. So what one can do is associate a young tableau with these states K. So K is essentially a bunch of these numbers, K1, K2, K3, and what one can do is one can associate a young tableau thinking like K1 to be the size of number of one cycles, K2 to be number of two cycles, and so on, and define a state in the young diagram basis, which I'm calling R plus. In the large n limit, if you calculate the eigenvalue, it turns out to be exactly equal to the quadratic acid, which we also saw in the first slide. The same. And this entire Hilbert space structure seems to be very similar to the chiral sector of a U-entropy atlas. Now, the most important thing is this translating between these two bases, this coherent state and this basis which is written in terms of this R plus states. But these coefficients are nothing but the Shouvik polynomials, arguments being this tau plus. Tau plus is this data that you give into the coherent state. Now we have the full machinery ready, and in order to write down the transition amplitudes, hello? Hello?
Yeah, we can hear you. It's fine.
Okay.
Yeah, go ahead.
Actually, yeah, I got a message here that the internet is not okay. We have the full machinery, and so the first thing is to write down a transition between two coherent states, tau A plus and tau B minus, which is over a time interval. So what you see is exactly using this equation. What one can do is we can write down this amplitude, and it turns out to be exactly same as the cylinder partition function for 2D angles. So the transition amplitude between these two coherent states is identical to the chiral partition function, where the holonomies are identified with this data given in tau A plus and tau B minus. Okay, so now going on, one can choose a very special point in this tau plane where all this these numbers tau that we give into the coherent state in trying to define the coherent state, they can all be one. And for such a case, the Shouvik polynomial actually simplifies simply to the dimension of the representation. So more geometrically speaking, that would mean to choose trivial holonomy on one of these circles. So you can think of closing one of these circles, and what you end up with is a test, which is precisely what you have. you reproduce the geometry for the angles theory. And if you do the same for both the sides, you eventually end up with a sphere, which is what you have here. You can.
Debangshu, you spent 10 minutes already.
Okay. Oh yeah. So this is the very similar thing which you saw in the first slide, where so for the sphere G is 0, so you simply get quadratic. So now, in order to define generic higher point function, we first define this droplet operator and this density matrix, where this is how we define the probability, which is precisely where the data of the genus goes in. And as we can see that the partition function exactly matches with what I started off with 2D angles, and this is how one can also construct generic endpoint group. So this corresponds to basically putting n many holonomies on a Riemann surface of K. Now, the thing is that I also promised something about this Q-deformed angles, which is that so the thing about this Q-deformed angles is that the gauge group itself is Q-deformed. And this is captured by this non-commutativity in the entries of the group element, which is parameterized by this Q. What we do is, however, a bit different. We choose a very special kind of coherent state, and which finally eventually ends up in giving us all the correct disk sphere as well as cylinder amplitude for the Q-deformed. So now throughout you must have noticed that I had been working on only one of the sectors, the plus sectors. In order to get the, because you know the partition function will also get contribution from the propagator coming from the minus sector, we need to join them and glue them up, and this is done by what is known as the composite representation, and this is a diagrammatic way of representing it. R minus this young capital being the one associated with R minus representation. You sort of create anti boxes here. You then delete this part, finish off this Young diagram, and then you associate this with the Young diagram for the full composite representation R plus R minus. And once the full Hamiltonian acts on this composite state, you do indeed get the quadratic Casimir to be the energy coming from both the sectors to be the full energy of the full system, and even the transition amplitude for the full state is also used. So eventually, so the main upshot of this work is that we have given a geometric prescription and constructed partition function for 2D angles on very generic Riemann surfaces, and it seems to be the case that this quantized Hilbert space on this droplet side contains much more information than we actually expected. It contains information on very generic 2D angle surface and also its Q-deformed analog. The system nicely decomposed into two parallel sectors, and we joined them later. And then we eventually defined very special coherent states in order to map the partition function of 2D angles to our unitary matrix quantum mechanics. Now, one thing that we did not explore much is the formation of folds. So we worked with P plus profiles with these upper and lower Fermi surface, which were very nice, single value. And they have been studied earlier. Our next goal is to exactly look at what happens to what do we get on the quantum mechanics, the 2D, what we get for the 2D angle side if we allow for formation of folds or shocks. And also what exactly are the gravity duals of this fold states or shocks. I think I'm out of time, and so let me just leave you with this pathway of our construction. So that's all I have to say. Thank you. I'll like to take a question.
Thank you, Debangshu. We have a question from Somadatta.
Yes.
So Somadatta, please go ahead.
Yeah, so could you go back to your slide where you had the theta function of the P plus P minus?
This one? This one?
Yeah, this one.
Yes.
No, the next one.
This one?
Yeah, this one. So should it be theta of P plus minus?
Sorry?
So this theta function,
yeah,
is it a product of P plus and?
This is the P theta plane. All that I'm saying is that when P value is less than P plus, so within this region, it is going to have support 1. That's all I'm saying. Outside, it's identically 0. This theta function is heaviside theta. I mean,
heaviside theta,
yeah, normal theta. Yeah, theta of x is 1 when x is greater than 0 and 0 otherwise.
Okay. Alok.
Yeah, hi Debangshu. Hi.
Hey, hi.
So, so for any for any n, Witten had this quantization of 2D Young-Mills, right? Using equivalent localization. No, I was just wondering if the partition function he computed, is there a nice way to compare with his droplet picture or?
Okay, thank you for the question. So the thing is that if you notice, this entire droplet picture comes out from a collective field theory, which is inherently a large n business.
Right, but you could do Witten's thing also for large. I mean, maybe if I understand correctly, it was for any n, right? I mean,
yes, exactly.
So
it was for
should a comparison be possible? I mean, okay, maybe I can ask just a small follow-up that, I think there were these non-perturbative contributions coming from what he identified as unstable solutions of the 2D Young-Mills equation in this. So is there a way in large n at least to identify those solutions in the droplet picture? Or I mean, I don't know if that's the right question.
Okay, this is very speculative, but probably these fold states are these non-perturbative solutions, but we have not, unfortunately, explored. But but this is very speculative, so don't take my word for it. But presumably these fold states. So if this thing evolves, so we have always worked with P plus to be single value, right? So you can have this profile to be going. Is my cursor visible?
Yes, it's visible.
So it can have something like this. So you can presumably that is what will correspond to those class of states.
Oh,
but
thank you.
Again, this is speculation.
Okay. I will talk to you later.
Yeah.
Okay, Ronak.
Hi, Debangshu.
Nice
talk.
Hi.
I actually have two questions.
Yeah.
First is what the Q in the Yang-Mills side, what is it on the matrix side?
So Q, this?
Yeah, the Q, what does it come from in the matrix side?
On the matrix model side, it's basically the Q deformation. It's a deformation of the gauge group. So it has an inherent parameter in it. So
I see. So
so for example, you can consider SU2 for example. So you will have a bunch of it will have entries alpha, beta, gamma, delta. So what you will have is alpha delta will be equal to some Q times beta, Q times delta alpha. And correspondingly so that's what is on the matrix models.
I see. Thank you. Also, I wanted to just kind of make a comment which is very interesting. This coherent state that you just wrote down.
Yeah.
The same coherent state the coherent state on the slide that was open. Just
sorry. Which?
With the gamma power n minus gamma power minus n that one.
Okay.
The slide that was open, like when you were answering my previous question.
Okay. Yes.
Okay. Yeah. That equation 23. Yes. So this coherent state actually turned up in a. I just checked, and this exact same coherent state turned up in a very different context, which is in studying entanglement in topological string field theory. There was this paper last year by Gabriel Wong, Will Donnelly, and others, and the capital N going. Yeah.
I am aware of that work, actually. Yes, I am aware of that work also. But the fact that this turns up in topological string theory should not be surprising. The fact that somehow entanglement is also involved here. I'm aware of it, but I have unfortunately not explored.
Yeah. Okay. Thanks. I was wondering whether you had any thoughts on this.
Yeah. I know. I don't have immediately any thought, but yeah, I'm aware of it.
Yes.
Okay. Thanks.
Okay, Debangshu, thank you very much for the nice talk. Please stop sharing your screen now. We now have Naveen Prabhakar from the IFR. Naveen is going to talk on a Hilbert space for the Chern-Simons matter theory. So Naveen, are you around?
Yes, Prasanta.
Good, it looks
Can you
good.
hear me?
Yeah, I can hear.
Can you also see my pointer?
Yes, it's perfect.
Okay.
So I will remind you after 9 minutes. Is that okay?
Sure. Yeah.
Yeah. Please go ahead.
Yeah. Just one small correction. I am now a postdoc at ICTS.
Okay.
But part of this work was done when I was at TII, so I guess you're not completely wrong. Okay. Anyway, thank you, Prasanta. I would like to first thank the organizers for giving me this opportunity to speak here in this conference. It's good to be back among the community. So let me start. So I'll be speaking on a Hilbert space for
listen to this talk. So,
Chern-Simons matter theories, and it'll be a short summary of what Shiraz spoke yesterday. So it will be, let me make it full screen. Okay. Yeah. So it'll be based on these two papers, one which came out last year with Shiraz, Minwala, and Amiya Mishra, and one which is due this month, which is called the Hilbert space of large and Chern-Simons matter theories, with Shiraz, Minwala, Amiya Mishra, and Tarun Sharma. So very briefly, the kind of theories we will be interested in 3 dimensions is these parity violating gauge theories called Chern-Simons theories, which are based on a gauge group and coupled to matter in the fundamental representation. So that's going to be the purview of my talk. So there's one thing to remember here, which is that this gauge coupling constant is forced to be an integer because of large gauge transformations, invariance at a large gauge transformations. And yeah, we also consider non-semi-simple gauge groups like UN, where the U1 and the SU part can have different levels. So I have chosen the gauge groups here appropriately to illustrate what is called Bose-Fermi duality, which I'll be coming to in a second. So why are Chern-Simons matter theories interesting? So these are exactly solvable in the 't Hooft large limit when the matter is in vector-like representations, like the one here in the fundamental representation. We could have many flavors as long as the number of flavors does not come close to the number of colors here. So that will define a vector-like representation. And these Chern-Simons matter theories turn out to be holographic duals of many gravitational theories on ADS4. There is a rich literature behind this. And because of the underlying topological field theory, which is Chern-Simons theory, one would expect anionic excitations. And these theories typically exhibit anionic statistics, which will be one of the main points of this talk. And these theories also exhibit what is called Bose-Fermi duality, which is a duality which does not demand the existence of supersymmetry to be established. So for example, Chern-Simons theory coupled to bosons is dual to Chern-Simons theory coupled to fermions. And there is also a change in the rank and the level of the gauge groups I have chosen here. So the rank and the level have to be flipped at the same time as the statistics of the matter particles here. And there's a small technical point, which is that an SUN gauge group is related to a UN type of gauge group on the other side. So very quickly, let me talk about the observable that I'll be interested in. I'll be looking at the partition function on S2 times S1. And we start by working in the large spatial volume regime. That's the volume of the S2 being large compared to other length scales in the theory. And the lightest mode in this theory, which is well known, the study of Young-Mills or any gauge theory on S2 SD times S1, will be the gauge field holonomy around along S1, and the mode which is constant along the spatial manifold, which is S2 here. And using gauge invariance, we can always diagonalize this lightest mode to an n by n diagonal matrix. And this will be the field which we will express our expressions in terms of. Okay, so the next step is to integrate out all the matter fields and the non-holonomy fluctuations of the Chern-Simons gauge field to give an effective action for this holonomy U. And in the larger limit, one can see that this effective action scales as n, and hence we can compute this partition function z by saddle point approximation. So the saddle point approximation takes this form. So there is there is this observable U, which is, or rather the field U, which is this holonomy mode. And in the process of computing the saddle point, it turns out that it's convenient to introduce auxiliary C number variables in the large n limit, which I parameterize as phi aux. So the integrand, which we have to extremize, takes this extremely simple form, which is exponential of an interaction part, which I'll explain in terms of this example in a minute, which depends only on these auxiliary variables, times the usual Fock space trace of the matter particle that's coupled to the gauge field. But the trace is twisted by this holonomy element, which I denote as U hat, the operator which acts on states of this Fock space. For example, when we have Chern-Simons coupled fermions, the interaction effective action is given by this, which is just a function of these auxiliary variables, which I call as C tilde and curly C. And here MF is the mass parameter, the Lagrangian. And when we integrate out or extremize over the auxiliary variable C tilde F, that the on-shell value, that is the extremum value of that, turns out to be the thermal mass of this fermion. And this other auxiliary variable, we don't have a good enough physical interpretation as of now. And the final part, which is this trace over the Fock space, when we exponentiate it as a log of something, that becomes this. This also must be familiar. The only new element here is that this U twist appears as this n by n matrix U inside this log. And for bosons, we would have a 1 minus here. And there are other additional terms which depend on the chemical potential for bosons, which I will not have time to go into, but they're present. So this energy here, because we are in the large volume regime on S2, we can approximate that in the larger limit by a theory on R2. And the spectrum is just the spectrum on flat space, and that's given by square root of C tilde square plus K square. K is the spatial momentum. And on the extremum, C tilde just becomes the thermal mass of the fermion, and this will be the energy level with spatial momentum K. So once we have this split in terms of S interaction and this trace over the Fock space, we see that the dependence on the chemical potential appears only through this Fock space quantity. So obtaining the occupation number is very simple. We just differentiate with respect to mu. And the answer would be something like this. It's extremely simple. This trace is just the trace over n by n matrices. And this U is the extremum value of the holonomy mode. And for bosonic occupation numbers, like I said, there is a minus sign here, and we have this. So in the larger limit, the trace is replaced by an integral over the eigenvalue density function. And now the eigenvalues will be concentrated on arcs on the unit circle. And one should be careful as to how one does this contour integral in these cases, because sometimes there may be poles which may arise, for example, when this argument is less than 0, which happens when the energy is below the chemical potential, which in turn happens when this thermal mass is below the chemical potential. So one should be careful in such finite density cases. And one thing we can notice now is that because of the appearance of this holonomy mode here, the usual Bose-Einstein statistics or Fermi-Dirac statistics are modified in terms of these Chern-Simons couplings. And these gives rise to what we call as anionic statistics. So it lies somewhere between bosons, the occupation statistics for bosons and fermions. To illustrate this, for the sake of time, we look at this extremely simple limit, which is the large volume zero temperature limit of the above formulas. And in this case, the extremum U can be shown to assume this universal form, this n by n matrix with these diagonal elements. And plugging this back into this trace, we see these extremely simple numbers for these occupation numbers of the bosons for various states and for fermions. And for fermions, let's look at the fermions first because it's easier to relate to. For energies less than the chemical potential, we expect the state to be fully filled at zero temperature, subject to the Pauli exclusion principle, which says that there are n fermions, the number of colors here. And for energies above the chemical potential, we at zero temperature, we don't expect the states to be filled at all. And that gives the correct number 0 here. And this is some, in the regularization that we adopt, we get this intermediate value of half NF for energies right at the chemical potential. Now, what is surprising now is that after coupling these bosons to Chern-Simons gauge fields, the singularity in the Bose condensate, which arises basically because for energies below the chemical potential, the states have to be filled, but we can add any number of bosons in a particular energy state. That is regulated to this number KB, which is just the Chern-Simons level of the Chern-Simons gauge field coupled to the bosons. And similar to the fermions, the energy levels above the chemical potential are not filled. So we see a Fermi surface kind of behavior in these bosons coupled to Chern-Simons gauge fields as well. So this is in line with the Bose-Fermi duality, because in the infrared, we expect a theory of bosons coupled to Chern-Simons gauge fields to be dual to another theory coupled to the theory of fermions coupled to Chern-Simons, and that theory exhibits a Fermi surface. So this kind of Fermi surface behavior is important. And under level rank duality, the level and the rank are interchanged between the bosonic and fermionic theories. So these two formulas are bang on. for that. So
sorry,
in particular,
Naveen, this is just to remind that you already spent 9 minutes.
9 minutes, okay.
Yeah.
Thank you, Prashant. So this hints at an exclusion principle for bosons, and let's flesh it out. So first of all, we took a lot of limits in coming to this conclusion, the large volume, zero temperature, large N limit. But if it's an exclusion principle, we expect it to be more fundamental. And it turns out that if we study the partition function at large N more carefully, we can uncover this more fundamental aspect of the exclusion principle. So suppose we focus on the U-dependent part, this Fock space trace. We can expand using usual Fock space manipulations to write it as this. So there is a piece for the particles and a piece for the antiparticles, and this chi is just the character for the symmetric N box representation, where N is the number of bosons in a particular energy state EA, evaluated on this matrix U. And we are integrating over all matrices. So in the large N limit, we have to extremize this, but I'm just retaining the integral because we'll make contact with something deeper in a minute. Some more manipulation just gives this following formula, where we have pushed this integral over U and isolated the parts which are dependent just on U. And now, if we look at this, this is just an observable in the pure Chern-Simons theory with an infinite number of Wilson line insertions, which is what I've written here. So there's this usual Chern-Simons action with the Wilson lines corresponding to the particles and the antiparticles. And the finite N version of this is well known. It's just the Veblen formula for the number of singlets in the fusion of the representations SNA for all A and SMA for all A in the dual chiral-Weissenberg model. And this is the same as the dimension of space of chiral conformal blocks with these representations. And long ago, Gettner and Witten showed that conformal blocks in WCW models with some integrable representations and one or more non-integrable representations vanish due to a null vector in the module corresponding to the integrable representations. Incidentally, the condition for integrability for a representation of SU and K turns out to be that the number of boxes in the symmetric representation should be less than or equal to K. So this says that the dimension of conformal blocks corresponding to representations which have more than K boxes will be 0. And in particular, that tells us that this integral is 0 if one of these insertions has more than K boxes. So this allows us to restrict the sum, which was from 0 to infinity earlier, to just this level KB. And this implies the bosonic exclusion principle. And since this Chern-Simons chiral-Weissenberg duality is rigorously established, this is also a very fundamental fact that's present in the Chern-Simons theory coupled to bosons. So in the last 1 minute remaining, let me focus a little bit on some technical aspects of this Chern-Simons chiral-Weissenberg duality. So suppose we consider this observable in pure Chern-Simons theory based on the SU gauge group at level K, which has these n Wilson lines inserted with representations R1 up to Rn. So this is basically the dimension of the Hilbert space of states in the pure Chern-Simons theory with sources in these representations. One can evaluate this path integral using standard path integral techniques, which Blau and Thompson did about 20 years back. One could also do this in a slightly roundabout fashion by embedding this back in a n equal to 2 Chern-Simons theory on S2 times S1, and again lift these ordinary Wilson lines to supersymmetric Wilson line insertions and compute the superconformal index. And because the fermions in this theory are quadratic and we can integrate them out, this will just reduce to an observable in the pure non-supersymmetric Chern-Simons theory. This is another independent way of obtaining the same quantity. There is a third way which appeals to this Chern-Simons-Weissenberg correspondence. So before that, let me just briefly describe Blau and Thompson's result. So this turns out that once you do this path integral carefully, this integral over gauge fields reduces to a finite sum over some eigenvalue configurations, that is the holonomy mode, some discrete set of holonomy modes. And so here, this is the usual van der Monde determinant that we encounter in gauge theories. And the Wilson lines just reduce to characters evaluated on the matrix U, like we discussed earlier. But the matrices U correspond to special eigenvalue configurations, which satisfies these equations here. So the first condition just says that it's an SUN matrix. And this van der Monde factor here does not allow coincident eigenvalues. But thirdly, the third condition is the new one, which is from the Chern-Simons Lagrangian, which is that ratios of these eigenvalues have to be kappa threads of unity. That's another way to say this express this condition. So there is another, like I was saying, there is another way to obtain the same dimension of Hilbert space through this correspondence, which is due to Verlinde. So that expresses this as a sum over integrable representations of this affine Lie algebra, SUNK hat, of this particular product of product and ratios of S matrix, Verlinde S matrices. And this formula holds only when R1 and Rn are integrable representations of this affine Lie algebra. Now, the two descriptions, that is one from the Chern-Simons path integral and the one from the Benjamin-Witten model, are related because of a magic formula that relates the S matrix, the Verlinde S matrix, to classical characters. And that's basically this. So this is one of the factors in this expression here. So suppose I have something like this, that is equal to the character of the representation R prime, the ordinary representation R prime of the ordinary SUN Lie algebra, evaluated on this particular matrix U, where this eigenvalue configuration is described as follows. So it's related to this representation R, that is on the left-hand side. So suppose the row lengths of the Young diagram of this representation R are given by Li, with, of course, the last row being 0 because it's an SUN representation. And suppose this Ni is the sum of Li plus capital N minus I. Then these eigenvalues are given by this particular formula. So it's very easy to see that these eigenvalues satisfy these constraints that I wrote down. So they are, in particular, they appear in the set of configurations that we sum over. We show that the converse is also true. That is, any solution to these equations here can be expressed as W of R, where R corresponds to an integrable representation of SUN hat Q. And further, the explicit formula for the S matrix for SUNK hat gives rise to this equality here, which appears here. So that basically reduces to the van der Waals determinant in the three-dimensional path integral. So this finally establishes the equivalence of the two-dimensional Verlinde formula with the three-dimensional Chern-Simons path integral. And similar relations can be established between UN K, K prime WCW theories and the corresponding Chern-Simons theories. So this is one part of the paper that's going to come up soon. So finally, I would just like to highlight some observations. So here in this short summary, I outlined this relation between eigenvalue configurations in the three-dimensional path integral and integrable representations of the affine Kac-Moody algebra. So this kind of is in line with this abstract harmonic analysis, which one can do for classical groups, where conjugacy classes in G, which are typically parameterized by diagonal matrices with non-coincident elements, are in one-to-one correspondence between with the irreducible representations of the classical group. Here we have something that's similar to the story for the finite group, which is we have a finite set of irreducible representations, which are the integrable representations of the affine Kac-Moody algebra, and some distinguished conjugacy classes given by these matrices here, which satisfy these equations for the case of SUN. So what is the object that this corresponds to in the case of the classical group? Yeah,
please try.
This is my last slide. So let me just summarize. Yes, thanks, Prashant. So the other question is that, so what is this object? That's one thing that we are planning to explore next. And the other point is about non-integrable representations. The Verlinde formula gives the correct answer only for integrable representations, but the Chern-Simons path integral naively does not seem to care because we can take any representation we want along the Wilson line. But what it turns out that when we look at the characters evaluated on the special eigenvalue configurations, the character of a non-integrable representation evaluated on any of these eigenvalue configurations can be related to that of an integrable representation up to a sign. So there are identities among Wilson lines in the Chern-Simons theory, which basically tell us that the independent Wilson lines in the space of Wilson lines correspond to those of integrable representations. But it would be nice to see actually the fact by Gepner and Witten, which says that the conformal block with at least one non-integrable insertion is 0 in the Chern-Simons path integral. So I'll conclude here. Thank you.
Okay, thanks, Naveen. So we have one quick question from Somadat.
Yeah, so because of the presence of the U in the partition function, the statistics has become the anion statistics instead of bosons and fermions, right?
Yeah.
So
Yes.
why do you continue to speak in terms of bosons and fermions then?
Well, in the ultraviolet, the fields that we use are still bosons and fermions. It's just that in the infrared, the effective description is in terms of anions. We do not have a fundamental field theory description of these anions. And we can always,
even in the ultraviolet.
Okay, Samrat, can I go to the next question? Maybe you can ask in the discussion session.
Sure.
Quickly.
Hi, Naveen. Thanks for the talk. So at some point, we also calculated this starting from Wisdom-Witten side. And there we have this integrable representation, all these things boils down there. But probably I missed in your talk. So are you guys, what is the manifold that you are considering on your Chern-Simons theory?
S2 times S1.
S2 times. So do you have any comment on S3? Because we have some calculations where with this integrable representations were giving us some phases, some non-trivial phases because of this integrability, exactly of this integrability condition, because Chern-Simons part does not care about non-integrable representations, you see.
I see, so I don't have any intelligent comments except to say that perhaps one can use our answers on S2 times S1 and then do surgery to get some answers on S3. But I mean, I'm not sure how hard or easy that would be.
Right. I mean, for S3, would be interesting.
Sorry, Aritra, maybe
Sure. Thanks.
Can I continue in the discussion session? Yeah. Okay.
Sure,
as we're running out of time. Okay. Yeah. Naveen, thanks a lot for the nice talk. Please stop sharing.
Yeah.
So now we have Himanshu Parihar as the last speaker in this session. He will talk on phase curves for entanglement negativity through geometric evaporation. So Himanshu, please, please start.
Okay. So
I will remind you after 9 minutes.
Okay, yeah. So thank you, sir. First, I would like to thank the organizer for giving me the opportunity for this talk. And the title of my talk is Phase Curve for Entanglement Negativity through Geometric Evaporation. And this work has been done in collaboration with Jaideep, Debarshi, Vinay, and Gautam Singh Gupta. So, so here is the brief overview of my talk. First, I will briefly review about the partial dimension reduction and then how to obtain JT black hole from a BTG black hole. Then I will talk about our computation of entanglement negativity for a single and adjacent interval. Lastly, I will discuss about the phase curve for entanglement negativity followed by a summary. So firstly, the partial dimension reduction. So consider the 3-dimension action, which is given by this expression, and we choose this lambda to be a negative cosmological constant. Then we consider the solution to the above action where the metric does not depend on one coordinate, that is phi coordinate, and we can be expressed in the following form, where the indices mu nu runs from 0 to 2 and AB from 0 to 1, and this phi, small phi is some function of XA, and this curly phi is the angular coordinate. So now using the above answer in the 3-dimensional action, we get the following form of this action, where alpha ranges from 0 to 1 and denotes the parameter which controls the extent of partial dimension reduction. So we see that the form of this action is similar to the dynamical part of the action of the JT gravity. If we identify L3 with L and G3 with LG2, and in this where the G2 is the 2-dimensional Newton constant and G3 is the 3-dimensional Newton constant. So in this JT action, this first part is the topological part and second part is the dynamical part, and this capital phi is the dilaton field, and the dilaton field can be expressed in terms of the angular component of the metric of this answer, and it is given by this expression. Here phi r is the renormalized value of the dilaton and is given by the 2 pi L alpha, and it specifies the boundary condition of the dilaton field. So now we use this procedure of partial dimension reduction to obtain the finite temperature ADS2 black hole from BTG. So for this, we consider the BTG black hole, whose metric is given by this expression, where RH is the horizon radius, L3 denotes the ADS3 length scale, and phi is the angular coordinate. So we see that the above metric is of the same form as the answer we considered earlier. If we identify this phi L3 with R, so now going to the null coordinates, U equal to T plus R star and V equal to T minus R star, where R star is the tortoise coordinate defined by this relation. So the BTG metric in these coordinates, null coordinates, takes the following form. Here the first term in the above expression corresponds to the metric of the non-estimal black hole in JT gravity upon identifying L3 with L, which is the ADS2 length scale, and the angular component of this matrix gives us the dilepton profile for this case, which is given by this expression, and the temperature of this non-estimal JT black hole is given by this expression, where E is the mass of the JT black hole. So now, due to this partial dimension reduction, the space-time has been split into two parts. One is the JT black hole, and the remaining is the CFT bar system, so which is shown in these two figures. Here, this disk is the time slice of a BTG black hole, and we are partially reducing it by some angle 2 pi alpha, which is giving us the JT black hole, and the remainder of the BTG is here indicated by this light green color, and by the ADS CFT correspondence, this part has a dual CFT living on its boundary, which is the CFT2. So now we have the JT black hole, which is coupled to a bath CFT2. So in this way, we obtain black hole plus bath system from this procedure. So the dynamical evaporation for the black hole may be achieved by putting time dependence on the parameter alpha, which takes the following form, where phi r now depends upon time, this time t, and it is given by this expression. So using this scheme of geometrical evaporation for the JT black hole, the authors Verheiden and Walinde have obtained the page curve for entanglement entropy of the radiation in this setup. So now we come to our computations. So first we consider a single interval R in a bath, where the R is a union of this left and right subsystem R, and we have several choices for RT surface depending on the size of the boundary subsystem as shown in figure below. So here we have like 4 choices of the RT surface. In the first 3 figures, we have the connected RT surface, while in the last figure, the size of the boundary subsystem R is so smaller such that its RT surface becomes disconnected. So the Renan entropy of order half of this subsystem R we considered earlier in a bath coupled to JT gravity, then given by these expressions, and the Renan entropy of order half corresponding to this boundary subsystem R is then given by the minimum of all these 4 choices. So now we come to the negativity of a single interval. For pure state, the entanglement negativity of a single interval with its complement is given by the Renan entropy of order half. So the entanglement negativity of the subsystem R in the bath is given by this expression, which is the Renan entropy of order of half. So the time evolution of the entanglement negativity for single interval in a bath is depicted in the plot given below. Here we have plotted the entanglement negativity of a single interval for different interval sizes, and we see that when the size of the interval is comparable to the size of the bath, we get the full part of the page curve, which is here shown by this red and blue curve, while when the size of the interval is smaller than the size of the bath, we only obtain the part of the page curve, which is here shown by these other color curves. So now we come to the second case, the adjacent interval in the bath. So we consider the mixed state configuration of 2 adjacent intervals, R1 and R2 in the bath. So in this diagram, so we are partially reducing the BTG spacetime by some angle 2 pi alpha, and here the boundary of this colored green region is our bath, and this red part is the subsystem R1, and this blue part is the subsystem R2, and this green part is the black hole, and the size of this subsystem R1 and R2 are L1 and L2 respectively. So the corresponding entanglement negativity between R1 and R2 is given by the combination of Renan entropy of order half of R1 and R2, which is given by this expression. So in this setup we consider, we have 3 parameters, namely alpha, L1 and L2, and we can study the behavior of entanglement negativity as a function of this parameter. So we first consider the case where alpha is fixed and vary the ratio L1 by L1 plus L2. So we compute the entanglement negativity between R1 and R2, where the size of the subsystem R1 is increasing while keeping the size of the JT black hole fixed to less than that of entire bar subsystem R equal to R1 union R2. The plot of the entanglement negativity obtained using the above proposal for the configuration of adjacent intervals in the high temperature limit depicts an analog of the phase curve for the entanglement negativity. So which is shown here in this plot. So we observe that the behavior of the entanglement negativity from our computation matches exactly with that derived in the context of random matrix theory in Saporian et al. So we see that as long as the subsystem R1 remains smaller than the subsystem R2, the negativity rises linearly, since the entanglement is governed by the size of the smaller subsystem. Here it is shown in the first part of this plot. Next, when we keep on increasing L1, at a particular point, the size of R1 becomes comparable to that of R2, and the entanglement between them saturates to a plateau, describing tripartite entanglement phase. Here it is shown by this plateau part of this curve. Finally, when R1 becomes much larger than R2, the entanglement between them is determined by the size of the R2, and which is the decreasing part of this plot. So next, we consider the second case where the ratio P equal to L1 by L2 is kept fixed and alpha is varying. So we determine the time evolution of the entanglement negativity for the adjacent interval configuration by varying alpha. We obtain the behavior of the entanglement negativity for this case with respect to 1 minus alpha of T for two different values of P, which is here shown in this plot. So the excuse me, the above plot also reproduces the phase curve for entanglement negativity of a mixed state configuration obtained through the random matrix techniques in Saporian et al. So we in this plot, so we see that for a smaller value of 1 minus alpha, the size of the black hole is much larger than the size of subsystem R1 and R2, and the subsystem R1 and R2 are strongly entangled with the black hole. So by the monogamy of entanglement, the entanglement between R1 and R2 is very small, which is here shown in the first part of this plot. So when the value of 1 minus alpha, that is the time increases, so the size of the black hole decreases, and the entanglement between R1 and R2 increases depending on their relative size. Here it is shown in this increasing part of the plot. This red part is the ratio when we have the L1 is equal to L2, that is the both subsystem sizes are equal. So we have this straight line, while the subsystem, the size of the subsystem L1 is twice the is half of the subsystem L2. We have this deviating plot behavior from this straight line. So similarly, using this procedure, we can obtain the analog of the phase curve for the entanglement negativity of configuration of two disjoint intervals. So
Himanshu, you spent 10 minutes already.
Okay, yeah, thanks. Yeah, this is my last slide. Next, yeah. So yeah, to summarize, we have described the partial dimension reduction, which splits the three-dimensional space-time into a two-dimensional black hole, and the remainder, which is the holographic dual of a boundary CFT. The entropy of an interval in the bath or radiation region is obtained by simply computing geodesic lengths in the three-dimensional space-time. We have computed the entanglement negativity of a single adjacent and disjoint interval configuration in a bath coupled to a non-estimal black hole in JT gravity. We can also interpret the results, entanglement negativity results we obtain in terms of the entanglement island construction in the two-dimensional effective theory. So finally, the behavior of the entanglement negativity follows the analog of phase curve for the entanglement negativity in bipartite random mixed state obtained through a diagrammatic techniques developed in the context of random matrix theory. So thank you.
Okay, thanks a lot, Himanshu, for the nice talk and also for making my life simpler. questions? Alok, please.
Hi, Himanshu. Sorry, maybe this is a very vague question, but is there a notion of entanglement with wedge? I mean, for the negativity also, like we have for the entanglement, I mean, von Neumann entropy. Maybe I missed it when you explained it.
So, means the entanglement wedge or entanglement
in the bulk, entanglement wedge in the bulk. Sorry, I maybe I missed it when you were explaining.
No, yeah, we can have the entanglement wedge because okay, in this diagram. So say in the 4 diagram, so we have these 2 RT surfaces. So the in this case, the entanglement wedge is disconnected, while in the first 3 diagram, the entanglement wedge is connected. So
these disconnected things are the wedge for the union of them is the wedge for the negativity, or I mean, is there a notion of wedge for the negativity, or is that
no? The notion is for the boundary subsystem. So you have boundary subsystem and you have the RT surface. Then the region bounded by this RT and boundary subsystem is the entanglement wedge. Yeah. So.
Yeah, Prashant, can I comment on this?
Yes, Gautam, please go ahead.
Yeah, thank you. Yeah, yes, Alok, there is a, I mean, I think maybe Himanshu misunderstood the question. There is a notion of entanglement wedge, which corresponds to negativity. Okay, but I mean, just like there is a quantity also called reflected entropy, okay, which is twice the entanglement wedge, typically. And there is some work and proposal of Ryu and Flam, Sensei Ryu and Jonah Kudler-Flam, relating entanglement negativity to the entanglement wedge. But there is, I mean, there is a subtlety in this because there is, from some recent work by Hayden and others, that there is also something, quantity called a Markov gap. So directly relating negativity to the entanglement wedge also involves the Markov gap, which comes from Markov recovery process. So there is literature on the entanglement wedge for entanglement negativity. Right. I hope I've answered your question.
Thank you. Thanks, Noel.
Right.
Okay.
Right.
Any other question?
Can I add something?
Yes, please.
So the connection is for adjacent interval. It is very clear, but for disjoint interval, this connection is quite tricky. So directly relating entanglement wedge and negativity is quite tricky in some cases, but yes, some cases it is straightforward.
Yes, but one can always relate I mean, one can always correct a related quantity called reflected entropy. Okay, this is a work of Faulkner and Datta, which can be directly related to twice the entanglement wedge, which is also a mixed state entanglement measure.
Okay.
Thank you.
Okay, if there are no further questions, let us thank Himanshu. Let us thank all the speakers of this session, Shouvik, Aritra, Debangshu, Naveen, and Himanshu. Now Alok will tell us when should I rejoin.
Yeah, so Swapna, are you there?
Yeah, I'm here.
Okay, so I would suggest that we reconvene at 4:30. Will that be okay? 4:30?
Yeah, it's fine with me.
So that would be a half hour behind schedule, but I mean, I don't think we can push it beyond that. Maybe while we are having this little small mini tea break of sorts, the speakers of this session, if they are here, could maybe even test screen share, etc. I mean, it's entirely up to them. So let's have a small break and reconvene at 4:30. Thank you.
Hi, Naveen, are you here? Can I ask you a question? I mean, since there is no discussion session today, maybe.
Hi, Shouvik. Yes, sure.
Yeah. Hi. So I don't know this thing very well. So you talked about this bosonic exclusion principle, and then you provided an explanation using this Gepner within relation to this Weizmann-Witten model. So
yeah,
I thought this correspondence to this Weizmann-Witten model, I mean, it works only for pure Chern-Simons. So is the idea that even if you add matter, I mean, then even then you can still use this correspondence to like explain that? Or maybe I just missed.
Yeah. Actually, I skipped a few steps in my explanation. So when we express the large n Chern-Simons matter partition function in terms of this integrals over U, that integral over the eigenvalue density function, that's what I mean, that can be shown to be the large n version of this pure Chern-Simons sum over this distinguished eigenvalue configurations. Or yeah, more generally, just the partition function of the pure Chern-Simons theory in the large n limit. So we just break down the partition function in terms of an integral over U, and then the other contributions due to the non-holonomy part of the gauge field and the matter contributions, etc. Those are all part of S-end, which do not depend on the holonomy once we introduce these auxiliary variables. So finally, we have some prefactor which is independent of U and some integral over this U, which is just observable in the pure Chern-Simons theory.
I see. And therefore, you can still use the.
You just use that.
I see. Okay.
Technical, computation from pure Chern-Simons theory.
Okay. Yeah. Thanks for the explanation. Yeah.
Sure.
Hey, Nilay, you there?
Hi, Alok. Yeah, I'm around.
Yeah, so you go ahead. I mean, you don't need to be any co-host or whatever. You can just
I see.
go straight up and
Just
share.
a second.
Yeah.
Just a second then. Is my screen visible now?
Nope. I just see Nilay Kundu. Yeah. Okay. I can see.
Visible, right?
Yes, yes, yes. And can you go back and forth? Okay. Yeah.
Okay.
All good.
Is it good?
Yeah.
Thanks. And is it also possible if I, log in from an other machine, or like if I would like to see?
As long as one of the two is muted, because if both are unmuted, then there's going to be an echo.
Oh, sure. I'll make sure.
Yeah. That's absolutely fine.
Thank you.
All right,
very
good.
much.
Sure. Yeah. Swapna, are you there?
Yeah, I'm here.
Oh, great. So okay, maybe Rudranil, are you there?
Yes, I'm here.
Perfect. So maybe one can test your screen share, as I think you're
Yes,
the first.
yes. Is it visible?
Yes. Can you go back and forth? I mean, just to check. Okay.
Oh,
thanks.
I hope this is fine. Yep.
Hello, Swapna. Can I just, this is Vijay
Yeah, sure.
Shnoy. Can I just share my screen and check?
Oh, yeah, sure.
Can you see my screen?
Yeah, I can. Yeah.
Okay. All right. I'm going to unshare. Okay. Thank you.
Could you, Vijay, could you kindly go full screen and just check that you can go back?
Yeah,
and forth?
sure. Yeah. That works, right?
Can you go back? Yeah, perfect. Okay.
Yeah. You can see my pointer, right?
Yeah.
Yeah. Thanks a lot.
Thank you. Thanks.
So should we start now or wait for 1 or 2 minutes, whatever?
Maybe we can actually start, frankly. We're already 30 minutes behind schedule.
Okay. Yeah, so I welcome all of you to the last session of the 4th day of this conference. So the first speaker in this session is Rudranil Basu from BITS Goa. He is going to talk about Carrollian field theories. Okay, so over to Rudranil. You have half an hour and 5 minutes for discussion, 25 minutes for the talk, and I will remind you just 5 minutes before that. That means after 20 minutes of your time. So you can please share
Thank you.
your screen.
I'm sharing my screen. Yes. Okay. First of all, I thank the organizers for inviting me to this wonderful conference. Pardon my bad handwriting here. I got my finger injured, so I could not prepare better slides. So, basically, I'll be talking about Carrollian conformal field theories and classifying or rather constraining interactions when we have conformal symmetry, Carrollian conformal symmetries. You might have heard Aritra talking about Carrollian physics a couple of days back when he was talking about tensionless strings and what they are working on, as far as I understand, that tensionless strings have the world sheet not as a Riemann manifold, rather a two-dimensional Carrollian structure data. So I, with collaborators, have been looking at Carrollian field theories for some time. The present one that I'm talking about was in last year with my collaborators Kinjal, two Adityas and Akhila. Okay, I'll straight away go to the main point. So this is for the appetizer. We know about, so everything is known about free field theories. They are integrable systems. The very well-known symmetries which come from space-time symmetries. For example, you have the concept quantity, the Hamiltonian, which if you describe the theory, the classically you are equipped with the Poisson structure as well, if you have a massive theory. So here I'm, for simplicity, talking about a scalar field theory, free scalar field theory. So these are the very well-known, well-understood symmetries when you have a free scalar field theory in a Minkowski spacetime. I prefer to use this notation sometimes, where xi is a vector field on the covariant phase space, and sometimes if you like to work, we won't be dealing much about boundary terms here, but if you have a boundary interactions, it's sometimes convenient to work in terms of the symplectic or the pre-symplectic structure rather than the Poisson brackets. So basically, this is the same thing, but in different notation, where is xi is a generator of Hamiltonian transformation on the phase space, and consequently in free field theories they give conserved quantities as well, where Hamiltonian is here for this vector field psi that's mentioned here, gives rise to this Hamiltonian, which is the Hamiltonian in this case as well. Now there are lesser known, these are known of course, that's why free field theories are integrable, but not much interesting from various points of view. You cannot go on much with those. For example, as you might have seen here, we have A del del A minus A star del del A star. If you just plug in any arbitrary function of your momentum here, that also gives rise to Hamiltonian flows on phase space and gives rise to conserved quantities. Basically, if you write in terms of momentum space variables, this factor, the arbitrary factor, which is an arbitrary function, gets into the Hamiltonian density, and for you choose a different function and you get a new conserved quantity. And these flows form an abelian algebra in the phase space. For the free field theory, you do not expect a central extension, and they are conserved as is evident from you. You can work on this and construct newer and newer conserved quantities this way. For example, you take arbitrary derivatives of A with respect to P, plug and construct tensors here, introduce tensors here. Yes, and so if you insert tensors here, the thing is that you'll have to be a bit careful. There are some tracelessness and divergenceless conditions that you impose on these tensors, so that these quantities, these vector fields really give rise to conserved quantities on your phase space. Not only they are generators of canonical transformation. These actually are the infinite number of high spin symmetries responsible for integrability of free field theories. I will just exemplify this for newer excitations in the last decade, that these include the BMS algebra as well. For example, if you consider a three-dimensional field theory, for example, the scalar field theory, you can construct, I did not write the generator of the transformations in the phase space, but it's easy to figure out. You can construct super translation charges as well as the two-dimensional Virasoro, the conformal transformations of the two-dimensional spatial plane as well. Okay, but all this is nice and fine. If you have a free field here, you can do many things. That's not much of interest from a quantum mechanical perspective. But one may think of what happens in higher dimensions. Till date, we do not know of so many large symmetries, even at the classical level, apart from very special case like N equals 4 super Yangians, where you have hidden Yangian symmetries. It's extremely hard to find anything more than Poincare in interacting theories. Moreover, the symmetries that I have shown, or even if you think about Yangians in interacting theories like super Yangians that I told, or of course N equals 6 Chern-Simons theory also has that. These symmetries do not have in general geometrical or local action in real space. These symmetries hardly are local. Their action on the fields are hardly local. So it's not quite straightforward to understand what they generate, these transformations generate in terms of space-time symmetries. But we've been thinking of this for quite a long time. And we have been giving away. So giving up, what happens if you give up relativistic symmetry and incorporate, let's say, ultra relativistic things. In day before yesterday, most probably Rajesh Gupta have been talking about non-relativistic CFTs. There also some interesting stuff happens that we also worked on that you get to have a large number of geometric space-time symmetries if you go to non-relativistic limits. We will go to the other extreme, the ultra-relativistic limits, which is the Carrollian limit for if you start from the relativistic point of view. And we will see that you indeed can land up with a large number of global charges, large number of true symmetries of a theory if you go to the ultra-relativistic limit. Okay. So this example is here. I'll just start off, then I'll go into the other motivations behind Carrollian spacetime. So you start off this Lagrangian. I'm not talking about talking in terms of Lagrangian densities. There are some technicalities there. So let's start with the Lagrangian in a 3+1 dimensional spacetime. Right now, I do not have manifest Poincare invariance. Actually, there is no Poincare invariance at all. Where we have three fields, AI, BI. These are SO3 vectors, and BT, which is a scalar. This Lagrangian, this is also this Lagrangian. This is an interacting Lagrangian. You will see it has b to the power 4th and b square AA. This Lagrangian has infinite number of the symmetry algebra is infinite dimensional, which is exemplified, for example, if you have a transformation like this, where f of x are the spatial coordinates, this acts on the scalar this way, one vector this way, which mixes bi and bt, and the other transformation this way. Since f is an arbitrary function, this symmetry algebra is infinite dimensional. This is abelian. This part is abelian, of course. What I'll show straight away is that this forms the abelian ideal of an infinite dimensional Lie algebra, which we prefer to call as Carrollian conformal Lie algebra. If you plug in f equals to 1, that is your well-known time translation. If you plug in for f as any one of the three coordinates, let's say flat R3, the spatial part, what you get is Carroll boosts. Here we see that space and time do not have equal footing. And for example, if you put f equals to x squared, you get temporal part of spatial conformal transformations. Apart from these, there are a finite number of generators. You get spatial translation, which is the usual one. You have dilatation, scaling symmetry, and spatial part of spatial conformal transformation, and spatial rotations. Yeah, in this case, since we are interested in 3+1 dimensional theories, this will be SO3. Now, this part is infinite. As I've been telling you, that this forms an abelian ideal of a larger algebra, and these are the finite parts of it. We call it Carrollian conformal algebra. Now, if we look at the global or finite part of it, this has this SO5, which is composed of rotations, spatial translation, dilatations, and spatial parts of spatial conformal transformation. They form the SO5. And if you introduce these generators, which are parts of this, if you wish, super translations, which are spatial dependent temporal transformations, which has special cases, the Hamiltonian and Carrollian boost and temporal part of the spatial conformal transformation. If you plug in all of these, what you get is the ISO5. And if you have all of these MFs, you get this infinite dimensional Carrollian conformal algebra. We have been looking at free field realizations of these symmetries for quite some time. And we did a couple of interacting theories as well, but now I will do how do we get to this theory? We just do not write down some Lagrangian and see that, okay, so we have kind of made a systematics for finding, searching for Carrollian conformal field theories. There's some kinematical tools as well as the dynamical ones. So this is the kinematics. We start with the space-time, which is non-Riemannian. So if you wish, not a space-time at all, which is equipped with a rank 2 covariant tensor. which is degenerate, of course, and you have a vector field such that everywhere in the space-time, this gives you the null direction, xi kills of G in this sense. And we define conformal isometries in a sense this way, that it preserves, you should be looking for vector fields which preserve G up to conformal factor, and which as well preserve this vector field, this is a special vector field, up to a conformal factor. The choice of the ratio between two conformal factors is yours, and we have chosen it to be -2 for reasons because we can then find free field realizations of these symmetries. I'm not very sure of if you choose any other integers and whether non-integers are allowed as well. But for our purpose, we will stick to this ratio of -2. And since we are interested in simplest of physics, we choose a flat Carroll structure. That means we choose a metric which is flat in spatial directions, and we choose the special vector field which is in the time direction. And it can easily solve these differential equations to give you the solutions. Now, in the solutions, the arbitrariness is there in terms of a function. So basically, that tells you that you have an infinite choice of vector fields. All of the other coefficients, omega, pi, delta, ki, these are constants. That means the other parts give you a finite number of generators. But due to this part, which forms an abelian ideal of the algebra, gives you an infinite number of generators. Duval, Hlavathy, and Gibbons have been talking about these structures for quite more than a decade. And they have interestingly shown that Carroll structures actually reduce to BMS algebra, which is the asymptotic symmetry algebra of asymptotically flat spacetimes in appropriate dimensions. For example, if you if you're working in 4-dimensional bulk and you wish to call BMS4 the asymptotic symmetry algebra, which has the super translations as well as the global conformal symmetries of the two-sphere, you get everything packaged here. Similar thing happens if you are interested in 3-dimensional asymptotically flat spacetime. The only thing is that in those special cases, for example, if you are in 4-dimensional bulk, the S2 has not globally defined, but infinite dimensional conformal symmetry of the S2. For that, solving these differential equations needs a bit of special care. You get the Virasoro as well, so the super rotations as well as the super translations. As a similar thing happens if you are in 3 dimensions. But we are right now not focusing exactly on a prescription of celestial holography or holography right now. We are dealing with very simple-minded analysis of a field theory in 4-dimensional spacetime, where our spatial slices are flat. Okay. To see how these transformations, these diffeomorphisms are connected to theory on Carroll manifold, we need to see how they act on fields. Now, this is a bit not so straightforward, because we wish not to work with tensors on Carroll manifolds. We have something different in plan, because we want to see operators which have specific dilatation symmetry and which transforms nicely under the spatial rotations. In that sense, so that requires a little bit of work on the representation theory, and I'll not detail what's written here. Basically, all the generators, how the generators act on the fields. I have not written transformations for arbitrary rank tensors. We are now pleased with what we have for scalars and vectors, and not higher spin fields right now, because we are trying to mimic something like gauge theories with spins not greater than 1 in 3+1 dimensions. That's why we are limiting ourselves to scalars and vectors. Now, from the dynamicals perspective, we start from the understanding that Carroll physics is basically, if you just blindly think of Carroll physics, is the ultra-relativistic limit of relativistic physics. In one way, you can think C goes to 0. And if you start with, for example, a Minkowski spacetime and a photon field, gauge field mu, the following limits are there, which is a magnetic and which another is the electric limit. There are reasons. For example, if you start with Maxwell's electrodynamics, you go to use the first limit, you go to you use the Maxwell's equations, and you get equations which have magnetic fields dominant, and in the second case you get the electric fields dominant. So epsilon is a small number. After doing all your analysis, you keep the predominant powers of epsilon and see what happens there. This is the 0th order way to understand this. Funny enough, so if you start with...
Yes. 5 more minutes. Rudranil, you have 5 more minutes.
Yeah, it's fine. So, funnily enough, if you use the magnetic limit on this equation, you get you lose the scalar part of your 4-vector potential, and you get these equations, and this is in a sense meaningless. 2 equations for AI, and hence they cannot come from an action principle unless you have some other fields. You don't have an action. Moreover, these so we thought about these equations earlier. These have Carroll symmetries, but only weakly. That means that if T is your equation of motion and star is a generator of a symmetry, and if you do the variation and it so the equation remains infinite only on shape, we call that weak invariance. Rather, there's a version which is a strong invariance. This says like this: if you have a number of equations of motion which are coming from varying for example, if you have an action and if Tk is the equation of motion corresponding to the field phi k, this condition is what is known as strong invariance. So there's a little subtlety that weak symmetries or weak invariance always has to be taken with a grain of salt, because in cases more often than not, weak symmetries are not often true symmetries because they are in many cases are not symmetries of the action. You can check, for example, if you take a complex scalar field and you do you do a transformation where your parameter is complex, not e to the power I lambda, but it has a real part as well. Your equations of motion are invariant, but your action is not. So in those symmetries are not true symmetries in that sense. Now, what we do is that we introduce newer degrees of freedom. So since we landed up with equations of motion, which cannot come from actions, we introduce newer degrees of freedom and see if we really can construct a consistent theory or an action. So this is known as Helmholtz criteria, integrality criteria. If you have a set of differential equations, then Helmholtz criteria says that there's a set of conditions. I'm not exactly going into the details, but say that if these conditions are met, then it's guaranteed that these equations come from a variational principle. So you introduce newer fields in the system, check for Helmholtz criteria, and check at every step whether conformal Carroll, this infinite dimensional symmetry is intact or not. This is a very rough cartoon check, the way we check. We start with an equation of motion, we pass it through Helmholtz criteria. If satisfied, fine, go and check full Carroll symmetry. If no, then add SO3 tensor. Basically, in this case, we try first by adding scalars and vectors at second order derivatives, since right now is at the tree level, such that we get back in a way that we had started with the limiting equations of motion, in a way that if we turn off those extra fields, we really get back the limiting equations of motion that we started off with. So this iteration is a self-consistent algorithm, and in most of the cases where we did not have equations of motion, we can succeed in finding a symmetric equation of motion. With one or two iterations, it converges. If not, that means you'll have to try with higher rank tensors. Okay, so for the present case, if we started off with Maxwell's electrodynamics, we only had the AI, the spatial part of the vector potential. And in this case, we had to add one scalar and one vector, which gave us and the consistency check passed through and gave us this set of three equations, and that which can come from a Lagrange, which has Carroll symmetry as well. We have an undetermined constant here, which can be fixed as per your choice. Now, the thing is that we wanted to see, look, so we started from a relativistic theory, we got up to an action which is inconsistent, we added newer degrees of freedom, which is consistent in terms of a variation principle. Now we were trying to see if there is a relativistic parent from which this new theory with the new fields can descend. We started off with a theory of two vector fields, but funnily enough, we did not find any such. So maybe it does not have a relativistic parent, or if there is, so you'll have to gauge fix some part of it. That part is not clear to us, but the zeroth order guess did not work. And about interactions, we added all possible quartics since we wanted to keep scale invariance. For conformal Carroll invariance, only a couple of deformations were allowed. So this is one is bt to the power 4, another is bt square, and the vector potential square. These two deformations were allowed. So this is the the conformal Carroll invariant theory that starts from a magnetic limit of Maxwell's electrodynamics. And if you want to incorporate interactions, you can incorporate interactions without thinking of gauge anymore, because anyway, these equations did not have gauge redundancy anymore. So we have lost that case. So we also tried to restrict 2-point functions based on global symmetries alone. Most of the 2-point functions do vanish, apart from a couple of two. This may be compared interestingly with what happens with ordinary electrodynamics. For example, if you have two correlations, photon propagators, but situated at two fields situated at causally disconnected, causally not connected points, you get actually similar kind of forms of 2-point functions. So this matches up to that case if you make a proper choice of gauge. So the xi parameter, if you choose R gauge, or you keep a parameter of xi which parameterizes your gauge, these 2-point functions are nice when you take the Carroll limit. This can be understood in a way that, so in the left panel I gave 3 points, A, B, and C. If you are in Minkowski, A, B are causally disconnected, and C is causally connected with A. However, if you take Carroll limit, your light cone converges to a single line, so it basically shrinks, and all points are causally disconnected. So if they are at spatially separated points, two points are causally connected if they are at exactly same spatial location. So in that sense, if you start off with different x1 and x2, you always have causally disconnected points. So that therefore, in order to check, so So even tree-level two-point functions, you have to think about two different branches. One is if they are located at exactly same point, that requires special care. In most cases, we have seen that if you start out with exactly same points, there is contact terms in terms of delta functions or derivatives of delta functions, which have different significance. If you, for example, consider three-dimensional Carrollian field theories, which may be believed to related to celestial holography. There also, you come across contact terms in two-point functions. We are working on something on that and try to see if, starting from a Carrollian field theory, you can see those contact terms appearing. This thing that I mentioned already earlier, does our interacting Carrollian theory have a relativistic parent? It seems no, for example. So this diagram does not come, you start with a Lorentz invariant action and you take ultra-relativistic limit, you get a Carroll action. This is one route. The other route is you start with Lorentz covariant equations of motion, you take ultra-relativistic limit. So this Carroll action does not always correspond to Carroll invariant equations of motion. So, and about what are the other things that I'm thinking in this line is right now. So you have this infinite number of symmetries, you have an exact action. You must be curious whether this large number of symmetries how were they spontaneously broken or not. And whether if you develop anomaly for those super translations, if you do a one-loop calculation with these interactions at hand. That might be something interesting in terms of the way we understand Carroll physics or even physics described by celestial holography. That's all I had to tell now. Thank you for your attention. I'll stop.
Thank you, Rudranil, for this nice talk. Are there questions? We can take only 2 or 3 short questions. I can see here, Agniva, do you have a question here? I see a raised hand.
Yeah, so a small question. Basically, where Rudra wrote the metric, it seems that the special part is the delta ij dxi tensor product dxj.
Right.
So I fail to see how this is a non-degenerate metric.
This is a degenerate metric.
Yeah, so I fail to see how, right? I mean, it's just delta ij along the.
So basically, you are in 4 dimensions, let's say, and your I and j runs from 1 to 3.
Right.
That's why you do not have one component. If you write the matrix, you have 1 0 in the diagonal and.
Oh, okay. And another thing is in this space, the physics, is it easy to introduce spinors? Because I mean, I don't seem to see any SL2C kind of transformation on anything here.
No, if you start from the representation, it's hard to get how you would introduce spinors. I have collaborators who are working on that right now. But if you start directly from Dirac spinors, you can land up with a prescription of spinors which have a transformation, have their own transformation properties under Carroll boost. That's the most non-trivial part that is different from your Poincare invariant theories. But if you really want to find a spinorial representation, that's non-trivial, and my collaborators are working on it.
Oh, okay. Thank you.
Okay, any other question? Okay, if not, let's thank Rudranil Basu for a very nice talk.
Thank you.
So next I invite Nilay Kundu from IIT Kanpur to kindly share his screen and start the talk.
Sure.
So Nilay is going to talk about entropy current and second law in higher dimensional theories of gravity.
Yeah, I hope my screen is visible.
Yeah, it is.
Okay. So I would like to start by thanking the organizers for giving me this opportunity to present our work. And I'll be talking about entropy, current, and second law in general diffeomorphism invariant theories of gravity. So please feel free to stop me at any point if you have any questions. The references for this talk are these two work which we did in the last 2 years, along with Shantanu Bhattacharya and Jyotima Bhattacharya and a group of students. Anirban Dinda, Milan Patro, and Shubayu are students at NISER, and Prateek is a student at IIT Kanpur, PhD student. And both of our work are crucially dependent on another work which Aaron Wall did a few years back. So that's the references for this talk. So I'll start with some general motivation or introduction. In classical two-derivative Einstein's theory of general relativity, black holes are interesting solutions and they behave as thermodynamic objects, so that we can associate geometric notions like temperature or entropy with them. And then we know via the area theorem that the area of any of the event horizon of any black hole always increases. And this gives us a geometric notion of entropy, which follows by some laws in black hole mechanics. And in that, by those laws, there is a intriguing similarity or analogy with the laws of thermodynamics. By the work of Bekenstein and Hawking, we kind of came to know that this is just not analogy. We can have a robust correspondence. For example, the fact that in general relativity, entropy is proportional to the area, we can fix the proportionality constant. So it's at that level. And we also know by the black hole mechanics, or so to say, the geometric notion itself helps us to kind of know a bit of something about first law and second law. Both of them are known to be satisfied. Now, in theories of gravity, which is beyond general relativity, we know that low energy limit of any UV complete theory of quantum gravity is expected to generate high derivative corrections to the leading two derivative Einstein-Hilbert action, for which this is my Ricci scalar and the leading two derivative action, and I can have other candidates which I will term as high derivative theories. And then I can have also, apart from pure gravity, some matter fields which are present in the theory. And black holes are still solutions in such theories, and we should believe that they should retain their thermodynamic properties as well. So we should have a geometric definition in those kind of high derivative theories or general diffeomorphism invariant theories of gravity. And it's not necessary that the area of the horizon, or the event horizon, happens to be the same definition of entropy. So there is one such entropy, definition of entropy. Again, this is again some geometric definition, by which I mean, if I'm given the Lagrangian of a theory, which is something given here, with this calculation, I can compute this quantity S world, or it's called the world entropy, which will be the entropy of the black hole in such theories. And this definition was constructed. By construction, it satisfies the first law of thermodynamics. And then we should probably ask whether this should be valid. There should be any second law for such definition of world entropy. And in general, there is no proof, except for certain examples, that the second law is satisfied for world entropy. Actually, one can argue that there may be situations where this definition of world entropy does not satisfy a second law. I mean, this is known in certain examples. For example, if you take a particular model of a theory and then you do some calculations, but there is no general proof in any arbitrary theory of gravity. It is also known that the definition of world entropy has certain ambiguities, which kicks in once you go beyond the equilibrium or the stationarity, and these are called JKM ambiguities after the names of Jacobson, Keynes, and Myers. So the total definition of entropy will be the world entropy, and plus some terms which I will call as JKM, such that at the equilibrium or at the stationary point for stationary configurations, this SJKM will vanish. So there is no ambiguity for what is a definition of a black hole entropy in such theories at the equilibrium point. But when you would like to extend that to non-stationary processes, then one should think about how to fix these ambiguities and all. So the main question that we were after, actually, a lot of people have worked on this, is can we construct a proof, a general proof for a local version of a second law for dynamical black holes in arbitrary diffeomorphism invariant theory of gravity. And this is, when I say arbitrary diffeomorphism invariant theory of gravity, I'm not basically focusing on just GR, so extensions of GR as possible. And this is by itself, in my opinion, an interesting question just in the field of gravity. So I'm sorry for not quoting the proper references, but as I said, Aaron Wall in 2015 gave a construction where indeed a local version of the second law of black hole thermodynamics in such arbitrary diffeomorphism invariant theory of gravity was constructed, but it has some subtleties. So that's why we started to learn that paper, and then we understood that there are some subtleties, and it's a version of second law of thermodynamics which is local in time but not in the spatial extent. I'll be more explicit as I go along. And so what we have done is have come up with a construction of an entropy current. What do I mean by this? It will be clear, but just to give you the idea that this is if we are working in d space-time dimensions, this is a d-1 vector defined on the horizon, which has time component and spatial components. It has by construction a non-negative divergence, and that gives us to come up with an ultra-local version of the second law, by which I mean local in both time and space coordinates, unlike this construction of Aaron Wall, which was local in time but not in the space coordinate. So, and how to understand it physically, just to give you an idea that non-negative divergence of an entropy current is the statement of second law. So what we have is not just a local entropy production, but also we come up with a mechanism due to the spatial components, which tells us that there is a spatial redistribution of entropy density between different adjacent spatial regions of the horizon. Basically, some inflow and outflow of entropy density on the spatial slices or constant time slices of the horizon to reach a final equilibrium. So I'll be more explicit as I go along. Now, just to give you a quick idea, what's the statement of second law in gravity? So for that matter, this is obviously a statement beyond equilibrium, because by first law, we only compare nearby configurations, which are state functions. So for second law, we must go beyond equilibrium. So if I start with an equilibrium configuration and I reach a final equilibrium, so the total entropy associated with the final equilibrium must be greater than or equal to the total entropy associated with the initial equilibrium. That's a notion of second law, which we know. Now, for gravity, what we have to think about is what is an equilibrium configuration. Technically speaking, that gives us a metric with a killing horizon that we take as a stationary configuration or an equilibrium configuration. And then there should be a definition of an equilibrium entropy, which is valid at the equilibrium point. So some black hole entropy on the killing horizon for initial equilibrium and the final equilibrium. And this black hole entropy could be the area of the horizon in Einstein gravity, and it would be world entropy in general high derivative theory of gravity. And just to mention this world entropy, if you consider for Einstein gravity, it reduces to actually area of the horizon. So we consider the most general diffeomorphism invariant theory of gravity. IR-Wall constructs such an example where we have an action which is some Lagrangian. The gravity part of the Lagrangian can have arbitrary dependence on the metric, the Riemann tensor, and covariant derivative of the Riemann tensors and such that. So this is what we start with. This is our theory. For matter part of the Lagrangian, we only assume that the stress tensor of that matter theory satisfies some null energy condition. And we don't consider anything beyond that. So we don't consider the matter to be quantum and it's having its own entropy. It's like the basic starting point of situations where, we're trying to just understand if there is a definition like the area of the horizon in Einstein gravity, just a classical analysis. This is not even semi-classical where we treat the matter part quantum mechanically. So the equation of motion that follows from this theory will be given by this, where this T mu nu will follow from the matter part, and this capital E mu nu will follow from the gravitational part of the Lagrangian, and this curl E is the total equation of motion, or that thing. Now, very crucial element in our construction is the setup where we kind of choose a particular metric gauge. Now, for that, we have coordinates R, V, and Xi's. Let's say we are working in d-dimensional spacetime, and we are considering arbitrary dynamical black hole configuration. The horizon we choose to be fixed at r equals to 0. So this is this surface over here, which is at r equals to 0. And then the coordinates on the horizon are given by this V and Xi's. So R is a coordinate that flows along this green lines, which goes away from the horizon. On the horizon, we have this blue lines, which gives me the flow of the V coordinate, and these red lines are the constant V, or constant time slices spanned by the coordinates Xi's. So what we say is that this any dynamical black hole spacetime can be brought to this particular metric gauge, where we have some conditions where, and additionally we have put some conditions like we choose this V and R to be affinely parametrized. So that brings us to this form of the metric. And more explicitly, we can, bring factor out some factors of R. So this GVV over here follows this condition, which is the definition of the horizon, and also this condition, which follows from the fact that V is affinely parametrized. So ultimately, it will start with an R square over here, and this is arbitrary functions of R, B, and X. So such that we have X, omega I, and Hij as functions, metric functions, and we can have their del R, del V of nabla. Nabla is the covariant derivative associated with the Hij. So these are the basic building blocks in our construction. Then we are studying dynamical processes where we start with some stationary black hole solution, let's say, then perturb it with some matter that satisfies the null energy condition. And after we have perturbed it, it finally settles down to another stationary black hole metric. That's the processes we are trying to study. So we start from equilibrium configuration and we reach a final equilibrium configuration. So the total metric can be written in a perturbative analysis where the G mu nu EQ is for the starting stationary or equilibrium black hole solution configuration. And this part is corresponding to the matter source, which perturbs it, which has a small amplitude. So we will treat this parameter epsilon in a small amplitude expansion. And then the main result of our analysis is a statement about gravity. I just want to make it highlight it that even if you forget the context of second law or anything, in any diffeomorphism theory of gravity, the off-cell structure of an equation of motion can be written like this, where we look at the VV component. I have determined what is the V and V coordinate. So the VV component, when computed at the horizon, will always have a structure like this, expanded up to order epsilon square. So this is the main result that we have obtained in our paper or in our work, and then we can use it and we can connect it to second law and all. Actually, that we have not done, that was done before, but this specific statement about any diffeomorphism invariant theory of gravity, this is basically what we have done. So just to highlight that this Hij is the induced spatial metric on codimension 2 constant V slices of the horizon. H is the determinant. Nabla is the covariant derivative compatible with Hij. And now, so as you have figured out that, or as I've already told you, this curly EVV has two parts, EVV and TVV. So this is actually the gravity part of the equation of motion, or rather VV component of its. up to linearized order in the amplitude of the fluctuation. So this is the main result. And now we will use it to connect it to the second law, and that's why the name entropy current comes in. So remember, we have this structure. So null energy condition means TVV is greater than equal to 0. The VV component of the stress energy tensor is greater than equal to 0. On shell condition means this EVV has to be 0. So this EVV part, this part which we have written like this over here, must be less than equal to 0. Now, if you look at this structure, then we also assume that in the future, we settle down to another stationary black hole configuration, which means the quantity inside should settle down to 0 as V goes to infinity. So this object is an object which goes to 0 as V goes to infinity, and its V derivative is less than equal to 0. So this object as a function of V is a monotonically decreasing function, but it goes to 0. So this quantity is greater than equal to 0 for all finite V. Now if you look at this, we should now probably justify why we call it entropy current. So this we have argued this thing, and this JV quantity over here looks like an entropy density with the JKM ambiguity is fixed, and it should match with the world entropy when equilibrium limit is taken. This JI component actually gives us the entropy current density, which signifies a spatial flow of entropy locally at each point of constant V slices of the horizon. And we have argued that this is indeed true. So that's what I will probably do in the rest of the time that I have. So we use a residual coordinate transformation freedom. So we have fixed the gauge to be like this, which still gives us a freedom to do a scaling of this type, where this R coordinate is scaled by a constant parameter lambda like this, and the V coordinate is scaled with the inverse factor of lambda. And we can show that this is generated, by this vector field, and we call this the boost transformation. Actually, this is in the perpendicular plane of the horizon, in the V and R plane. This is like a boost transformation. And then I should tell you what is we have taken an order epsilon square limit, right? So how to take that limit? So under this transformation, which is generated by this vector, this metric is invariant, by which I mean that this G mu nu, which I have written here, if you take a Lie derivative with respect to the vector xi, which is given by this vector, is 0. And if you see the differences over here, where the metric functions can depend on the factor V, but the R and V always comes as a product. So any general space-time can have any dependence on R and V, but for stationarity, this has to be R times V. And this is actually the boost symmetry, or I have defined for you the equilibrium limit. And then you can define how any generic quantity A, which is built out of the derivatives of the metric components and their derivatives, how do they transform under this boost transformation? So the metric remains invariant, and if this any quantity A transforms with a factor lambda to the power W, then W is called the boost weight of that quantity A. So this is true for any quantity if that is built out of this metric coefficients and their derivatives. And you can see that this quantity R and V have boost weight +1 and -1. All the metric functions are boost invariant, because if you see X, it has a factor of R square and a factor of V square. So X is boost invariant, omega I is boost invariant, and Hij is boost invariant. So we can classify everything in terms of their boost weights. And basically, if you take the Lie derivative of any object, then it transforms like this. And from there, you can see that this W, if you have, look at the components, then it's the number of V coordinates minus the number of lower R indices, which is there. That gives me another way of understanding what is the boost weight. And then stationarity or out of stationarity means that if some object B is constructed out of this object R times V, that's the definition of equilibrium quantity, then whenever, if I look at any arbitrary quantity A, which is defined like this, which has more del V derivatives than del R derivatives, then whenever it operates on any functions like this, it will bring down factor of R hanging. And then if you take R equals to 0, which is the horizon, so you're computing things on the horizon, so it will vanish. So this gives us what is the equilibrium limit. Take everything, anything which has some del V derivative more than del R derivative acting on equilibrium objects, that will become 0 when you take equilibrium configurations. So I'll skip these things, and this will also kind of tell us how to organize things which are of order epsilon, which is the breaking of this stationarity. So whenever you have object which is a product of two quantities like this, where in each of them you have del V derivatives more than the number of del R derivatives, so you will get an order epsilon from here and order epsilon from here, so there will be order epsilon square. So I'm telling you that's how we kind of organize the things, which quantity we are looking at a off-cell structure of the VV component of equation of motion, and then we have to decide which one is order epsilon and which is order epsilon square. So this gives us the rules for doing that. And then I'll tell you why the VV component of equation of motion is so significant in arguing the second law. So this is the definition of the world entropy, and this is the world entropy density. Let's say this one is from the Einstein gravity, and this part is from the higher derivative part of the Lagrangian. Now, this is a valid definition at equilibrium. If you have any out of equilibrium pace, then that part should vanish when you take the equilibrium limit, because the world entropy is valid at the equilibrium point. So what are possible S corrections that you can add to the world entropy that can give you an extension of the entropy for non-stationary or non-equilibrium quantity? Now what you do is this S total is defined like this, and you take a V derivative of it and define something called this theta, which is like the expansion in the Rai-Choudhury equation, the expansion of null generators, congruence of null generators, and then you take a further del V derivative of that. So it's just organize it up to order epsilon square. This comes like this. So no equation of motions has been used till now. Now, if you use the equation of motion, you can change this RVV in terms of TVV and the EVV-HT, which is the contribution to equation of motion from the higher derivative part. So that takes us to this quantity. Now you see, if we are in Einstein gravity, these two parts are not there. And then if you impose TVV is greater than equal to 0 by null energy condition, so you say del V theta, which is here, is negative. So del V theta is negative, and theta goes to 0 as you go to V equals to plus infinity. So theta is always positive. Now if theta is positive, del S total is positive, and that gives us the area increase theorem, basically. But for higher derivative theory, we have these two parts. Now, if they cancel themselves up to order epsilon square, then we can get a proof for the second law. And you see that this is what we want, and this is what we defined as a entropy current. Now, if you see they are of the same structure, if you can identify this JV with this object, and that gives us the thing that this component so this was a result just by looking at the equation of motion. And now if you take the equilibrium limit, it indeed gives us the entropy density for the world entropy. So I'll skip the details. I think I don't have enough time. I think
you have 5 minutes.
Okay.
You have 5 minutes.
So, yeah. Thank you. So so this is what actually we did. So now just let me tell you how did we do it? Just to tell that, so we need to look at the structure of equation of motion, the VV component of the equation of motion. We just use the IR world Noetherian prescription, where the variation of the Lagrangian is related to the equation of motion plus a total derivative. So we can massage this and we can probably arrive at an equation like this, where this EVV is the VV component of the equation of motion, theta is the theta that you get here. Basically, these are the symplectic potential or symplectic current, symplectic two form, this Q mu nu. But I mean, what is important is that we know from the construction of IR and Wald what they are. If I'm given a Lagrangian, any diffeomorphism invariant theory of gravity, if you give me a Lagrangian, I know the expression for theta and Q mu nu. So all that we did was to kind of look at those definitions given in IR and Wald, and then just see if they can be arranged in that structure. That's what we actually did, and we used this boost invariance and all. So basically, you can see that theta r is given by this expression, Q is given by this expression, and from there you can prove that up to order epsilon square, the VV component of the equation of motion looks like that. So what it does is actually it gives us an algorithm where, JV and JI for, we can take a theory, take its Lagrangian, compute this theta and Q, look for this B naught and this Q tilde, and then we will know what is the JV and JI. So that's what we did. It gives us an algorithm for this JV and JI. And then, in one of our paper from 2020, we actually, forget all this. That's what actually we did first. We took specific models, like examples of theories, and computed the VV component of the equation of motion. And it needs clever reorganizations, but you can indeed check that you get some JV and JI, which are given here. And then you can follow this algorithm that we kind of came up with, this abstract proof, and then see whether they matches, and they exactly matches. So that gives us a confidence that it works. So I will end with just an interesting understanding of this. Let's say we focus on the Einstein-Gauss bounded gravity in 3+1 dimension. So all our calculation was not specific to any specific dimension or anything. It works for d equal to 4, d equal to 5, 6, 7, all dimensions. So let's focus on d equal to 4 dimensions. We know that Gauss-Bonnet term is a total derivative. So we should not get any contribution to equation of motion from this term in 3+1 dimension. So this is the equation that we claim is what we have shown. So this part is 0. But if you compute the equilibrium Wald entropy following the formula that I gave you, it gives you it gives you basically the Ricci scalar of the codimension 2 surface horizon slices, which for us is a 2-dimensional surface because we are in 4 dimension. So this is if you integrate it, this gives you the Euler number. It's a topological number, but JV is non-zero if you follow that definition of Wald entropy. So it kind of looked like a puzzle that we have a 0 on this side and we have non-zero JV. But we kind of, if you kind of allow for this JI, which is indeed there for Gauss-Bonnet theory in 4 dimension as well. So there is an identity in 2 dimension basically, which tells you this right hand side is also 0 and the left hand side is also 0. So it's a 0 versus 0. So what happens is the total entropy probably doesn't change because this is an Euler number, but a non-zero spatial current accounts for the change in the local entropy density. So for future directions, one major abstraction over here was the fact that we chose a particular gauge of the metric. So it's not a covariant construction. And also secretly the null surface, a lot of bad thing happens. The metric goes degenerate and stuff like that. So we should basically come up with a covariant construction of this. We can extend it beyond linear amplitudes. We should have a fluid gravity interpretation because if we do the whole analysis in ADS space, in the boundary, we have a fluid gravity construction that gives us an entropy current. So probably there should be a map that will give us the entropy current on the horizon. And there are also interesting connections with holographic entanglement entropy and stuff. So I will end it here. Thank you for your attention.
Thank you, Nilay, for a very nice talk. So there's question, question. I see Agniva raising her hand for a question. Please go ahead with your question.
Hi, so I have two small questions. One, it seemed this EVV expression that you wrote, it seemed that everywhere it is order 1 and then order epsilon square.
Well, so this part will have order epsilon or whatever it is. But
okay, so there is also an order epsilon and an order epsilon square term. I mean,
yes.
Okay. Okay, and these black holes whose corresponding entropy, are, I mean, are they charged? Do they have some angular momentum, or is it like nothing?
I mean, it can have anything actually. That's the interesting thing. You know, we don't look at the solution. We don't do it on shell. We are, you know, okay. I mean, ultimately, it should be a solution of the equation of motion, and it should come up with its own mass and charge. What are the charge? That's are the charges. But we are just making statement about the off-cell structure of equation of motion, and that is so powerful that gives us all this thing. And you know, we probably ultimately put it to equals to 0 and look for particular metric or Schwarzschild, Carr, whatever you want in ADS space or.
Okay.
So it can have. I mean that part was not very important for our construction.
No, but in the, I mean, the reason I ask is, yeah, I mean, it should appear as in the final expression for your entropy, right?
Yeah, it should have, but you know, we have not been very, so they will probably enter through this expression. So if you take particular, work it out for particular, you know, theory and particular theta q bit tilde. So this part is for the JKM ambiguity, and this is the world entropy base.
Okay. And this pre-symplectic potential that you wrote, the theta, capital theta, I mean, is it globally exact?
Yeah. All that stuff actually. Okay. Yeah. I mean, well, if you ask me if it's we have just looked at diffeomorphism invariant theory of gravity. So it's one of our future directions. Probably we are looking at if you have, you know, Chern-Simons theories of gravity, what will happen and all that stuff. But other than that, everything that we know about this theta and q mu, they still holds here.
Okay. Thank you.
Okay, TIFR has a question. Please go ahead with the question.
Hi, Nilay. That was a spectacular talk. Two sort of questions.
Yes.
The first one was probably not very important, but you said you said that one of your conditions was this null energy condition that was the on the stress tensor. Now, yes. The stress tensor is defined as whatever appears on the right-hand side of the modified Einstein equations. Is this right?
Yes.
So I was.
So yeah, if you take, yeah.
I was wondering whether that condition was invariant under field redefinitions of the metric. By which I mean, you know, you could think of the stress tensor as being like the derivative of the Lagrangian with respect to the metric.
Yes.
And if this condition is true with one. But since you're dealing with higher derivatives theories of gravity, you should all the statements that you make should presumably be invariant under field redefinitions of the metric, like redefinitions like G mu nu goes to G mu nu plus R mu nu. And is it clear that if this condition is invariant under such field redefinitions?
Yes. So what I need to think about it to give you any, I mean, just to understand your question properly. But what I can say is, you know, in the metric gauge that we have chosen, we have been able to argue that this T mu nu never kind of creates a problem, because the field redefinitions that you are probably talking about should also keep in mind that we are fixing a gauge. So
I'm not talking about coordinate redefinitions. I'm talking about metric field redefinitions. So G mu nu goes to G mu nu plus R mu nu, that kind. You know, so what your stress tensor is will depend on what your metric is.
Yes.
Now, in Einstein gravity, there's a canonical choice because there's one choice of metric that makes your Lagrangian two derivative. But once you go to higher derivative theories of gravity, there's no canonical choice anymore. And one should allow field redefinitions of the metric. And I was wondering whether this condition that you imposed was, if it was true in one field frame, would be true in others as well. I think it's not very important for your proof because it's perturbative.
Not very important for our proof. For example, you know, just like theories like, you know, if you look at f of r theories, then field redefinition can bring it to Einstein gravity plus matter, scalar fields.
Right.
So those kind of situations will be taken care of by our construction, but I'm not sure, you know, I'm not able to say about other cases, for example, F Riemann type of theories, it certainly works, but is there a general proof that this T mu greater than 0 is still true? That I'm not able to come up with an answer right now.
Okay, one more question, if that's okay, Swapna.
Yeah.
Okay, yeah, okay. At the end of your talk, you talked about generalizing this theorem to nonlinear order as one of your future directions.
Yes.
I was wondering whether you
yes.
expected it to apply at nonlinear order to every theory of gravity, or your expectation would be that it would fail at nonlinear order for most theories of gravity, and this would be a criterion for allowing for good theories of gravity. For instance, if you took Einstein-Gauss-Bonnet in 5 or higher dimensions, we know that such theories violate causality. So somehow sick theories, and perhaps the sickness will show up in the fact that there is no positive energy theorem for such theories at nonlinear order. Is this a possibility?
This is a possibility, but I will give you even the simplest example. Einstein gravity. This is not true that the structure of this equation of motion that I've told you holds true beyond the linear order. But interestingly, the extra term that appears comes with a definite sign that makes the del V theta with the desired sign.
Right. So that's consistent with the fact that Einstein gravity is a good theory. But
it is a good theory.
Know that Einstein-Gauss-Bonnet in 5 dimensions and higher is not a good theory because it violates causality.
It will show up in one of its. It will show up in one of its avatars. But yeah, I don't know. But I just wanted to mention that in one of our old work, we have actually looked at the Einstein-Gauss-Bonnet gravity, but not in an amplitude expansion, but in the frequency expansion. There we could, complete the proof up to all order in the Gauss-Bonnet parameter. So I don't know, but what you are saying is definitely a possibility.
Thank you.
Okay, so Amita Virmani has a question. Please go ahead.
Yeah, thank you, Nilay. Very nice talk. Actually, I have a question about one of the last slides where you mentioned this Gauss-Bonnet thing. So this GI, so go below. Yeah. So these Kij terms, these terms comes from your algorithm for constructing the GI. I did not follow that.
Yeah, I mean, so it will come. So if you are, if you are not interested in this probably sophisticated higher world construction and all, you can just take the equation of motion and just write in brute force. Then you will see that this structure is there. And also this comes from our JV and JI type of algorithmic structure as well.
Okay, and related point, so this JV and JI, so maybe you were not able to go into too much details in your talk, but JV and JI, the notation that you have used, they must form a vector on the null surface.
Yeah,
and,
they could form, but I should have written this whole combination as some del mu J mu, but I'm not doing this because there are subtleties on the null surface, it's degenerate, so how do you take an inverse and all? But probably it's one of the future direction that you can come up with a covariant analysis, maybe some near horizon symmetries like, I don't know, Carrollian or BMS or whatever. People are studying this in these days recently. So maybe that's the thing. So it should be written, but I'm not writing it because then I will have to ask the question that
in your analysis, it does turn out is as a tensor with V index only, and GI turns out as a tensor with I index only.
Yes.
So I guess, yeah, thanks.
Okay, the last question is by Madhava Hall. Please go ahead with your question. Yeah, I see a raised hand from Madhava Hall.
Am I audible?
Yeah, I can hear you.
Hi, thanks for the talk. So I was wondering, the gauge conditions the boundary conditions you imposed on metric and so on, do they allow, since this formula is supposed to work for non-equilibrium black holes, does it also allow for outgoing radiation from the horizon?
Well, I think if you look at this thing, so this I'm not getting into in this X, but probably it will be R squared times something, which is probably the news or the Bondi mass. I don't remember exactly. So all that information is there in these functions of X, omega I think. It should be an expansion in R square. So
I mean at the near horizon boundary conditions and so on.
It's a near horizon boundary condition. I think
so
should be
Just because you said news, like did you mean some asymptotic statement or?
Yeah. So this is actually this gauge choice is true as asymptotically near horizon.
Okay, I think there are no more questions. So let's thank Nilay for a very nice talk. And we move on to the next talk by Vijay Balakrishna Shenoy.
Nilay, please unshare.
Yeah,
Yes.
please. Yeah.
Sorry.
Thanks.
Okay, so Vijay is going to tell about fractals from fields to paper and trees. Okay, so Vijay, please. Yeah.
Can you hear me?
I'll remind you after 5 minutes. Sorry,
Yeah, you can hear me, right?
Yeah, I can.
Yeah. Okay, so first of all, I want to thank the organizers for inviting me. I'm actually a condensed matter person, and this is a completely new set of people to talk to. And it's been fantastic listening to all the talks. So thank you for that opportunity as well. So the work I'm going to talk about is done in collaboration with Roderick Mosner and a wonderful undergraduate student at IIC who has now moved to Caltech, and I've been generously supported by DST. Okay, so my talk has roughly 4 parts, if you like. The first part, I'll give you a big picture. This is to sort of, since I'm talking to a different community, I want to give you a big picture of what are the kind of contemporary problems in quantum condensed matter physics that people are thinking about and where fractons fit in that. And then I have 3 different stories to tell, and the talk will have a certain different flavor than the kinds of talks I've heard. I will not get into any sort of detail on anything. I'll just try to sort of lay out some general ideas of the field and sort of give you 3 examples of things that I have myself been involved in. Okay, so this is the sort of flavor of the talk. It's more of a catalog of results and not a detailed description of them or detailed discussion of them. So the first thing is, what are these fractons and where do they fit into the bigger picture? So to see this, I think I should move this somewhere else, maybe. Yeah, okay. To see where they fit into the bigger question, let's just see what is a big question in condensed matter. So you start with some UV scale, you define some set of degrees of freedom on that scale, probably which implements some symmetry or the other. And then you ask, you put some interactions between them. And the way we think about it in condensed matter is that there is a space of Hamiltonians that you have. And you sort of move in the space of Hamiltonians and you can ask what kind of different distinct phases you can get. And the influential idea in this field has been from Landau. And the main idea there is symmetry. And this had really influenced a lot of thinking in condensed matter physics until about 1980 or so, when the quantum Hall effect was discovered. And even then, you see much of what we learn in condensed matter physics was, at least starting with electrons, is summarized by these 4 states I've listed here. I won't go through them in detail. And the question then is, are these the only phases you can get by starting with electrons on some UV scale and they conspire to give you these phases, or are there other phases as well? So this is the question. So I pose the question, but you may wonder why one should bother about this, right? And I think I have a convincing answer to this. And the idea is that if you think about how humans evolved, you will see that every epoch of human evolution was actually controlled by a particular phase of electrons. So, the Stone Age was insulators, and then we found a gapless phase of metals, and then we learned how to make insulators into somewhat metallic, and now we are entering a new phase of, or new epoch, I hope, where we're going to use more exotic phases that are going to be what are called topological and entangled phases, and to produce even more fantastic things, and it could completely change the way we live, right? Okay, so this is the idea. This is what is the motivation for this. So let me just tell you what is the current status of what we understand on this. It's a very, very sketchy slide. I'll just show it anyway. So there are many more quantum phases, even starting with electrons, than what I showed you, the 5. And this is really something that has been discovered in the last 15 years. And the recent realization is that, which was somewhat difficult for condensed matter people, is that two more concepts than what is more than what is just symmetry is necessary. One is entanglement, and this is and the other is topology. And this is difficult because these are not 4-letter words, and we are condensed matter people sort of take the 4-letter words more easily than bigger words. Okay. So what is this idea of entanglement? So entanglement has now taken the the center stage for this, and everything is sort of thought as either short-range entangled phases or long-range entangled phases. And short-range entangled phases are those phases where entanglement is, there can be some interesting entanglement, but it is all short-range, so it has some nice area law, and that's all that is there to it. On the other hand, there are other phases which are what are called topologically ordered phases, and these are long-range entanglement. So the short-range entangled phases, you can also put some extra symmetries, and you must have heard of these things called topological insulators. They are actually short-range entangled. But for the purposes of my talk, I'm actually interested in these long-range entangled phases, and these are what are called topologically ordered, and I'm going to discuss a little bit about them and why they are of interest and so on. So instead of giving you some big formal definition of what a topologically ordered phase is, I'll just give you an example. So the simplest example of a topologically ordered phase is the ground state of the Z2 gauge theory on a square lattice. So what is the Z2 gauge theory on a square lattice? I have the square lattice I've shown here. These are the links of the square lattice, and at every link, I place a qubit or a spin half, a two-state system. And then there is the Pauli operators Z and X. And I have a magnetic field term, if you like. So this is, I go around the plaquette, and so it's all the Z's on the, yes, please.
I think the slide is frozen in the first one itself. I cannot see the next other slides.
Are the slides moving? Sorry?
Oh, it's the slide of key questions, condensed matter physics key questions. That's what we can see.
Oh, okay.
Have you moved forward from it?
Yeah, yes, I have moved forward from it.
No, nothing's moved here. You might unshare and share again, perhaps.
Okay, sorry about this. Yeah, can you see this now?
Yes. Why bother?
Yeah.
Yeah.
Can you just try going forward and back once?
Yeah. How about now?
Yes, phases current status.
Yeah. So this entanglement idea has been seen by everyone, right?
I'm seeing this slide for the first time.
Okay, so I'll just quickly go through this. So the idea is that, the main point, that is the main player here is entanglement. And so there are short-range entangled phases and long-range entangled phases. And, the so-called topological insulators, which are very popular these days, they fall in the category of short-range entangled phases. And you have long-range entangled phases, which are the topologically ordered phases. And they are actually useful for quantum computation as quantum memories. Okay, so this is what I'm showing you. I hope you can see that I'm showing you the toric code on the slide with the toric code here. Is that visible now?
Yeah, it is visible.
Yeah. So what is the toric code? It's just a version of Z2 gauge theory. So it's basically, I have a square lattice and I have spins sitting on the links of the square lattice, and there's a magnetic field term and something like an electric field term. Let's not get into the details. And the idea here is that the ground state of this is fourfold degenerate on a torus, right? And the degeneracy is not protected by any symmetry, or it is not coming from any symmetry. In fact, if I put the same kind of theory in a completely arbitrary random lattice like this, some Poissonian random lattice like this, you will see that it has exactly the fourfold degeneracy as you get from a square lattice. And so the idea is that this degeneracy is not protected by a symmetry, but comes from some kind of entanglement structure, some global Wilson lines of this theory. And the values of those Wilson lines fix, there are 4 distinct possibilities for those Wilson lines, and that's what actually gets you the degeneracy. And so the idea now is to use these degenerate states as your qubit. And that is then, they are then protected from decoherence and so on. And this is how it can act as a quantum memory. But this is, you'll realize that this is not such a good quantum memory if you are at finite temperatures. And the reason for that is the following. There are these excitations of this gauge theory, and those are the monopoles. You can actually change the plaquette value in each one of them. And, thermally, you can excite a pair of plaquettes. And once these plaquettes are excited, as I've shown here, these plaquettes can move freely around, by single spin flip operations, and they can be thermally flipped, and they can just move around, and they gain entropy, and then the topological order just breaks down. So this is the problem. So if you want to make the system robust, you have to make it large, and if you make it large, you lose out on entropy at finite temperatures, and the toric code is no longer a good quantum memory. So people have thought about trying to fix this problem in some way or the other. And one way people considered doing this was to go for some different types of qubit arrangements. And I'm going to introduce a model which turns out to have deep connection to fracton physics. And this model is called the X-cube model, and is sort of the poster child of fracton physics now. So what is this model? You take a cubic lattice in 3 dimensions. So I'm now in 3 spatial dimensions, and there is a cubic lattice. And the magnetic term now is somewhat different than what we had in the toric code. So what I have is, I take a cube, it has 12 spins that are on its links. And the magnetic term is like a volume term. It's a product of all these 12 spins. So that's what I've written as B cube here. And now there is something like a some charge operator here, and they're vectors. So I have this these 4 spins here. They take product, and it has a normal x direction. So it's called AX, and so on. And so this is also some kind of gauge theory, but it has a very interesting property. The interesting property here is that the ground state of this has a sub-extensive ground state degeneracy. And so if I put this on a 3 torus with nx, ny, nz sides, the lengths of the sides, then you see that the ground state degeneracy is this massive number. Okay, and again, this is a very interesting degeneracy, in that this degeneracy also depends on what kind of lattice you have. In the sense that if it were not a cubic lattice, but some other lattice, then the degeneracy changes. It is still sub-extensive, but these factors will be different. And so people have now come up with notions of what is called as geometric order, or something called as foliated fracton order, and so on. There's one more point I wanted to just briefly mention here, because it will become useful for me later. And that is that you will see that these theories have certain dual descriptions, and dual description will be some kind of Ising models. And those Ising models will have subsystem symmetries. What do we mean by that? You could actually flip a subsystem of spins, not the full or not local, but a subsystem like a plane of spins or something. And the theory will be invariant to that. Okay. So you may ask, what has this to do with fractons? So what you will find is the excitations of this. So for example, is I can go to a cube and try to change its the value of b there. I could make b equals -1. And what you will see is that you cannot move these things by single spin flips. So let me just quickly demonstrate that for you. So you can see that this is the standard the toric code that I showed you. So I go to the and you see I can move these plaquettes by single spin flips, right? Very easily I can do that. But if I come here and I flip one of these spins, you see I create these 4 the 4 cubes which have negative b. So I try to move this by flipping a single spin. And now you see that I cannot be in the same energy manifold, because I've created 2 extra cubes. And this means that I cannot move a single cube without creating other excitations, or in other words, a single cube is immobile. Interestingly, a dipole of these can be moved, as you can see. Right? So a dipole of these can be moved. So single charges cannot be moved, but dipoles can be moved. And this means that the charges of this theory have fractional mobility, and this is why people call them fractals. Okay, so there's a whole set of things that have gone on in this field for the last 3, 4, 5 years, maybe 5 years, and you can look at some of these review articles for inspiration, or if you like, if you want to explore further. So what I'm going to try and tell you is how to construct some phenomenological theories that can have fracton-like excitations. Okay, so this is what I'll do first, and maybe since I'm kind of running short of time, I'll run through this fairly fast. And let me just give you an idea. The big picture is the following: that what we want to do is we want to write some kind of gauge theory, and the gauge theory has higher rank tensors as electric and magnetic fields. So this is the crudest idea here. So imagine that I had a gauge theory where the electric field tensor was a second rank symmetric tensor. And I impose a Gauss law, which says that two divergences of this on these two indices is the charge. I just say this. And now you will find that I have a conserved charge and a conserved dipole moment. So what does this mean? So if the dipole moment is conserved, and I have an isolated charge, I cannot move that charge because motion of the charge will violate the conservation of dipole moment. Which means if I conserve the dipole moment, I will make the charge a fracton, which means the charge cannot move. Okay. And this is the idea. And so the charge current itself will be the divergence of some kind of dipole current and leading to a continuity equation, which is of this form I'm showing here. So you can actually make this formal by writing a gauge theory and so on. So I will actually show a more general version of this in a minute. And this theory will have a gapless photon. And so we can ask a more general question. Can we have a theory where I have order n fractons? And what do I mean by order n fractons? I have fractons whose 2 to n multiples cannot move. And not only they are point objects, they can be extended objects. And they can be in arbitrary dimension. And so this is something we worked out a couple of years back. And the mathematical structure that we need for this, at least one possible way of doing this, is you need to have certain kind of tensors. So there are symmetric tensors, anti-symmetric tensors. You can have derivations. You can have these exterior derivatives. You can have divergences. This is just notation. And so the main mathematical structure we need here is something called as Kn tensors. So what are Kn tensors? They are symmetric tensors of anti-symmetric forms. Or symmetric tensors of K forms, right? So that's what I've written here in some symbolic way. And these are the objects that will enter the theory as gauge fields and so on. And I have used some notation here to derive, to describe what kind of mathematical operations we can do on them. But the big picture is the following. Our scalar potential of the Maxwell theory will become a k-1 n tensor, and the vector potential will become a kn tensor. And the charges will have the same kind of structure. So this is the charge, and this is the current. And you can define electric fields which are of this kind. I've just written this down in this way. And you have magnetic fields written in this way. And in this way of doing things, the electric field will be a kn tensor, and the magnetic field will be a k+1 n tensor. You can write a Lagrangian density in this fashion, and you can define a gauge transformation. And the invariance of the Lagrangian to this gauge transformation will force a continuity equation of this kind, which will give us that the theory has fractonic excitations up to order n. That means the 2 to the n multiples of this cannot move freely. And they are also k-1 dimensional extended charges. So there is a more general version of this. I'm not showing any details of this. You can actually have photons which disperse here as q to the n. You can construct theories with different kind of photon dispersions. Omega goes as q to the z, where z can be anything from 1 to the n. You can look at our paper for the details here. And just to make a comment to connect with the community that I'm talking to, if you look at this 2-1 z is equal to 1 theory, this is the non-fractonic theory of line charges, which is this Carl-Brunman theory. And also there is a more generalized version of K1 theory, which is the theory of extended objects, the Maxwell theory of extended objects. So this is a bit formal, and you can ask whether these things have anything to do with reality. And the answer is yes. And the idea is that this 1-2 z is equal to 1 theory can be shown to be actually dual to an elastic solid in 2 dimensions. And what are the charges of this theory? The charges of this theory are disclinations of the elastic solid. And the dipoles of this theory are the bound states of, or the dipoles of disclinations are dislocations of theory. And so this picture has now, it allows us to revisit some of the ideas that of the crystal elasticity and so on that we have looked at in 2 dimensions, and the Kosterlitz-Thouless transition in 2 dimensions. Okay. So in the remainder of the time, I don't know how much I will be able to do, because I think I'm kind of running short of time. So I'll just show you something very interesting. And so the idea is, I'll show you that fractons are much closer to us than we think. And if you just look at the sheet of paper that I'm holding, you can see fractons in there. I'll show you. So I'll ask you to indulge me in finding a piece of paper close to you, and just ask yourself, if I draw an arbitrary line on this piece of paper, and ask yourself, can you fold this paper smoothly along this line? And the answer is no, because if you try to draw an arbitrary curve on this and try to fold the paper along that, you will see that it will produce other small micro folds and so on. On the other hand, if you try to fold the paper along a straight line, it folds very nicely, right? And so on. So bottom line of this is that the fact that the paper can be folded only along a straight line is actually related to fractonic physics. And I'll just show you that in the next few minutes. Okay, so let me start by discussing some things here. So if I want to discuss the elasticity of a three-dimensional solid, like solids in our world, then you have a displacement field, a strain tensor, and elasticity tensor, and these solids have elastic waves, phonons, if you like, which disperse as linearly with momentum, right? Okay, so if you have the fortitude to read Landau-Lifshitz all the way to the end, volume 7, I believe, a theory of elasticity, then you will see that there is a theory that you can write down, which is a somewhat somewhat effective theory when the system is thin meaning that two of its dimensions are much bigger than the other dimension, like a piece of paper that I'm holding. Okay, and this is called the theory of plates. And the main point here is that if I know the displacement of the plate vertical to its mid-plane, then I know everything about this. Okay, and I won't get into the details. I'll just show you what the Lagrangian is. The Lagrangian has a kinematic parameter that enters it, which is the curvature, two derivatives of this displacement, and you can write the potential energy corresponding to that. And then there's the kinetic energy of the motion of the plate perpendicular to the plate. So that is the kinematic piece. Okay, the kinetic energy, I mean. So this is the Lagrangian, and you will see that this theory has waves which disperse as k square, not k. All right. Now what I'm going to do is I'm going to introduce defects in this theory. So what are the kind of defects I can introduce? So I can have, W is my displacement field, so it has to have something to do with some badness of W. So one thing I can do is I can have what is called as a tear defect. So W becomes double valued. So as I'm showing you here. Or you can have, because it's the curvature, second derivative of W that enters the Lagrangian, you can have slope discontinuities of W, as I have shown here. So it's called a fold defect. And so what we can do is we can write down what are the fold defects and the so-called the tear defect and the fold defect. And the most important thing you should note here is that the fold defect is characterized by a vector quantity. And what is this vector quantity? It is the vector quantity is the jump in the slope as you traverse, as is the holonomy of the derivative, right? So it is a jump in the slope. And now what I can do is I can construct a theory in which this W field has both the smooth elastic displacements as well as the defect displacement. So this is my theory of defected plates. Okay, so this field W has now both the smooth and the defected. Okay, so I've introduced the theory of plates, and I'm going to keep this aside for a minute. And I'm going to discuss a different kind of gauge theory, which has been studied recently quite a bit. And this gauge theory is a gauge theory with vector charges. So what is this gauge theory? So I have a scalar potential, which is a vector. It's kind of a strange thing to say, but okay. So that is the vector. And my vector potential is a second rank symmetric tensor. Okay, so this is A alpha beta. And how do I define my electric and magnetic fields? So this electric field is defined in this fashion. It's like a strain corresponding to this, symmetric part of the gradient corresponding to this phi alpha. And then there's the usual time derivative with respect to A. And then there is a number, which is the magnetic field, which is, two derivatives of two curls of this symmetric tensor. And this is my Lagrangian density written in the fairly usual way. And I can now see what kind of gauge transformation leaves this invariant. And the gauge transformation that leaves this invariant is this particular expressions that I have written. Okay, so what will gauge invariance buy me? It will tell me that there is a continuity equation of this kind. That is, the rate of change of this vector charge density is the divergence of a second rank symmetric current, which certainly means that the total vector charge is conserved. And in addition, you can show that there is something called a moment of a charge that gets conserved. And that's what I've written down here. So what does that mean? That means if I have an isolated charge Q alpha, then that isolated charge can move only along its direction. That means that in the plane, if its vector charge is Q alpha, it can only move along Q alpha. It cannot move in any other direction, because if it moves along any other direction, it will violate this moment conservation condition. And this theory has a set of photons which disperses as k square. Okay, so what I'm going to show you now is the main result. So one can show that the defective plate theory is actually dual to this vector charge gauge theory, right? And the duality will show you, this is the duality table, if you like. So the bending moment will get mapped to the electric field and various other things. So in particular, the vector charges actually get mapped to the tear defects. So this is the main point here. The vector charges are related to the tear defects or the defects which have the jump in the slope. So how do we understand folding now? So if I now take this, the blue line, the blue data shown here corresponds to the plate version of this picture. So you see that here I have a vector charge, I have a jump in slope where the slope along the E2 direction is, is changing. So the duality dictionary will tell me that this corresponds to a vector charge whose vector is along the one direction. So now from the gauge theory side, this Q alpha, this charge can move only along the one direction. And that is exactly what happens when I have a piece of paper and I have a straight fold here, and I can just move this, move this charge along this fold. So this point is a fracton actually, right? And you can move it along that. And that's because, the gauge theory allows only for motion of the charge along that direction. So folding can be understood as motion of a charge along its direction. So now you see you can get more out of this. So you can ask what happens when I tear paper. So you see, if I take this configuration of the plate, so it has now a tear, and if you compute what is the charge associated with this kind of a defect, you will see that that is exactly same as the charge what I showed in the previous slide, with the charge along the x1 direction. But now what is happening is I'm trying to move the charge perpendicular to the x1 direction along the x2 direction, and that's what I'm doing by tearing. And when I do that by tearing, I shed these a dipole of these vector charges, and the dipole of the vector charges you can show is actually a tear defect. So what happens is leaves behind a trail of tear defects, and that is what is the torn piece of paper, which, as you can see, is okay. I've kind of run out of time, so this is the picture. So I just wanted to show you something very exciting that we have been trying, and maybe take your suggestions on how to proceed, and maybe some connections to other things. And so the main point here is the following. I'm going back to the quantum problems, and I'm again coming to this again from the idea of quantum memories and so on, of how to how to use ideas from fractons, etc., to try and get better quantum memories, etc. So this is what one is motivated by. And so the idea is that all the lattice models, etc., that I showed you, they have a continuum limit as a field theory defined on a manifold. For example, the Chern-Simons theory, for example, the toric core that I showed you, you can show has a continuum limit, which is like Chern-Simons theory with some matrix level. It has multiple gauge fields and so on. So I won't get into the details of that, right? And you can then use topological quantum field theories to try and actually classify them. And there's a lot of work on this already. You can look at this beautiful paper here by Zhougang Wen. The question we are asking is, why should we stick to manifolds? Can we go beyond manifolds, right? So can we go on discrete systems which are not, which don't have this long wavelength descriptions as quantum fields defined on a manifold, right? And so if you ask this question very broadly, then of course there are infinite, there are many different ways you can make things non-manifold. So what we want to hold on to is, we want to hold on to some notion of translational symmetry. And this naturally leads to the notion of tree graphs. And this is what I call as arboreal arenas, right? Arenas where you define some qubits, where you place qubits, and which have some notion of translation symmetry. So let me show you what those arboreal arenas are. So you can start with this thing called the Bethe lattice, which is that, I have some graph and it's connected like this, as I've shown. It's a tree, so there are no closed loops in this. So there are notions. So if it is k coordinated, so for example, if I have a site and if there are k links coming to it, then we call it Bethe k. And there is a notion in graph theory also called as hypergraphs. And what is a hypergraph? The link here not only connect to one point or 2 points as shown here, it can connect to multiple number of points. And each site can actually have any number of links connected to them. So for example, Kn means each site has K links coming to it, and each link has N sites attached to it. So this is, for example, beta 2,3, and this is hyper beta 2,3, and this is hyper beta 3,3. And now there is also a notion of a graph Cartesian product. So you can actually define higher dimensional versions of this. Of course, that's a very vague thing to say here. What you mean by this is that if you think of this as one dimensional in some sense, then you can define higher dimensional objects by some notion of something called as Cartesian product. So you can actually create higher dimensional arboreal arenas out of this. And the beautiful thing about this kind of construction is that the notion of what is a plaquette, what is a cube, etc., naturally generalized to arboreal arenas. Okay, so what is the new physics you get out of this? So this is the sort of portfolio of the results that you get here.
Sorry to
yes. Yeah, I'll just finish.
To interrupt you. You have just 2 minutes.
Yeah, I'll just finish in 2 minutes. Yeah. So what happens here is that you can define gauge theories on such things. And what I want to show you is the most exciting thing is that even the simplest Z2 gauge theory on an arboreal arena is fractonic. So their excitations cannot move. Okay, so this is a very interesting result. And this could possibly have applications for quantum memories and so on. I won't get into the details of that. And these are very large degeneracies corresponding to many global Wilson lines. There is a new class of dualities. So for example, the Ising model on a Kn hypertree is dual to the Ising model on the Nk hypertree. And there is also a beautiful classification of topological orders. Okay, so this is the sort of main summary of results. So I'll just quickly show you some of the main results here. So you can define what are called these generalized quantum Ising models and generalized gauge theories. So they have confined phases and deconfined phases. We can map them out. You can also do this for X-cube model. X-cube model, all its excitations are completely frozen. They cannot move at all. There is a big ground state degeneracy. And you have these fantastic set of dualities. These are, all known dualities of discrete systems. They are special cases of the dualities that we have, like Kramer's Bonnier on various lattices, etc. They are all special cases of the duality we are showing here. And so this is the duality table. So we have a complete set of dualities that we have worked out, and this is the table of that. And here's a very, very beautiful result we are very excited about. So you see, I asked the question, what are the different kinds of topological orders you can have? So let's say that there are different distinct kind of topological orders. They are actually classified by some kind of patterns of entanglement. Let's say whatever they are, and there is some way to classify them. But we do not know how to apply that directly to these arboreal lattices. So how do we do this? So we use a notion of something called as entanglement renormalization. So the idea is that if I can find a quantum circuit which connects one to the other, then I say they're equivalent. And now comes a very beautiful result. You will see that if I take two-dimensional arboreal arenas and define the Z2 gauge theory on them and work in the deconfined side of it, then there are only 3 distinct kind of topological orders, right? Toric code orders. So there is one toric code order on the square lattice kind of stuff, which is what I discussed in the beginning of my talk. Then there is an arboreal arena where one dimension, which is, this is B2. B2 is like a line. So along one direction, it's manifold-like. In the other direction, it's tree-like. There is a toric code order on that. And remember, that's independent of K. So as long as K is greater than 2, that the toric code order on K equal to 3 and K equal to 4 is same. And similarly, there is a distinct toric code order on when K1 and K2 are greater than 2. And similar things go for fracton orders, but now there are 4 distinct types of them. So we have now gotten some handle on how to start thinking about classifying quantum orders on this kind of tree-like structures. Okay, so I've run out of my time. So let me just summarize. I hope I gave you a brief view of what is this fracton world, what is going on here. At least what we are doing here, at least. I told you about 3 things. I told you about some generalized gauge theories. I told you about, I gave you an example of fractons in real life. And I told you our attempts to try and go back to the quantum problem and try to use some of these fracton ideas to look at models which don't have a manifold description at long wavelengths. And we believe that that is quite promising, and it can lead to some interesting possible applications as quantum memories and so on. This is something that we are working on. And I've also put in, I've also listed some directions to go forward. Okay, so let me thank you, and thank you very much for the opportunity to talk. Thank you.
Thank you, Vijay, for a very interesting talk. So I see questions, one from Madhavahal. Please go ahead with your question. No? And there is a question from Somdatta. So if he is available, please ask your question.
Yeah, so the question is, as far as I understood, the fractons are such that the single charges cannot separate from the initial configuration, but dipoles can separate, right?
The version that I showed you, that is the case, yes.
Yeah. So doesn't this look suspiciously similar to what happens for quarks? Because quarks can't separate, but mesons can.
Yeah. But you see, the quarks are in a confined phase. So you can show that this theory is actually deconfined. So it's in the electrical sector, they are deconfined.
No, what I'm saying is, can't this fracton model be modeled in terms of, I mean, can't quark confinement be modeled in terms of some sort of fracton physics?
No, see, the fractonic gauge theory has a confined phase and a deconfined phase. So if you go to the deconfined phase, everything will have, there'll be string, if you go to the confined phase, all charges, everything will have string tension, right? You can't separate any of them, right?
Yeah, that's what happens for quarks, right?
Yeah, but so it's completely confined. But here, if I look at, I showed you the magnetic sector, but if I look at the electrical sector, it is completely deconfined. Hello?
Okay, so I think there is no more questions. So let's thank Vijay again for a very beautiful talk.
Okay, thanks so much. Yeah.
So our next speaker is Professor Nathan Seiberg from the Institute of Advanced Study. So can you please?
Yeah, I'm trying to unshare.
Yeah, sure. Yeah, Professor Seiberg, can you please share?
Can you hear me and see me and see the slides?
Yeah, so he's going to tell us about exotic theories and UV-IR mixing. So please.
Thank you. I hope you can see me, hear me, and see the slides correctly. Can you? Is everything okay?
Yes.
Yes, it's all okay. So thank you for inviting me. It's a great pleasure. Unfortunately, I cannot be there in person. I wish I could. But at least I succeed to see on the side some familiar faces of good friends of a long time. I really enjoyed the previous talk, which gives a nice segue to what I'm going to talk about here. And because I'll mention a little bit fractons, is I was really fascinated by these developments in condensed matter physics. And I felt that they have to fit into the language of high energy physics, which is appropriate, say, for this audience here. And there was a very long pandemic. There still is a very long pandemic. And with a group of fantastic collaborators, Pranay Gorantla is Indian, actually. He was in TIFR. And Odalam and Shuheng Shao, we have been working for the last 2 years or so on these exotic models, trying to understand them in the language of quantum field theory in high energy physics, which is really distinct from the language of condensed matter people. And I found that really an eye-opener and extremely exciting. So as a way of introduction, it will have a little bit of overlap with the previous talk, but my perspective is a little bit different. So there is a law that I've learned when I was at the beginning of graduate school, and long before most of you were born, that whatever you do at short distances doesn't matter very much for the long distance physics. Most of the information about the short distance theory is washed out by the time you are at long distances. This is the reason it's convenient to organize the classification of phases and phase transitions between them in terms of the low energy effective field theory. So the law is that low energy, and I try to be consistent with the colors. This is my infrared or low energy, and this color is the UV or short distances. So the law is that the behavior of every lattice with short range interactions is captured at long distances by standard quantum field theory. So that is very, very useful because the quantum field theories are characterized by a small finite number of parameters, whereas the short distance Lagrangian or short distance Hamiltonian can depend on a very, very large number of parameters. And that's why this description is effective. And indeed, the technical term for it is effective field theory. So for decades, I was convinced this is right, this is always right, until several years ago, some exotic lattice models came out. I first heard about it about the work of Ha. Can you see my pointer? Can you see my pointer?
No, actually.
No.
Can you see the pointer
slide,
now?
But not the, yeah, now we do, yes.
Yeah.
Okay,
Now it
it
is.
started with the work of Ha. And honestly, when I first heard about it, I thought within a year or two, somebody will debug it. This will end up being wrong and I don't have to bother with it. Well, this didn't happen. In fact, this model of fractons became more and more popular. There are more and more models. This is not going to go away. And there's actually an older paper by condensed matter people, by Paramakanti, Balance, and Fisher. I'll talk more about that one. A model that does not have fractals, but in many ways, it has some of the peculiarities of models of fractals, and it's a lot easier to work with. So throughout this talk, I will focus on this model, the XY plaquette model, which actually does not have fractals, but it has some of the features that the previous speaker talked about. And as you will see, it's very close to various models that high energy physicists, especially string theorists, like to study. And in that sense, we can borrow a lot of techniques, and yet it poses some of the challenges that models of fractals do. So to summarize this slide, there is this law that has been dominating physics for nearly a century. It's been very, very effective. And there are some counterexamples that don't fit the law. And we would like to understand what's going on here. So during the pandemic, we have been studying many examples, including known models of fractals. There are many examples in the literature. And we reproduced, using our language, some of the results in the condensed matter literature. But we also found new results about the same models. And we also found new models. But it would be more effective to start with one particular example. And this is these 2+1 dimensional models, my terminology about dimensions, so that I can talk both to condensed matter physicists and high energy physicists. 2+1 dimensions mean 2 space and 1 dimensions. And since 2+1 is 3, this is what in high energy physics called 3 dimensions. So what did Paramakanti, Balance, and Fisher do? They considered the 2-dimensional lattice and wrote a Hamiltonian model. I'll do it in Euclidean space. So in Euclidean space, with the Lagrangian, I have also a lattice in the time direction, and we have an action. We have a phase at each side of the lattice. And in the time direction, we have cosine of delta tau phi. So this is kind of the standard interaction as in the standard XY model. In the standard XY model, in the spatial directions, we look at cosine of the difference of phi between 2 neighboring sides. Whereas here, we go around the plaquette and we take linear combinations of the phi's around plaquettes and we write the cosine. So this model is well defined. We can put it on the computer. If we have a finite lattice, we have a finite number of integrals to perform. The action is bounded from below. Everything is convergent. There is no reason not to analyze it. And this model is interesting for many reasons. One of them is that it has a subsystem symmetry, which I'll refer to as momentum. In the condensed matter literature, this is called charge. In the string terminology, this is called momentum, because you can shift phi, which a priori depends on x, y, and tau. You can shift it by an arbitrary function of x and plus an arbitrary function of y. So you take all the spins, say, in this row, and you can rotate them by a phase, and you can check that this is a symmetry of the action. And we have a separate group element for each horizontal line, and a separate group element for each vertical line in the lattice. So that's why it's called a subsystem symmetry. It's not like a global symmetry that rotates all the spins, but we rotate only the spins along one line. And then we follow the law, and the law tells us, that I mentioned in the previous slide, that at low energies, at long distances, the number of lattice sites is large, and we kind of scale and we look from afar. There is a continuum description. And we just follow our nose and assume, let's assume that phi is smooth. If phi is smooth, we can expand these two cosines, and we find this 2 + 1 dimensional field theory. Unlike the lattice model, this 2-dimensional field theory is free in the sense that it's quadratic in phi. The only subtlety here is that phi is a periodic variable. So phi is identified with phi + 2 pi. So this is very similar to actions that field theories like to study, and it's good to keep in mind the corresponding 1 + 1 dimensional version of it. Where instead of dx dy, we have here only dx squared. This is the compact boson, and there's huge literature about that. So this model seems free. It is free, and it seems straightforward to analyze, but it turns out to be extremely subtle. And I'll point out some of the subtleties in this model. So for the rest of the talk, I'll concern myself with two questions. One, what is the relation between this lattice model and this continuum model? This looks like a straightforward question. The answer turns out that it's not. And the second question, how should we think about such continuum field theories which have this structure of derivatives and have that such a subsystem symmetry? And again, this looks misleadingly simple. In fact, this is quite complicated and so. So these are the two questions which look really easy. The goal of the talk, usually in the talk, you look at a complicated question and you answer it. The goal of this talk is to present simple questions and show you that the answer is actually complicated. So this is the model we should study. And it has a subsystem symmetry. And we can ask, what does it look like in this continuum notation? In the continuum notation, since we have a continuous symmetry, there should be a Noether current. And the Noether procedure tells us how to find the current. So the current satisfies a very interesting conservation equation. d tau j tau is not dx jx plus dy jy, but it's dx dy jxy. So we have double derivative here. As a result, the conserved charges normally are obtained by integrating the temporal component of the current. But here we can integrate either along y or along x. So along x at fixed y or along y at fixed x. And because of this conservation equation, these charges are separately conserved. So this is what the subsystem symmetries look like if we wanted a local characterization of them using local conservation equation. And this action has two such conserved charges. One of them is the one I'll call momentum. This is the current, this is the time component, this is the space component. And the equation of motion of phi shows that it is conserved. If we try to perform this transformation on the action, it shifts phi by a function of x and a function of y. And notice that these functions can be discontinuous. We can shift only at one value of x and not touch what happens at the other value of x. So we already see that this is going to be a little bit subtle, because in this quantum field theory, we should also analyze what happens when the field configurations are discontinuous. This model also has another conserved charge, which is not present on the lattice. So this symmetry started on the lattice, and I presented it on the previous slide. But there's also another conserved charge with another conserved current, this one. And if you just hit this one by d tau and this one by dx dy, you see that the two this current is also conserved. And if this thing reminds you of the 1 + 1 dimensional compact boson, which has a momentum and winding symmetry, it's not a coincidence. This looks a lot like the momentum symmetry, and this looks a lot like the winding symmetry, and hence the name. In the condensed matter terminology, this is called vorticity. And if we know our 1 + 1 dimensional compact boson, and it has momentum symmetry, and we know it has winding symmetry, it begs the question of, is there a self-duality? And in fact, there is. We can perform a duality transformation here and exchange mu and mu0. It exchanges the momentum and the winding symmetries. Again, this is very much as the standard XY model in 1 + 1 dimensions. And this self-duality exists in the continuum, but does not exist on the lattice. So this is a peculiarity of the momentum of the continuum theory, which is not present on the lattice, very much as in the compact boson in 1 + 1 dimensions. So what do we do when we have a field theory? First thing to ask is, what is the spectrum? So we place it on a lattice, so that to make things very concrete and very easy. And then we take the continuum limit. And the continuum limit is taking the lattice spacing to 0. And that's kind of this purple violet color, because it's the UV limit, number of sites to infinity with fixed space, size of space. And we find various states. First, there are plane waves. And so we just substitute the plane wave and we find the energy of the plane wave. And it scales like 1 over the length square. The reason is that the energy is proportional to the momentum in the x direction times the momentum in the y direction. This is because of the structure of the derivatives. So the energy scales like 1 over L square. And comparing with the 1 + 1 dimensional compact boson, the energy there is 1 over L. So we see the energies here are parametrically smaller than for a compact boson. They are of order 1 over the length square rather than 1 over L. There is more density of states at low energies than in the compact boson. The surprise is really with the charged states. The states that are charged under the momentum and winding symmetry. The analysis is completely straightforward. And the surprise is that the energy of the charged states is infinite. The scale is 1 over L as opposed to 1 over L square, but there's a factor of the lattice spacing in the denominator. So as we take the continuum limit, all of them go to infinity. This is to be contrasted with the situation of the compact boson that we are all familiar with, where the energy of the charged states also scales like 1 over L. So in the 1 + 1 dimensional compact boson, both the plane waves and the charge wave and the charged states have energy of order 1 over the length. Both of them are finite, and both of them participate in the low energy conformal field theory. That's not the case here, where the plane waves have finite energy. It scales like 1 over L square, and the charged states have energy of order 1 over L, but another lattice spacing A here. So they are actually infinite in the continuum limit. This is shocking. It's shocking because it means that we have states, all the charged states. So we have some huge symmetry, the subsystem symmetry, and we have some charged states, and all the charged states have infinite energy, finite energy on the lattice, but it becomes infinite in the continuum limit. So the charged states are present in the Hilbert space of the lattice theory, but not in the Hilbert space of the continuum theory. What this thing means is that operators that violate the subsystem symmetry, like the exponential, this is very similar to what we have in the 1 + 1 dimensional compact boson. Such operators are infinitely irrelevant in the continuum theory. So such operators exist on the lattice, but they are infinitely irrelevant in the continuum limit. In the language of the renormalization group, such operators are known as redundant operators. These operators have correlation length, which is of the length of the lattice spacing, not of the length of the continuum limit. As a consequence of that, the low energy theory is robust against symmetry violating deformations. We can turn on e to the I5 in the continuum limit, and the low energy theory doesn't change. As a result of that, there's also no BKT transition. Let me give another manifestation of this result. We discussed the plane waves and the charged states. The plane waves have energy of order 1 over L square. This is finite in the continuum limit, and we can write it in terms of the lattice parameters, the number of sites square times the lattice spacing square. And the charged states have 1 over LA. So this is infinite in the continuum limit. And in terms of the lattice parameters, it also has the 1 over A squared, the same A square as in the plane waves, but only one factor of L in the denominator. We are interested in the limit L going to infinity, namely the number of sites in the lattice goes to infinity. And we can take this limit 2 different ways. Option 1, we take what we described, the continuum limit. We take the lattice spacing going to 0 with fixed size of the box. So we put the system in a box, and we take the limit such that the lattice becomes finer and finer. There are more and more points in the lattice, holding the size of the box fixed, so that we should get some field theory, or whatever we get, in finite volume. This limit kept the plane waves and pushed all the starch states to infinity. After we have done that, we can also take the size of the box to infinity. We can also take the limit in the opposite order, which we can call the thermodynamic limit. We take still a number of sites to infinity, holding the lattice spacing fixed. But if we do that, if the lattice spacing is fixed, then the size of the box goes to infinity. So what we do is not make the lattice finer and finer, but instead we make the lattice bigger and bigger. As we take this limit, all these states come crashing down to low energy. And later, if we want, we can take A to 0. So the spectrum in these two ways of taking the limits, first A to 0, or first little l to infinity, the spectrum is not the same. So taking the continuum limit and taking the thermodynamic limit, these two limits do not commute. This is clearly a UVIR mixing, and I'll say more about that later. The main point here is that the way we take so everything on the lattice makes sense. We have a finite lattice spacing. Everything is nice and finite. And now we start taking limits. And normally in field theory, the continuum limit and the thermodynamic limit commute. In fact, the preferred way for a field theorist is to say, first we take the lattice spacing to 0, holding the size of the box fixed. And then we take the size of the box to infinity. And it doesn't matter in which order we do that. Here, there's actually a difference, and this is the hallmark of the UVIR mixing. And this is really the source of the problem in formulating a quantum field theory for these exotic lattice systems. We can get the same insight and understand it even better if we study correlation functions. So this is, again, a very meaningful thing to do. We can do it on the lattice, or we can do it in the continuum. And we can do it on the lattice, get final answers, and then start taking limits and see what we find. So we have studied many correlation functions. For example, we can study the two-point function of derivative of phi with respect to tau, or two-point functions of exponentials. We also studied various four-point functions. And once we have a correlation function on the lattice, we formulate it such that the whole thing is solvable already on the lattice. It's not the version that I presented, but there's another version of the system where everything is solvable on the lattice. So we take these closed form expressions, they're closed form but complicated, and then we take two different limits. The number of sites going to infinity, and we can do that together with the lattice spacing going to 0 with fixed volume, or in terms of positions of operators, these x and y, we hold them fixed in space. So for example, if we look at this correlation function, or at this one, we hold the number of sites in tau keeps growing, such that the total time length remains fixed. Or here we separate in x and y, with x and y are not positions on the lattice, but they are positions in space. This is the distance between the points, and we make the lattice finer and finer in between. And then we can take the infinite volume. Alternatively, we can hold the lattice spacing fixed, take the number of sites to infinity, and then the operators are at fixed positions on the lattice. And then later, if we want to do that, we can take the lattice spacing to 0, which means that the operators are separated more and more in terms of lattice spacing. And to give you a spoiler, again, these two limits will not commute. This correlation function in taking the two different limits do not commute, again, signaling the UVIR mixing. Let me give you a demonstration of that in this two-point function. If we take the continuum limit and infinite volume of this two-point function, we do it on the lattice, we take the limit, and we get a closed form expression which simplifies in various limits. Tau much less than x times y, we get some power behavior. So that's not very shocking. That's what we would expect in any field theory. If we set tau is very small compared to the distance, we can set it here to 0. And as the two operators separate from each other, the correlation function decays like a power. A more interesting limit is tau much bigger than x times y. So we get a prefactor, which is a power. That again follows from general scaling. But there is an interesting factor here of the log of tau over xy. Now, for generic x and y, this is the answer. It's finite. We can take the limit in any way we want. Everything is fine. But the singularity here is xy equals 0. See, here I cannot discuss the singularity as x times y equals 0 because I assume the tau is much less than x times y. But here tau is much bigger than x times y. So I can ask what happens at xy equals 0. This is very surprising because what we see here is two operators at different Euclidean times, so they are not at the same point in space-time. I can even keep their x different, but they have the same y. So I have two operators at different times, at different x, but they happen to be at the same y. And the correlation function diverges. So the correlation function diverges at the place where there is nothing there. So I just looking at the 2-point function and I move 1 point relative to the other, and all of a sudden it diverges. Is this a UV divergence or is it an IR divergence? That's very confusing. And the way to answer that is that we go back to the lattice and we take the limit more carefully. So if we look at the lattice, the divergence is absent. And the divergence appears either as so if we hold, send A to 0, we keep the finite size of the box fixed, the divergence is absent. Or the other way around, we send A to 0, but we work in finite volume, again, the divergence is absent. So this divergence here arises either from the UV or from the IR. And there's no way to tell whether it comes from the IR or the UV. Again, we interpret it as a UV-IR mixing. And that can be understood in a lot of detail, and I don't have time to do that here. So we see that from the correlation function, this correlation function, we also see this UV-IR mixing. The more interesting correlation function is a 2-point function of the exponential. Recall that, so let's go back. The analogous calculation in the 1 + 1 dimensional compact boson, this is the propagator. This is d by dz phi with d by dz phi, which is 1 over z squared. So that's kind of similar to this power behavior here. The log is peculiar to this system, which makes this system more interesting. This is the analog of the 2-point function of e to the I phi with e to the minus I phi. Because of the subsystem symmetry, the two operators have to be at the same position. Otherwise, this correlation function violates the subsystem symmetry. But we can have them at separate times. So this calculation can be done, and it decays exponentially with tau over the length of the systems times little a. So if I take the continuum limit, it goes to 0. Or if you wish, the correlation length or the correlation length between these two operators is of the order of 1 over the lattice space. That is of the order of the lattice spacing. So in the continuum limit, these two operators vanish. They are redundant operator. And this is consistent with what I said earlier, because I said that the states that come between them are these charged states, and they have energy which diverge in the continuum limit. We can also see it from here, because the exponential suppression is the time difference between the two operators, times the energy of the lowest lying state, and the lowest lying state has energy 1 over LA, which diverges in the continuum limit. We can also study the same correlation function in the other limit. L goes to infinity with finite A. In fact, this was computed already in the paper of Paramakanti, Balance, and Fisher, except that we did it using a different formalism. And we reproduced their answer. So this is the 2-point function in the other limit. And it's again very strange. In the compact boson case, we have a power of tau here, and the power of tau appears as e to the minus a log. Here instead, we have e to the minus log square. This means that this 2-point function decays faster than any power of tau, again signaling that these operators are very strange. Another peculiarity here is that the A dependence in the correlation function cannot be absorbed in wave function renormalization of phi. Normally, such A dependence on the cutoff is absorbed in redefining the operator such that the correlation function becomes finite in the limit. Here, we cannot do that. So all these facts mean that as we try to define the continuum limit or the thermodynamics limit or whatever this operator vanishes in the low energy theory. It is a redundant operator. I'm approaching the end of my time, so let me summarize what we have seen. I started the talk by summarizing the lore. The low energy of any lattice system with local interactions is expected to be captured by a continuum quantum field theory. And this lore has been dominating condensed matter physics and was very influential also in the context of high energy physics for decades. But various exotic lattice models challenge this expectation. And these models have several characteristics. Most of them I did not discuss, but fortunately, we just heard a beautiful talk discussing these elements. And the elements are subsystem global symmetry. I did discuss that, but it also appeared in the previous talk. As a result of that, we have some discontinuities and even singular observables in the continuum limit. I did not have time to discuss it here. There's large ground state degeneracy. This was mentioned in the previous talk. And defect with restricted mobility. This was also mentioned in the previous talk. And if you go deeply into the various models, you can see how all these facts are intimately related to each other. They're not kind of logically, they're not independent of each other. In the example I discussed here in detail, we don't have many of these features, but we do have the subsystem global symmetry. And the existence of the subsystem global symmetry led eventually to all these subtleties of states with the infinite energy that contribute, and UVIR mixing and so forth. So this brings me to this UVIR mixing, which my understanding is that this is the most peculiar thing about all these exotic models. That the long distance physics is very sensitive to phenomena at very short distances. Most of the information in the short distance theory is washed out by the time we take normally is washed out by the time we take the continuum limit, but this is not the case here. And the long distance behavior is very sensitive to some short distance details. And this is a bit reminiscent of UVIR mixing, which is common in various string constructions. And in this audience, I think people will be easier for the audience to relate to these. The little string theory exhibits one kind of UVIR mixing because it has T-duality, the local operators do not exist, and so forth. And also ordinary field theory on the non-commutative space also exhibits UVIR mixing, where there are infrared singularities, which started their lives as ultraviolet singularities. So the ultraviolet behavior of the model translates into infrared singularities. And the physics of these UVIR mixing in non-commutative spaces is actually not unlike the kind of singularities, the kind of UVIR mixing that we see here. The origin of the UVIR mixing in theories of non-commutative space is that these theories, although it's not obvious from the original formulation, are described dipoles. As we make the dipole more and more energetic, it actually grows in space. And since if it has more momentum in the x direction, it becomes bigger in the y direction. And therefore, the UV singularity in the x direction translates into an IR singularity in the y direction, which is a bit similar to what we saw in this talk. Also, it's similar to what we have here because of the appearance of dipoles. So these are all these exotic models. And there are various peculiar quantum field theories that capture these facts. I discussed one of them in this talk, but during the last 2 years, we wrote many papers, the same group of authors with Pranay, Hota, Shuhen, and Shuhen. And they involve very peculiar field theories, which we analyze in detail. And the peculiarity of them is that they involve discontinuous fields. But perhaps the most exciting thing about that is that there are many, many interesting puzzles that I don't know the answer to. And that's why this field is exciting. Thank you.
Thank you, Professor Saiba, for a very nice talk. So now I invite people for a question. I see Sunil has a question. Please go ahead.
Yeah, that was a beautiful talk.
Yeah, Sunil.
Thank you very much.
Thank you, Sunil, and it's good to see you, and I'm looking forward to seeing you again soon.
Yeah, me too. So I had a naive question. You had some parameters in your original Lagrangian, some mu and mu naught, and you said there's some exchange duality. But then somehow this, in the 1+1 compact boson, there's actually a duality which has a fixed point where we get an enhanced symmetry. So is there any special point in the parameter space of these models where anything new happens?
I doubt it, because these two models, you see, in the 1+1 dimensional boson, the parameter, say the radius, is a dimensionless parameter, and it's an exactly marginal deformation. And the spectrum of the theory depends on the value of this dimensionless parameter.
So here it doesn't.
Here, mu and mu0 are dimension full.
Mm-hmm.
And in fact, there's a scaling symmetry that allows me to set them both to be 1 GeV or 1 kilogram.
Okay.
So there's no spectral point. And indeed, if you compare with the compact boson, the plane waves don't do anything exciting. All the excitement there comes from the charged states. Right? The charged states have energy R and 1 over R. The plane waves have energy of 4 over 1.
Mm-hmm.
Now, the analog of that here is that the plane waves are the plane waves here with their peculiarities, and all the charged states are gone. All the momentum states and the winding states are not present in the continuum theory. They exist on the lattice, but not in the continuum theory.
I see.
Just to kind of to show you the interest, to show you it's more interesting, in some other versions of this model, the charge states are present. And there your question is meaningful. And then the situation is subtle for other reasons.
I see. Thank you.
Shiraj has a question. So please go ahead, Shiraj.
I know you. I know you.
Thanks for the spectacular talk. It's a very vague question, but in the non-commutative theories, you could. There was this interesting star product whose structure exhibited this UV-IR kind of mixing. I was wondering whether there's any sense in which there is an interesting product in some of these theories, perhaps through some operator algebra or something like that. Sorry for the
it's a fantastic question. I do not know a satisfactory answer, and that's the quick answer is that I do not know the satisfactory answer. But there's a deeper answer that I would like to give, and that is that these theories have this subsystem symmetry. Some versions of it do not have the full subsystem symmetry, but have only a dipole symmetry. These are the kind of symmetries that figured in the previous talk. So there I can easily write a Lagrangian for them. Here I have dx dy phi 180 square. There I have di dj phi 180 square. So I have both the x square and the y square and the x dy. So I have more terms in the Lagrangian. And since I have more terms, I have less symmetry. But still there's an enhanced symmetry compared with the regular one. This enhanced symmetry is what's special. In the case of the non-commutative geometry with the star product, there is no special global symmetry associated with it. So my view on this subject is that, again, it's because of my upbringing and my background in field theory, is that I always go after the symmetry. Once confused, this is one of my mottos, once confused, you go after the symmetry. And these systems have indeed very peculiar symmetry. That's not the case in the non-commutative geometry case. So this is not a satisfactory answer, but I doubt there is an interesting star product here. Another way of saying it is that you can analyze higher dimension operators. You ask, what else can we add to this system? Can it change the story here? And in the case of non-commutative geometry, it's very important that you have the whole power of higher derivatives in order to have the star product. That's not the case here. Here we just keep the lowest order terms and the higher order terms are irrelevant. So this story is also, so recall in your paper on non-commutative geometry, the higher derivative terms, kind of terms with 4 derivatives, you expand it in derivatives, all of them are crucial in order to tame the UV divergences. The UV divergences are tamed by an exponential of a derivative, not by having just a finite number of derivatives. Here, the whole structure comes from just a finite number of derivatives. But I gave a long answer because I don't know the answer. Usually, if I know the answer, it's short.
Thanks a lot.
Vijay has a question. Please go ahead.
Thank you, Professor Saiber, for a very nice talk. I had a question regarding the RG of your theory. So if I just do a simple, probably naive RG, I will get a second derivative term at the first one loop, right? I mean, because I have this dx dy phi, dx dy phi, dx dy phi. So I can actually have two higher momenta ones which will give me a first derivative. Is it possible?
No.
That is, I'll get.
No, you don't get, if you start computing. So first of all, this theory as it stands is free. So the renormalization group is trivial. The theory is actually scale invariant.
Yeah.
So this continuum theory is scale invariant and is not changed under renormalization group. So I could rephrase your question about doing it on the lattice. Imagine
yes, with the cosine. With the cosine, yes.
Okay, if you do it with a cosine, you could ask. Then it's different. So I can give you several different answers. First, if you go all the way to the infrared and you found the continuum theory I described here, and you fine-tune whatever you need to fine-tune, then you could ask, how do we check whether it's robust or not? We try to deform the low energy theory. So whatever deformation we have at short distances translates to something at long distances. So we should check what are the different operators in the long distance theory. This will check the neighborhood. I don't know how to do it in general, but we can do it when the deformation is infinitesimal. And under infinitesimal deformations, these operators that you mentioned are not generated. In fact, these operators that you mentioned violate the symmetry of the model. So if we formulate this model while preserving the subsystem symmetry, the operators you mentioned violate the subsystem symmetry, so they're not going to be generated. I'm making a stronger claim here that even if you violate the subsystem symmetry, all the operators that violate it are irrelevant at long distances. In fact, they are infinitely irrelevant. That's why there is no BKT transition in this model. They exist in the cosine model, but not in the continuum model. So I don't even need to impose the subsystem symmetry. I can just go to I impose whatever I need to impose, find this infrared behavior, and then I explore its vicinity. And the vicinity is clearly unchanged by operators, as you mentioned, because these operators violate the symmetry. And I make seconds more than that. Even if you violate the symmetry, it's still stable. Perhaps by a small amount. I'm not guaranteeing the size of the stability region, but they are robust in that region.
Yeah. Thanks so much.
Thank you also for your talk.
Thank you so much. Yeah.
Quite beautiful.
Okay, one last question by TIFR.
Hello, Nati. Thanks for a fantastic
talk. Hi, thank you.
So
I don't see you.
Oh, I don't know. The camera should be on. I don't know why.
Oh, now I see you. You're far from the camera. You're outside the frame. Yeah.
Oh, okay.
Good to see you.
Yeah, so it's a two-part question. You wrote down this continuum description for a particular way of taking the continuum limit, where you take the small L fixed and then take the lattice spacing to be small, making it finer and finer. And also there was, I mean, one could do it another way where one would take thermodynamic limit. So would there be a separate kind of a continuum description for that limit? And I guess the second part is that, you know, this UV-IR mixing, which one could see from the non-commutativity of these two limits, whether that can be diagnosed purely from the continuum point of view.
Yes. So the answer let me answer both questions. Question number one was, the field theory that I described fits nicely with what I call the continuum limit. Namely, the lattice, this volume of space is fixed, size of space is fixed, and we make the lattice finer and finer. That's usually what high energy physicists call the continuum limit. When people do, say, simulations of QCD, that's what they do. They define QCD in finite volume by making the lattice spacing finer and finer, because there's a continuum field theory in finite volume. This is the Lagrange that I described. You could ask, what about the other limit? So first of all, you can take whatever limit you want. There's a lattice model. You can take whatever limit you want. You either get something interesting or not. Usually when you take continuum limit, you take whatever you do with the lattice spacing, and then you perhaps tune some coupling constant to a critical point, and you have to do it at a particular rate such that you get something interesting. What happens in this case is that if you try to take the other limit and you try to see what you find, and try to find some effective description of the low-lying modes, it is very singular. So in the other limit, the spectrum, for instance, there's a lot more states at low energy because all the charge states also come crashing down. The theory that I presented here is scale invariant. In the other limit, even the results are not scale invariant. So the other limit is a very singular limit. And the literature is full of people who analyze the other limits. And they didn't know that there are these two different limits, but what they did was effectively to study the other limit, and it was very, very confusing. So my take on that is that there is a limit that gives you a continuum field theory in finite volume, and that's what we should be studying. There are various other limits which are more singular, and if you want, you can study them. Then you had another question which was also interesting. Can you remind me what it was?
Yeah, is there a way to diagnose UVIR mixing directly from the continuum point of view?
Yeah, so it actually, everything comes just from the continuum point of view. Where can I go back? Okay. So here is, for example, so this is a continuum computation. You look at this Lagrangian, there's a Green's function. You can compute this two-point function using the Green's function. That's what you find. Everything is nice and finite. And then you ask yourself, what is the meaning of the singularity here? Why is there a singularity when two operators are not at the same time and not at the same y, but they're simply at the same x? Yet the two-point function diverges. And you can see that you regularize it, and actually it doesn't matter how you regularize. You can think of it either as a UV mixing or as an IR mixing. So you can ask yourself, where did this come from? And it came from the fact that the energy of the plane wave is P of x times P of y. So you can have states with very low energy with arbitrarily large Px, provided Py is sufficiently small. And you can have states with low energies with arbitrarily large Py, provided Px is small. And you can cut off this divergence either by making Px not grow too much, or making Px not go too small. So you can regularize, it's either in the UV or in the IR, still keeping the energy finite. So what does this thing mean? Finite tau probes finite energy. You see that if I hold y fixed and send x to 0, it probes large Px. And the theory has low energy states with finite Py with arbitrarily large Px, provided Py is small. And that's what gives this divergence here. That kinematics is a bit similar to the kinematics in the non-commutative space. With the x and y kind of act in opposite ways.
Yes, thank you.
Somdatta has a question, so that will be the last question. Somdatta, please.
I was just wondering whether you can couple the scalars to gauge fields, and you can have a theory of scalars and gauge fields where you can have higher dimensional operators with phi sandwiching, with 2 phi sandwiching 4 Ds and make it a gauge invariant operator, such that when you analyze the theory, you have a similar theory to what you had with the kinetic term, the usual F mu nu, and the higher order term supplying that sort of terms that you were considering. And I was just wondering whether these sorts of theories can be analyzed in order to get the sort of fracton behavior that the previous talk was considering, and kind of get the sort of behavior of having a single charge not separating from the body and 2 charges separating from the body in order to give something like confinement.
Okay, so let's first get confinement out of the way. There was a question about that. the phenomenon of fractons has nothing to do with confinement, just as the previous speaker mentioned. Another way of saying it is if we put probe particles in a confining theory, the energy of the state grows linearly in the distance between the two probe particles. Where in the case of fractons, the energy is independent of the separation between the particles. So first of all, we get confinement out of the story. I presented now to your other question. I presented here one model which has only a free scalar field. No interactions, no gauge field, is the baby version of everything. This is kind of the starting point. It's like when you start learning quantum field theory, you start from a free scalar field. This is the first example you study. Now you can couple this system to gauge fields, where with the subsystem symmetry becomes the gauge symmetry. Or you can study the gauge fields on their own, the gauge fields without the matter theory. Most of the condensed matter literature, and also in the previous talk, you saw some discussion of this classical theory, where the speaker wrote the analog of Maxwell's equations for such a scalar field coupled to the gauge fields. Much more interesting is to study the quantum theory. And in the case of the pure gauge theory, we have done it in a lot of detail in our papers. You can also Higgs these U1 gauge symmetries and have Zn versions of them. And I did it here in 2+1 dimensions. You can do it in 3+1 dimensions. So we have analyzed of the order of, depending on how you count, of the order of 40 different models, with kind of doing all sorts of things like that, not all of them at the same level of detail. And for the purpose of half an hour talk, which is now almost 50 minutes, I picked to discuss only one particular example, the simplest of them. But there are many other knobs you can turn.
Okay, thanks.
Okay, so thank you, Professor Seiberg, for a very beautiful talk and the subsequent discussions. Thank you very much.
Thank you.
Alok has suggested that we will not have the break and we will go for the last talk of this session. So I invite Ahmed Almeri from the Institute of Advanced Studies in Princeton. He will talk about the entanglement wedge of the couplings. So Ahmed, can you please share your screen?
So I actually decided last minute to change the topic of my talk.
Okay, okay.
So instead, I'm going to be talking about comments on the final state proposal and the gravitational path integral. Can you guys see my slides? And can you hear me? Everything's fine?
I can hear you.
Yeah. Yeah.
Okay.
Yeah.
Hi. Yeah. Been a while. How much time do I have for the talk? Speaking time?
You have 25 minutes and 5 minutes per talk.
Okay,
so
thank
now
you so much.
It's 7:15. It's 7:15 p.m.
Okay,
here in India.
All right. Okay, thanks a lot for the invitation to speak at this wonderful conference. I obviously couldn't attend all the talks, but I'll make an effort to watch them on YouTube later. So I'm going to be talking about a somewhat new perspective on an old idea on the final state proposal based on lessons that we learned from the gravity path integral. So this talk is a little bit about the information paradox. So let's review that. In the semi-classical approximation, let me just move this video. Okay, so in the semi-classical approximation, we know that the entanglement entropy between the black hole and the Hawking radiation grows monotonically because the radiation outside is entangled with its partners behind the horizon. Schematically, I'm going to describe the situation with, well, this picture and this quantum state for the radiation. This is supposed to represent some maximally entangled state between R tilde. Tilde will often mean particles behind the horizon, and R outside the horizon, and they're entangled, and the total dimension of the Hawking radiation Hilbert space is D. And this state comes about due to vacuum entanglement of the quantum field theory on top of this gravitational background, the black hole background. The state on a Cauchy slice at late times looks something like this. Here's this red, on this red slice, we have the total global state psi. It describes the matter which formed, or the star which formed the black hole in some state I, tensor product with the state of the Hawking radiation. If you're a purely outside observer, the state would appear from your perspective to evolve from a pure state of the infalling matter to a mixed state of the subsystem R, and hence information has been lost. The pure state I goes to a mixed state rho R, which for our purposes can be thought of as just the identity matrix. You can diagnose this the purity of the state by computing something called the purity, which is also called the second Renyi entropy, which is trace of rho squared of the system you're interested in. And in this particular state, because R is maximally entangled with R tilde, you get 1 over D, which is not equal to 1. If the state was pure, you would get 1. So that's the information paradox, but this talk is also about the firewall paradox. So let's review that as well. If you suppose that there's no information loss, then the entropy of the Hawking radiation must start to decrease after the page time. So we know that in order to have unitary evolution, the entropy of the Hawking radiation should go up and then come back down. It's always going to be bounded by Hawking's answer, the von Neumann entropy of the radiation, and the coarse grain entropy of the black hole, the area of the horizon over 4G. The statement here is that after the page time, or the additional constraint that comes from this unitarity condition, or that information is not lost, is that the outgoing Hawking modes after the page time have to be entangled with the old radiation far away. Or sometimes this old radiation is called the early radiation. Basically, whenever new modes come out, they have to purify the Hawking cloud far away. However, this seems to conflict with something else that we want. Namely, in order to have a smooth horizon, vacuum near the horizon, we know that the outgoing mode has to be entangled only with the interior partner. Sometimes I will call this the no drama condition. So the conflict in the firewall paradox is that you need the late outgoing mode. It seems like it has to be entangled with 2 different systems. So these 2 requirements are contradictory due to monogamy of entanglement, as shown by in a bunch of works in the early 2000s. Well, in the early 2000s and also in 2012. The upshot of my work with Morov, Polchinski, and Sully was that a single infalling observer can potentially witness this contradictory state. If you have an infalling observer, like suppose you assume that you want everything, you want both vacuum at the horizon and unitarity. We know that that's an impossible quantum state, and what we showed is that an infalling observer, in principle, would be able to witness this impossible quantum state, and hence it's really a paradox. So, all right, so that's this picture here. And our suggestion was that perhaps one should replace the horizon with a firewall. And some other proposal was that maybe you should, one way to get around this paradox is to instead impose some non-local encoding of the interior as part or as a subsystem of the outside radiation. I will talk more about this later. So this is the outline for the talk. I'll first discuss this old proposal of Horowitz and Maldacena on the final state. Then I'll discuss some problems that were pointed out of the final state. I'll propose a fix, and I'll motivate that from the gravity path article. Okay, so the point is that in order to quote unquote solve the information paradox, we need a mechanism that would move the information from the inside to the outside. What Horowitz and Maldacena pointed out was that this is doable via post-selection, where you simply declare that the state of the singularity is predetermined. It projects on the quantum state that evolves into it. Sort of the rationale behind the proposal is that we like to think of the initial singularity that the Big Bang singularity that gave rise to the universe, if it's actually there, that it has some initial state. It comes with an initial state. And so why can't future singularities also come with a final state? And now the idea is the following. So the idea is that here's the picture of an evaporating black hole. You declare that there's some Bra vector on the singularity which acts on everything that falls into it. And the state is a non-normalized state. There's some factor D, and it's a maximally entangled state between the infalling interior Hawking modes and the matter that fell in. Up to a unitary that acts on the matter. Okay, so that's the upshot. That the singularity projects the matter and the interior Hawking particles into a maximally entangled state. Let's see how this gives a channel for the information to come out. So you can see this most clearly by representing this space-time with a projection in terms of a quantum circuit. Here, this line here represents the infalling state of the matter in some state I. The state phi d here of r tilde r represents the entanglement between the interior and exterior Hawking modes. Now the additional ingredient is that we impose a final state that projects on the subsystem M, including r tilde. And it's a maximally entangled state as I described, up to a unitary on one of the legs. And so what this does is that just from the quantum circuit perspective, this gives you a channel for the information I to go through the circuit and appear in R. This unitary S that we acted here ultimately ends, it appears in the state of R as S acting on I. So this S should be thought of as the S matrix of the black hole. So this entire circuit can be collapsed into this equation down here that you end up with a pure state of the Hawking radiation if you post-select, and S is the S matrix as I described. Okay, so the upshot is that the state I of M evolves to the projected global state psi, which is a pure state of R. To analyze this proposal more, we need to consider a slightly modified setup where you take the matter that formed the black hole to also be maximally entangled with some outside reference. Okay. So imagine instead of collapsing a star in a pure state, you collapse a star in some mixed state that's entangled with something else. I'm going to write that state like this. Okay. So the global state now, I'm sort of I'm just considering some arbitrary decomposition of the state on this slice. I'm going to separate out some a qubit's worth of sort of maximally entangled pair across the horizon, B tilde B, and also the remaining everything else, the remaining radiation, and also the matter that formed the black hole into some entangled state R tilde R. Okay. Now, in order to have unitarity here, there's a condition that one needs to impose on the final state. The condition is that if you take the final state and you trace out R tilde, then the remaining density matrix of B tilde has to be the identity. What this essentially just means is that there's an isometry from B tilde to R tilde. Okay? So the state on F, well, that's one way to say it, that there's an isometry from B tilde to R tilde. Another way to say it is that in the final state, B tilde is maximally entangled with R tilde. Okay, as in the density matrix of B tilde is the identity. Again, it's not normalized perfectly. Well, it's just not normalized. The upshot again is that this, if you impose this condition, then this guarantees that B is going to be maximally entangled with R after you project to the final state. So again, you end up with a pure state of the exterior. B and R are in a pure state. Now we can ask, how does the final state, or what does the final state predict for the AMPS experiment? In order to answer this question, we first need to define the measurement operators. So let me first define the no drama operator, the operator, the measurement which checks, or in this case confirms, that B tilde and B are in the appropriate maximally entangled state. Okay, so this would be the measurement that checks that the horizon is smooth. There's another measurement that you can do which checks unitarity, namely that that BR are in a pure state, and also not any pure state, but the pure state that was prepared using the final state projection. Okay, so this is a measurement purely on the outside that checks that the Hawking radiation, that the entire cloud of radiation is in the correct pure state. Now, we're trying to define, we want to define probability. So, but in a modified, in some sense, in a modified, in a modification of quantum mechanics. The way you define probability here is you take the state psi, you project onto the measurement result that you want, and then you project to the final state, and then you take the square of that. Okay? So that gives you the probability of finding the measurement result associated to a given projection. So usually in regular quantum mechanics, this F would not be there. But here we're doing post-selected quantum mechanics, so the rules are slightly different. Let's compute the probability of there not being any, of there being no drama. Okay, so if you look at so this is the probability of finding that B tilde and B are in the appropriate final state, or in the appropriate entangled state. So if you focus on this diagram here at the bottom first, this is, if you ignore this blue square, then this is the state that you, well, it's the state of the radiation, or rather the state of the system, given the final state projection. And now what we're doing is that we're inserting into the quantum circuit the projection. Okay, so this now describes a quantum circuit where a measurement has been done, and you have to square it to get the probability. So that's this other, that's the top half of the diagram. Now we can evaluate this diagram using the condition that we talked about before that ensured that you had an isometry from B tilde to R tilde. So that's this condition here, and you get 1. Okay, so this is the diagram that shows if you keep track of all the factors, count the number of loops, and so on, you get 1. Okay, so the horizon, the upshot is that the final state gives you the horizon, it gives you a smooth horizon with probability 1. You can then ask about a different question. You say, well, what's the probability of finding unitarity? Namely that, that the outside state is in the correct pure state. Again, all you have to do is you have to insert these projections, and then use the properties of the final state. And this circuit diagram becomes, again, a bunch of loops. You count all the factors, you get 1 again. So awesome. So the evolution is unitary also with probability 1. But so far we talked about each measurement by itself. But recall that the AMPS experiment is about a single observer that does 2 different measurements. For that, we need to consider the probability of finding that B and R are in the appropriate pure state, and that B tilde and B are also in the appropriate pure state, in this order. So you first check that the outside, you have an infalling observer. This observer is falling in from the outside. They first check that the outside is in the right state, and then they check that the horizon is in the right state. Just by causality, this is the right order. So again, you put in the circuit, this means you first do the outside measurement, and then you do the inside measurement. You evaluate this circuit, and you get 1/2⁴. Okay, so you don't get 1 anymore. And this is weird. So to recap, the probability of the blue measurement is 1, the probability of the red measurement is 1 individually. But if you perform both experiments in this order, then you get 1/2⁴. This is acausal. The statistics of the unitarity measurement seems to depend on whether in the future you're going to check or you're going to perform the no drama measurement. And that's simply crazy. Let's take a closer look at the unitarity measurement. There's something funny about it. So that's given by this expression here. So right now I'm ignoring the no drama measurement. If you write this, well, the projection pi_br is given by this red box. The thing to note is that this state has 2 final state projections. One, which was originally defined, this F here, and one from the ket of the measurement operator. And so what seems to be what we seem to have is that we seem to have 2 different black hole interiors. There's the R tilde B tilde black hole interior, which was associated to the original final state. But then there's an R tilde prime and a B tilde prime, which are introduced by the operator. And so the question is, which of these is the true black hole interior? The answer to this depends on whether one considers the interior as a subsystem of the outside or not. In the following sense, if you were to take it to be on the outside as part of the outside, then if you do a measurement, a projective measurement on the outside, you should also project out the inside. Essentially, the proposal is that this circuit here should instead be drawn in this way. You have some state, and once you do a measurement, you completely project out that state, and what you're left with is the new ket what you're left with is the ket from the projection operator. This is familiar from standard quantum mechanics. If you have some state chi, now you want to measure if the state chi is in the state chi, you act at this projection chi. The new state is given by the ket of the projection operator. This is how standard quantum mechanics works. In some sense, whenever you do any measurement, you completely destroy the system that you have and you create a new system. You can think of it like that. And the idea is that in this setting, when you do a measurement on the radiation outside, you remove the old black hole interior is removed, and you create a new black hole interior. And this reinterpretation actually fixes this acausality problem. And the APS experiment now succeeds with probability 1. So here's a circuit diagram of what I'm saying, in that, so you start with the state of the black hole, then you do the BR measurement, that's this thing here. But after doing the BR measurement, you've introduced a new interior, and hence when you do the B tilde B measurement, that has to be performed inside the new interior, not in the old interior here, which is way in the past in some sense. Okay, and if you do this, you get 1. So the probability of first checking that BR are in the appropriate pure state, and then checking that the horizon of the newly created black hole is in the pure state, then you get 1. Okay. In some sense, the problem that was found before by Basu and Stanford was that from the circuit perspective, they were trying to reach, after doing this red measurement, they were going backwards in time in the circuit picture, and that's the source of the acausality. The remainder of this talk will be about justifying this picture from recent results of using the gravity path integral and the page that reproduce the page curve and so on and so forth. So let me quickly recap that. So there have been some recent insights from the gravity path integral regarding quantum entanglement in the theory of gravity. And so let's analyze this using a simple gravitational model that has aspects sort of similar to the final state. Let's consider closed universe states with particles that are prepared using the gravity path integral. I think something like this was considered in the paper of Pennington et al. So the picture here is that you have some Euclidean boundary, Euclidean ADS boundary, where you insert some states I and A, some particles say, and at some point there are end of the world branes that fall in from the boundary. This is just a way of preparing a closed universe. So I will call the state prepared, the state that the path integral prepares using this prescription as psi IA, C for closed universe. Now imagine introducing a reference system R, which you entangle with one of the particles, let's say the purple one, and let's say that the dimension is of this purple particle is large, and so then we have some entangled state like this. Naively, it looks like there is non-zero entanglement between the reference and the closed universe, right? So this purple particle is naively entangled with R. So I will demonstrate two things, the first is that R is secretly in a pure state, and that the operators on R can affect the state of the closed universe. The upshot is that operations on R, the way that they affect the closed universe is that they project out the closed universe, and they create a new closed universe with a new excitation in it. Let's first talk about the entropy. Suppose we compute the density matrix of R. So naively, what you do is, you just trace out the closed universe, so you get a picture like this. And actually, this picture would give you a mixed state for R. A more careful definition is the following, where essentially the prescription is to not fill in gravity unless you're computing a number, like the traces and so on. So when we talk about a density matrix, you should not fill in gravity yet. The norm of the state is just trace of rho. So now we're computing a trace. So we connect the outside indices of R, and then we fill in gravity. There's this, what I'm going to call the disk configuration. And this disk gives you a factor of the partition function z, which cancels with the normalization, and you get 1. And there's a factor of d coming from this loop. You can then compute you can check whether the state is pure or not by computing the purity, which is the second Renyi entropy, trace rho squared. And what you find so you set it up in this way, and then you fill in the gravity. And what you find is that there's a way of filling in the gravity that gives you the original answer squared, okay, plus corrections. And we just said that the original answer is 1, so this is 1 plus 1 over d. So R is approximately pure for large d, as required. For the experts, this is actually exactly pure. This 1 over d is not there, in the sense that trace rho squared is equal to trace rho all squared. If this was cryptic for those unfamiliar with this, maybe we can talk about it later. It's not that important for the talk. Okay, so the last thing is the fact that the closed universe should be thought of as a subsystem of R. This can be demonstrated by finding operators on R that modify the state of the closed universe. This is related to this PETS map discussion of the paper of Pennington et al. The claim is that the following operator, well, so far this is trivial. The following operator, OR, it takes a closed universe of state A to a closed universe in state B. Yeah, so let's define this operator, and one can check that the way that you check that this does what I claim it does is by computing its overlap, or rather its matrix element between a state of the universe with a particle in state A and one with a particle in state B. So and show that it's equal to 1. And so this picture here is given by this picture, and these are color coded to show what corresponds to what. And again, if you take this overlap, you get 1 plus 1 over d. Okay? So you get the same. It's 1 to very good approximation when d is very large. The upshot here is that when you act with OBA on the state psi, the way that it gives you a new closed universe with the state B is that you project out the closed universe in the state A, and what remains is the closed universe in the state B that comes from the ket of the operator. Okay, so the old closed universe gets projected out and a new one is created. Let me give one more very quick example, which comes from the evaporating black hole setting. This again is going to be schematic. So here's a picture of an evaporating black hole, which has some particle in the state A that falls into the island. OBA, the operator on the radiation. So here's an operator on the radiation. It acts, these I, J matrix elements act on the radiation subsystem. And the claim is that this takes the black hole from the state A to a black hole in the state B. And the way it works is the following. When you act with ORBA on state psi, so here, this is the operator and this is the state. It takes, you construct a new spacetime that is composed of segments of the old spacetime and also of the operator. So the action, so this operator acts on the radiation. So that's, well, the way it acts is that this pink region projects out the pink region of R, and it gives you a new radiation segment. The green segment of the operator projects out the island, the inside of the black hole, and the new interior comes from the operator. And the portion in the middle, because the operator doesn't act there, is retained from the old black hole. So you have this is your new spacetime composed of new segments and an old segment. So that's pretty much everything I had. So let me just quickly review. So I reviewed the final state proposal and also talked about the criticism where it leads to these paradoxical results, this acausality. I motivated a fix of the final state, which takes into account sort of the intuition that the inside of the black hole is secretly a subsystem of the radiation, and that the interior can be get swapped with a new interior when you act on the radiation. And I motivated these, or rather motivated this intuition based on some concrete results from the gravity path integral that demonstrate that operations on the radiation influence the interior. That's all I had. Thank you very much.
Thank you, Ahmad, for a very nice talk. Are there questions? At least I didn't see anything here, but if anyone has question, please ask. Well, if not, then please thank Ahmad again.
Yes, I have a question. I have a question.
You have? Okay, yes. Okay, please. Yeah.
Yes, sir. In the AMS experiment, was entangled black holes considered?
You can apply the AMPS argument to entangled black holes, yes.
So if you have entangled black holes which are close enough, can the Hawking radiation from one have any kind of effect to the interior of the other, and hence the order in which we did the experiment, it might change the interior?
Sorry. I think I misunderstood your question. So entangled black holes, like you mean like a wormhole? Is that what you mean?
Yes.
Yeah. So that case is an example where the let me see. So I would say that's the simplest example where the quote unquote interior being part of the radiation is well, it's an example of that. So when you have entangled black holes, like a wormhole, there's no firewall, as you know.
Recording in progress.
I guess what I'm saying is that so there's some echo. Can you guys hear me?
Yeah, Ahmed, yeah, we can hear you. Swapna, I think there's some echo. Are you logged in from two devices, or somebody is? Probably.
Yeah, seems to be some.
It's probably better now.
Yeah. So
okay, can you hear me?
I can hear.
Recording in progress.
No,
it's okay. Ahmed, you could go on with your answer. Sorry.
I was going to ask the previous the person that asked the question to maybe repeat the question. Maybe I strayed a bit too far.
Okay.
Deepan, you can please go ahead and.
Yes. If we have two entangled black holes or a wormhole which is traversable, in that case, can the Hawking radiation of one be entering the other, and hence will that change something and hence will that also change the black hole interior or the singularity or the final state projection which we have taken?
I'm not entirely sure, but I would, if I was to make a guess, I would say no.
So in that case, also the AMPS thing will work, and the AMPS experiment will work, and the order will remain the same for the AMPS for the measurement in the circuit, and the final state, and the final projective black hole interior, which we took.
I think the the quick answer is yes, as in like in the sense that things, the final state, applying the final state proposal there with the fix that I proposed would continue to give consistent results, and there would not be a firewall. I think, I hope that answered the question.
Okay, thank you, sir.
Okay, Gautam, please go ahead.
Thank you. Hi, Amit.
Hi.
Thank you for a nice talk. Yeah. I just had a small point, some curiosity actually, that that your model sort of states that there'll be a projection, there'll be a final state projection, right? Is this projection unique when you make a measurement on the radiation system?
Yeah. So this projection, as I said before, that it has in it the details of the S matrix of the black hole. It provides the S matrix, and hence it's the details of the final state should ultimately be fixed by the theory that you have. So it's not a choice that we make. It's supposed to be part of the full UV complete theory that describes black holes. And no one up until now, I mean, we don't have that much information about, well, if that, well, there are no concrete proposals for what the final state is yet.
Okay, thank you.
Karan, please go ahead.
Yeah, I just wanted some clarification perhaps on the filling in the gravity afterwards part, which was there on the trace rho squared slide, I guess, the part where you were giving the prescription. So is that just a standard gravity path integral that we're performing here, or, I mean, subject to certain boundary conditions, or is there anything more to this?
No, that's it. So you set up the calculation in this way. You say you have some boundaries, and then you impose some boundary conditions, and then now you allow for all gravity configurations that satisfy the boundary conditions.
Okay, so it's just the subjecting of boundary conditions. That's nothing else.
Correct.
Okay, thank you.
Somdat, please go ahead.
I have a question. Like, I've always wondered, like, how can a quantum state, a pure state which has to be a quantum state, how can it gravitate unless it collapses to a classical state or a classical configuration? How can such a thing gravitate? And if it collapses to a classical state, then the information is lost in any case, right?
I don't know what you mean by collapses into a classical state.
So for instance, if you have a quantum state, if you have a quantum field theoretic state, right?
Mm-hmm.
It would have to collapse to some classical state before it can gravitate, because unless it collapses to some classical state in a specific space-time, it can't gravitate with the gravity in that space-time.
I don't see why not. As in, I mean, I'm worried. I don't want to get into interpretations of quantum mechanics, but I mean, in our world, I believe everything is quantum, and there's some quantum state that describes me and the Earth, and I still feel its gravity. So I don't the gravitational force would not be there in a quantum description of the system.
Oh, sorry, I lost my internet connection. I think it's okay now. I don't know. Are there more questions? Because I lost the connection in between.
No, Swapna, I think we're done.
You're done?
I don't see any hands, but you can ask again.
Okay, so then I thank all the speakers of this session for delivering very nice talks. And I thank all of you. So now it is over to Alok.
Well, thank you so much, Swapna. Thanks everybody, all the speakers, and it's late here in India, so thank you, and thank you, Ahmed. All right, so folks, see you tomorrow. starting at the regular time. Thank you.
Yeah, thanks.
Thank you,
Bye-bye.
Alok. Thank you, Sapna.
Thank you. Bye-bye. All right, team, I think we can start the recordings. In the meeting.